Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. Some of you may have gone through our Linux Forensics course, which was notable as one of the most comprehensive courses around that used free and/or open source tools. So we have a new course for you. I'm very excited to be able to be your instructor for this course. Now, those of you that don't know me, a little bit about me. You may have seen me around if you go to any conferences. I tend to go to a lot. I tend to speak at a few. Spoken at DEF CON 6 times in the last 4 years, for example. I've done some repeat performances at places like Black Hat, GERCON, 44Con, B-Sides, Forensic Cure, etc. So I've been known to speak at a conference or two. Also been known to write some books. I wrote a book called Hacking and Penetration Testing with Low Power Devices, and this is a book that tells you how you can build your own low powered hacking devices that you can plant around your target and hack them remotely. We also wrote a book called Linux Forensics that was the first book published by Pen Tester Academy. I've also written another book on USB forensics. At my day job, I'm a digital forensics professor at Bloomsburg University of Pennsylvania. I've been programming since I was 8 years old, in assembly since I was 10, and hacking hardware since I was 12. I'm also an aviator and plane builder. I have a dozen ratings, a couple thousand hours of flight time, and have built planes and done other fun things with aviation. So let's talk about this course. This course should have a lot of fun stuff. We're going to start out talking about live response. So we will talk about human interactions. How do you interact with the people involved in your incident response? We're going to talk about how you can create a live response kit, how you can minimize disturbance to your subject system by transporting data across the network. We'll talk about collecting volatile data of different types, and we'll decide whether or not it's justified to perform a traditional dead analysis. We will also talk about dumping RAM if you want to use some of the new exciting tools like Volatility. We will talk about acquiring file system images. The traditional file system analysis is still the most powerful. It's very mature. It's something that we've been doing for decades. So we pretty much have figured out how to do this. So we'll talk about tools such as DD, DCFLDD, DC3DD, etc. And we'll talk about things like write blocking, using software-based write blockers and hardware-based write blockers. We will talk about analyzing file systems. How can you mount images? How do you find the strange? You don't want to look at just the normal stuff. There's so much data today that you need to find the strange stuff. We'll talk about some searching tools that can help you with that. We'll talk about authentication-related files. We'll show you how you can recover deleted files and how you can find hidden information. We will show you how you can do all of these things using open source and free software, such as the Sleuth Kit and Autopsy, how you can get volume information, file system information. We're going to dig deep into FAT file systems and NTFS file systems, directory entries, show you how you can construct timelines. We'll spend a bit of time on timeline analysis so you can see things like when the system was installed, upgraded, booted. Are there any newly created files that might be related to malware? Are there any changed files, maybe some Trojans that have been installed? Are there files in the wrong place? Has someone been trying to exfiltrate some data from your system? And we're going to dig pretty deep, just as we did with the Linux Forensics course. We're going to show you everything you could ever want to know about FAT and NTFS. So this will allow you to find even the more advanced attackers because you know everything there is to know about these file systems. We'll also show you how you can search unallocated space on your media. We will delve into network forensics, How can you use snort on some packet captures? Things like TCP stat. How do you separate conversations with TCP flow? How can you trace backdoor traffic also with TCP flow? These are some of the things we'll talk about. We will talk about file forensics, understanding file signatures so that you can find files that have the wrong extensions, which is an easy way to hide information in Windows because of how it works. We'll talk about finding things in swap space, how you can reconstruct someone's web browsing history, their cookies, browser caches, etc. How can you deal with unknown files? You can look at hash databases and see if it's a known bad file. We can also use things like the file command and strings command. We will look at log files. We will look at the recycle bin and show you how you can get files back from there. We will talk about something called prefetch files, which also can provide information. We will talk about alternate data streams, which are something specific to NTFS. Other things we'll talk about. We'll talk a lot about the Windows registry. The Windows registry is rich with information for the forensics investigator. We will use some tools such as RegRipper. We'll also talk about Python, and we'll see how we can get system information out of the registry. How can we get some of these auto start programs? We'll find that there are a lot of places that you can put things in the registry in order to auto start something. We will talk about USB devices and all of the information pertinent to these that is stored in the registry. We'll talk about user information that is stored in the registry. Past and present mounted devices, user activity, system restore points. We will spend a lot of time on the registry because it does provide an awful lot of information to the examiner. We will talk about memory forensics. We will use tools such as Volatility to retrieve process information, look at various Windows objects, search for malware, look into event logs. They're not just stored on the disk. There's also information to be gleaned from memory. We'll look at the registry in memory. We'll look at how we can reconstruct some network artifacts, looking at Windows services, the Windows graphical user interface. We will look at file systems information in memory. We will look at ways of detecting kernel rootkits in memory, and we will look at creating timelines based on information stored in memory. We will also look at reversing Windows malware. So we will look in depth at Windows executables, including looking at the headers, imports, exports, Windows resources, some obfuscation techniques, dynamic linking issues, and we'll do a little bit of command line analysis. We will also talk about how you can carefully run malware inside of a virtual machine, of course, while you capture some traffic and you leverage various debuggers. We will even talk about what do you do when it's all done. It's not done until all the reports have been written. So we'll talk about using tools such as Autopsy, Stratus, and OpenOffice in order to lessen the pain of writing reports. So what are our overall goals here? We're going to leverage open source or at least free software as much as we can. We're going to go for completely open source stuff. Occasionally we will find some useful software that is at least free. We're going to get very hands-on and practical with our exercise and our demos throughout. We're going to be hands-on, but at the same time we're also going to be very technical. So we're going to dive deep into things like the file systems that you find on Windows, into the registry, etc. So we're not going to emphasize any particular tool, certainly not any super expensive commercial tools that might run you over $10,000. We're going to show you how you can do some thorough Windows forensics using free software. And of course, one of our other goals overall is we want to provide you with the most comprehensive Windows Forensics course available. So hopefully you will set off on this journey with me, and I'm very much looking forward to this, and we will see you soon in our next video. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to start talking about some forensics basics. So we're going to start with some background material. At the most basic level, you probably need to know what forensics is if you want to study it. Now, Merriam-Webster says forensic is a noun which means belonging to, used in, or suitable to courts. My definition of forensics is forensic science or forensics is the scientific collection of evidence that's good enough that it could be used in court. It doesn't have to be used in court, but it is of sufficient quality that it could be used in court. Now, there are different kinds of forensics. Many of you are likely familiar with physical forensics. We talk about things such as transfer, where anytime two things interact, there's some transfer of materials. Things like if you hit another car, you will have some paint transfer. If you touch something, you will have fingerprints which transfer, and you will also have things such as DNA. We're going to talk about digital forensics, things like network traffic, what's going on there, data storage, small devices, and computers. Some general principles when we're looking at digital forensics. We want to maintain the integrity of the evidence. We want to maintain what we call the chain of custody. The chain of custody, when it comes to physical evidence, is often in the form of a document that is a part of or attached to a container in which the evidence resides. And typically, this document will list everyone that has ever touched this evidence from the moment it was collected, and this assures that no one has tainted it. We also will try to document everything. I know that lots of us like to use digital documentation. We like to have our electronic tools, but this is one of those cases where handwritten documentation can be better. Also, if possible, I recommend you work with a partner. It helps if you have one person documenting and one person working. Other advantages of working with a partner, you have another set of eyes, and if anyone were ever to question what occurred, you have another witness. You also want to follow standard procedures. If you follow standard procedures, then people have less of an opportunity to question what you've done. So phases of investigations. The first phase is what we call evidence preservation. In the medical field, they say first do no harm. We have something similar. We say first don't destroy the evidence. The next phase is evidence searching, trying to find evidence. We'll talk later what evidence is. Now, this phase has become more complicated and more lengthy because storage has exploded. Today, your typical desktop computer has 1 to 5 terabytes of storage. If you look back 10 years, it was nowhere close to that. And then finally, we have the most fun stage, event reconstruction, trying to figure out what exactly happened anyway. Most of what we will talk about concerns incident response. It is certainly true that the forensics techniques that we will learn can be used in other circumstances as well, such as finding evidence on someone's devices, but our primary focus will be on incident response in this course. So if we are trying to do incident response, the first thing we want to do is validate that there actually was an incident. Then we want to preserve, search, and reconstruct our events. We might need to do some preliminary investigation to determine if there was an incident. We'll talk more about that in later videos. And remember, it's not all done until those exciting reports have been written. I know it's not a favorite thing for many of us to do, but it is a necessary thing. So what does this process look like? Here is a picture of the overall incident response process. Somebody calls you and they say, hey, I think something happened. The first thing you want to do is determine whether or not something did happen, whether or not there was some sort of a breach or other security incident. Then, if there was, you might decide to perform some live analysis, find what you can find before you take the system down. Some cases, it might not be easy to take the system down, and you might have to live with just what you can get from live analysis. You can make the decision whether or not to perform dead analysis. If not, you can write your reports and document your lessons learned. If you do dead analysis, we'll show you how to acquire those images and then perform that actual dead analysis. So there you have it. That's just a high-level view of what we're going to talk about in this course. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about some first steps. You're just trying to get started doing some Windows forensics, so what are the first steps that you need to take? As a review, we talked about the overall process last time, where you have some sort of a call that's placed telling you that someone thinks there's been an incident, and then your normal first step is to perform some sort of live analysis. Typically, this will be a limited live analysis that you perform in order to see if an incident truly occurred. Now, before this happens, it pays to be prepared. So what do you want to do? You want to have a response kit of some sort set up. Now, ideally, you will have a 32-bit and 64-bit version of each utility that you might want to run. Also, ideally, you would have CD-ROM and USB with these utilities on it. Although, to be honest, today, less and less systems would require the use of a CD-ROM. Now, we will build these tools throughout this course. You will also need some hardware. You'll need some write blockers. If you're going to make images of subject drives, you will need some media, a place to put these images, RAM images, etc. What I personally like to use is an external USB 3 hard drive that I will connect to my forensics workstation. Why is that? It is very easy to share an external USB drive. USB 3 you want for the speed. It is not that expensive today to buy a decent size external USB 3 hard drive, which you can expense to your client. So whenever you go out on an assignment doing an incident response, you should have at least one decent sized USB 3 external hard drive with you. You will also want your forensics laptop. We'll talk a little bit more about that in a bit. Other items you should have. You should have your notebook. Well, what kind of a notebook? A bound notebook with numbered pages is ideal for taking notes. It's great. It doesn't require any batteries, and it's easy to take with you. It's also great in the case where someone might accuse you of adding or deleting something from your notes. You can show pretty easily that you didn't insert a page into a bound notebook. And if the pages are numbered, you can very easily show that you didn't remove anything either. So here's a good example of a nice cheap notebook. It's bound. I just have a little bit of a note saying that it belongs to me. And this one did not come with pre-printed page numbers, so I just wrote some on there myself. So let's talk about your forensics workstation. Your forensics workstation should have at least 8 gigabytes of RAM. Ideally, it will have at least one USB 3 port. It should have wired networking available. So if you like one of those ultra-thin laptops, it may not be the best choice if it does not have a wired network port and you want to run a 64-bit Linux distro. There is no good reason to be running 32-bit Linux today. Now, this distro could be a specialized distro such as Swift, or if you're new to Linux, you could pick something such as Ubuntu or Linux Mint, which is based on Ubuntu. They're both very popular, or your favorite distro. Personally, I do not like to run the specialized distros for a couple of reasons. One reason is that normally these will run as a live distro. Running anything as a live Linux distro is going to give you less than optimal performance. So don't do that to yourself. Another thing I will say about many of these specialized distros is that they normally come with a theme that most people find obnoxious for day-to-day use. And some of them lack repositories for all of the common tools that you might like. So how do you install these tools? Well, Swift is a good starting point. Now, if you want to install Swift, you can do so on top of Ubuntu 14.04, not 14.10, not 15.4, or any other version of Ubuntu. It is very specific, and here's the command to do that. You just use wget in order to get a script, which is then passed to bash. Now, if you want to just install the tools, which would certainly be my recommendation, you can use a different version of this command. The biggest thing you'll notice is that this -s-y is missing from the command if you just want to install the tools. As I said, this is problematic if you want to install on a different version of Ubuntu. So if you have a different version of Ubuntu, how could you go about that? Well, you could use a script such as the one that I've written here. So here I have a pretty simple script. It starts out by adding some repositories here. So I add some of the standard repositories that Swift uses to my normal set. And here are a bunch of packages that I would like to install. So I have my big list of packages. And here's my actual script. I first do an apt-get update, and then for everything in my package list, this line does here, I run the following. I start by checking to see if it's already installed. So dpkg-list will list all installed packages. I then pipe this to awk, and I print the second item. I then use egrep to check to see if that second item matches the package name that I'm trying to install exactly. As a reminder, the caret anchors it to the start of the line and the $ anchors it to the end. So it is looking for an exact match for the package name. I'm sending errors to dev null just so they're not printing to the screen when things are not found. So if I found it, then I just echo that the package was already installed, else I echo trying to install, and then I check if the install succeeded. So I have another if statement, and I use apt-get -y. -y says if it asks me yes or no, should I automatically answer that prompt, I will install the package. Once again, errors go to dev null. If it's successful, I echo succeeded. Otherwise, I echo failed. I close this if here. I close the other if there, and I use done to end my loop. So that's it. It's a very simple script. that I'm using here in order to install just the tools I want into my favorite version of Linux that's based on Ubuntu or Debian. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. I'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pentester Academy. In this video, we're going to talk about starting an investigation. So another look at our high-level process. We've just gotten started. So we're right here in our incident, yes or no box. We're getting ready to do just a little bit of limited live analysis in order to make that determination. So has there been an incident? What are you going to do? First, you're going to open a case file. This is not as complicated as it might sound. All you need to do is decide on a case file name. If you don't know what to use, you could use something like the date. And if you are very busy and you have more than one case in a day, you could use a suffix for the number of case in that day that you opened. Next, you want to talk to the users. Ask them questions such as, why did they call you? Did they call you because they lacked internal expertise on Windows Forensics? Or did they call you because their company policies say that whenever they suspect there's a breach, they must call an outsider? Why do they think there's a problem? Is there some strange activity on a Windows system? Is there a peak of network traffic? Is there funny network traffic? Ask them why they think there's something strange going on. Find out what they know about this potential victim system. What is it normally used for? Where did they buy it? Was it shipped from an online vendor, possibly intercepted? Did you buy it at a local store? Has it recently been repaired? Maybe somebody did something to it while it was being fixed. You need to start your documentation process. Previously, we talked about having your nice bound notebook with numbered pages so you can start taking some notes. What did the users say? What do you know about the subject system? You might consider taking some pictures of the system and the screen if you think it's appropriate. If you're not sure, just take them anyway. Most of you probably have a digital camera on your phone, and electrons are cheap. So go ahead and take a couple of photos, if you will. You are now ready to actually do something with the system, to actually begin interacting with it. What's the first thing you want to do? You want to mount some known good binaries. Now, this is a bit more complicated than the situation that you have with Linux. In Linux, it's pretty easy to just mount a bunch of known good binaries, but in Windows, you do not have a proper shell. Well, what do I mean by that? On a Linux system, if you are running a shell like bash, whenever you type a command, you are actually executing a program. In Windows, however, if you run the command prompt and you type a command such as dir, it does not run a separate program. It runs a subroutine within the command prompt. So it is not an actual shell. It's just a program that accepts some commands. Other complications with Windows. Windows is highly dependent on dynamic link libraries. Because of this, you can get into what's known as DLL hell, where you don't have the right DLLs and or the DLLs have been compromised in some way. And it's hard to get standard utilities that will run correctly if this has happened. Once you have mounted some of your known good binaries, you need to check your path to make sure that your programs get run first. And as we said, you cannot completely replace Windows binaries. Because of these factors, advanced malware can hide its presence from you when you're doing a live response on a Windows system. It is not 100% accurate. However, in most cases, you will be able to find at least something that leads you to believe that a compromise occurred. I recommend that you use a USB 3 flash drive for your response drive. The performance will be much better. That said, for your practicing, if you're going to use VirtualBox, as I will do in this course, you should probably stick with USB 2. The reason for that is even with the latest version of VirtualBox, which is version 5 right now, that claims to support USB 3, I have had a lot of difficulty getting USB 3 drives to mount successfully in Windows systems running inside of VirtualBox. So you can also save yourself a couple of dollars or whatever currency you choose to use by buying USB 2 drives. Now, one of our goals is to minimize the disturbance to our subject system. So what things should we keep in mind? Don't install anything to the subject system if you can help it, and you probably can. So you should have everything you need on your thumb drive. Don't create any new files on the system either. Try to minimize your memory footprint. You might want to try to do some memory forensics later with a tool such as Volatility. Some possible solutions. Netcat, the Swiss Army knife for network packets. That is, in my opinion, the best solution. Another possibility is to store things to your USB drive. Now, this might sound like the best solution initially. However, if you know anything about USB, and by the way, if you'd like to learn more, there's an excellent course on USB here at Pen Tester Academy. You will know that write speeds for USB are horrible. As a result, writes are highly cached. This caching is going to consume memory, which will not minimize your memory footprint. That said, there are some times where using Netcat is not practical. Netcat does have some dependencies, such as some DLLs, which are probably installed on most systems, but perhaps are not. In a future video, we will go into detail on how to use Netcat on Windows. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about Netcat and how you can use it in order to exfiltrate data from your Windows subject to your Linux forensics workstation. So the first thing you want to do is you want to actually get Netcat and install it to your response drive. Now, there are a couple of options here. You can go with the full version of Netcat that is included with Nmap. However, there's a small problem with that. The problem is that there are some dependencies with that version of Netcat. There is a standalone executable for Netcat that is available, and if you do a little web searching, you will find that it's located here. So I'm at johncreighton.org/blog/46/netcat-4-Windows. So you should be able to find this with a Google search. You'll notice this is a very old blog post from 2009, but it still works. I don't find the performance to be nearly as stellar with this version of Netcat. However, if you don't have to install a bunch of libraries that are not existing on the system, it's worth the reduced performance. It's also very simple. So if you scroll down to the bottom, you will see there's an option to download Netcat for Windows. If you go ahead and click on that, you will get a zip file, which you can unzip and install to your response drive. So I've already done that, and I've gone ahead and installed it, and now I will run it inside of my subject system, which is running a virtual machine. So here I have my subject system. This one is running Windows 7, and if I open a command prompt, I can go to my E drive, And my E drive has a live version of Ubuntu, and it also has a Win response subdirectory. So this is actually a bootable drive, so I can use it for multiple things. So if I go to my Win response directory and do a dir, I will see I have both Win32 and Win64, and I have the Netcat zip file, and I've also gone ahead and extracted it. Also on this response drive, which we are going to build up over the course of this class, is Nmap. So if you have the necessary dependencies, you can try to run Netcat that is included with Nmap, and you might get slightly better performance. So that's kind of up to you. Notice I have this nice, small 61K executable. And if I look in the Netcat directory, I'll actually see the source code right here. Great. So how do I use this version of Netcat? Now, the flags are slightly different from what we have with the Netcat that you might be used to. So if I do a netcat /question, rather if I do a netcat -h for help, it will tell me what the options are. So here we're trying to connect to something else, netcat options, host name, and the port or ports. I can detach from the console and run in the background, which is not what I want, and there are some other options as well. For our purposes, the only option we're going to use is -w for wait, and this will set my network timeout because the default seems to be rather long. So let's go ahead and do a simple example. I'm first going to start a listener on the other side on my Linux machine. So on my Linux machine, I will start a netcat listener, and I'll say -l, and I will listen on port 4455. And now it's going to sit here and wait. So on the other side, I will give it something to display. I will do a dir and pipe that to netcat, and I want to go to the host 192.168.56.1, and the port will be 4455. If I go back here to my listener, you will see that I have received the contents of the directory, so the response from the dir command, and it's sitting here. And it will sit here for quite a while, mostly because I neglected to do one thing. I neglected to give it this -w option. So I will repeat my command, and this time I will use -w2. So my listener is set up, and I'll send my packets again. And you can see this returned a little bit quicker. And if I go back to my terminal, notice that my listener exited after displaying the information I wanted. Now, if I want to keep a running log of this information, I do not want this to just exit. I want this to stay alive. And there's an option for that. It's the -k option. So if I rerun this with -k and I go back to my virtual machine, once again, the process on my virtual machine has exited, but I'm still listening. So that's a useful option for Netcat. Another fun thing I can do with Netcat, I can use Netcat to send files. And in order to do that best, I've actually set up a nice little automated system that will allow you to have a listener or two on your Linux forensics workstation, and then there will be some scripts that you can use in order to automate sending the responses from commands and sending files to your forensics workstation. And we will talk about these in future videos. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about automating use of Netcat for live response. In particular, we're going to start out talking about automating the server side, the side of this conversation on your forensics workstation. So here I have a couple of scripts, and these are bash scripts. And of course, bash scripts all start with their shebang bin bash to make sure that you're running bash. I define a usage function that tells you how to do this. And this one is called start case. It expects a case number. I check and see, did you in fact give me one argument? If you didn't give me less than the one argument, I'm going to give you the usage back. Otherwise, I echo out starting case and then use the case name which you gave me. If there is no directory that has the name of this case, that's what I'm testing here. I'm saying if not a directory by this name exists, then make it. And this is how I close an if statement in a shell script. So some of you, especially if you're primarily working with Windows, may not be familiar with this method. Now I create a listener, and you'll notice here I've enclosed some commands in backticks and follow them with an ampersand. And what this does is it runs my command in the background. If I look at the command, it says nc netcat. It uses this keep alive flag that we talked about last time. It's listening on port 4444. Everything it receives, it appends, that's what the double greater than does, to a file in the directory that's the same as my case name into a file called log.txt. What this allows me to do is to have an ongoing log of the results from commands that I run on my subject system. Once this is ready, I go ahead and echo that I started a log listener for this case on this date and time. So this is a little trick in shell scripting. If I take a command such as date and I enclose it in parentheses that follow a $, the command is executed and the results are substituted into whatever else I'm doing. So in this case, I'm echoing out some stuff and I will have the date and time inserted. This is all piped to port 4444 on the local host, which causes this to be appended to my log. Then I will start another script for my file listener. The file listener waits for the client to send a file name on a certain port, and as soon as that happens, it will create a listener on another port to receive the data for a file. So here, once again, I call start file listener.sh, and I give it the case name, and I start it in the background. So that's my start case script. If we have a look at the start file listener script, it of course starts with shebang bin bash, has a usage statement, and it will check to see if you specified a case name. If not, it will give you a usage statement. Now this guy has an infinite loop. So while true, do starts the loop, done ends the loop. The first thing it's going to do is say the file name is equal to, and once again here we're using our little trick. I have the command nc-l, create a listener on port 5555. The results for this command are used to create a variable called file name. Now this will block and wait for a line to be sent. So once a line has been sent that contains the file name, this will exit. And then we will drop to the next line. On the next line, we create a new listener on the port 5556. Any information received on this port is redirected to a file in the case directory, and it's given a name that is the result of running this command. So what is this command? This command base name will give me just the file name. It will strip off all of the path information. So I might have sent a file from the Etsy directory. It will strip that off. If it was from someone's home directory, it will strip off that path information as well. So it will retain just the file name inside of my case directory. I will also have a log, and we'll see this in a future video, that tells me exactly where this used to be. Notice that here again, I have not used the -K option. I am not going to keep this alive. So, as soon as I'm done receiving my file, this line exits, and I go back here into my infinite loop, and this process continues. When does it stop? Well, it stops once I run close case. Close case simply says I'm going to shut down all of the listeners. And once again, I use my trick where I run the date command. I pipe this information to port 4444 on my local host. And then I use the kill all utility to kill start case. I kill any start file listener processes. And then finally, I kill any Netcat processes. And the reason for this last line is sometimes you'll have some stragglers out there. Depending on exactly when you killed these other two scripts, you might have a couple of Netcat processes just kind of hanging out there. So there you have it. There's the forensics workstation side of some automation that will allow you to receive pretty much anything. So you can run any command and have its output there. If you have some suspicious files that you want to look at, you can easily use the system to transfer them to your forensics workstation where you can more carefully and safely examine them. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about automating the client side or subject side of your use of Netcat. As a reminder, we're going to use Netcat in order to easily get information from the subject system without causing too much disturbance. So earlier video, we showed you the forensics workstation side, and for this side we have a couple of command files, or batch files if you will. They're technically not batch files, but these are scripts that you can run in Windows. So the first one will set up a couple of variables. So I start by turning off the echo so that everything is not echoed to the screen. I have a little remark telling you what this is. Then I will check if you did give me a parameter on the command line. I will set rhost equal to that parameter. If rhost isn't set, in other words, if you did not do so, I will default rhost to be localhost. I will set the remote port to be 4444, and I will set the file name port to be 5555, and the file transfer port, the port that is used for the data, to be 5556. Once I've run this script, I'm now ready to send log information, and that is this script. Once again, I start by turning off the echo. I have some remarks. I check to see if rhost is set. If not, I default it to localhost. I also check the port, which is defaulted to 4444. If you didn't give me anything, I'm going to complain, and I'm going to echo out a usage statement, and I will exit. Now it's time to run the command, so I first echo out this string, where I say I am logging information for %*. % is the entire command line that you gave me. I pipe this to netcat-w2. Remember, the W flag is to wait, and I give it the host and port. So I have kind of a starting banner, if you will. Then I call that command line, %*, and I pipe the results to Netcat once again with the -w2, our host, our port. When that completes, I echo my end banner using the exact same construct. So this is pretty simple. I also have the ability to send a file. This script also starts with echo off, and then I will set my variables if need be. If you did not give me a file name, I'm going to complain at you and give you a usage and then exit. Next, I will log that you are trying to send a file. So I will say attempting to send the file, and here's the name, and I send that as usual to Netcat. Now this next bit might look a bit strange, but there is no base name command in Windows like there is for Linux. So I can use this for command. So I'm saying for/f and then %i in %1. So this is in %1 was the file name that I passed in. It says do set the base name equal to %% tilde nxi. So you might say, well, what in the world is that? This construct, believe it or not, will give me the base file name. It will strip off the path. Then I echo that into Netcat, and then I run Netcat on my host and my file transport port, and I redirect my file into it, and this will send my file. So let's have a quick look at this in action. So I've started my case, and now this is my Linux side. It's all ready to go. Here is my Windows machine, so I can set up my client and give it the address. And now I can execute a command and send the results across the network. And that's done. I can also send a file, and I can verify that this worked correctly. So if I go back to my terminal here and I do an ls, I can see a new directory called test. I can tail the log txt file, and you'll notice here's my command, and here is where I sent the file. Also in this directory, I see the files that have been sent across. So there you have it. I have a system that allows me to easily send the results of commands and also files across the network to my forensics workstation. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to start collecting some volatile data. In a few previous videos, we showed you how you could use some basic scripts in order to automate the process of using Netcat to gather information. And now we're going to start putting that into practice. So we're still here in our first box. We're doing a little bit of limited live analysis, which will then proceed into a full live analysis and possibly further on our system. So what data should we collect? The first thing we want to collect is the date and time. Now, why do we want to collect this? We want to collect this because the clock can easily get skewed, as you likely know, if you have a computer that is not connected to a time server. Its system clock will quickly drift off of time. Also, there might be a different time zone. Perhaps the time zone is set incorrectly for the particular subject system, or it's in a different time zone from your forensics workstation, and you want to be sure that you know what time things occurred when you start building timelines, etc. You also want to look at some network interfaces. Are there any funny networks? Is there any network interface that's in promiscuous mode? What sort of connections are there? Are there open ports? What programs are there associated with various ports? Who's logged in? What processes are running? What services are running? What files are open? What is in the routing tables? Is there something strange in there? What are the mounted file systems? Are there any funny network shares or other file systems that you don't recognize? Are there any scheduled jobs? Is there some piece of malware that's running periodically? You can look at process memory dumps, and that will give you some more information. What's in the clipboard? What drivers are installed on this machine? What are those network file and print shares? And what is the command history? What sort of commands have users been running on this box? So these are some of the basic things that you might want to look at. So without further ado, let's get on to collecting data. So here I have my subject system, which is a Windows 7 box, and I'm going to go ahead and open a command prompt, go to my response drive, and I will run my setup client command. And now I will go to my Linux machine. On my Linux machine, I will make sure that I'm running my listeners. And in this case, they're already started. I'm going to go ahead and close my case, and I'll start a new one just to remind you of how this works. So now I have a new case that's been opened. If I go back to my Windows system, I can start collecting information. So I will start by logging my date and time, like so. In case you're wondering, the /T option for date and time just tells me the date and time without asking me to reset it. Next, I will get some network connection information using netstat-an. If I do a netstat-h, I will get some information, and notice that -a displays all connections and -n displays addresses and port numbers in numerical form. So I will use send log, and that's done. We can also use some other flags for netstat. So we might want to try something like this. While we're using netstat, we might want to use the -r option to show our routing table. Let's go ahead and pass this over to our forensics workstation. Now, let's have a look at what showed up so far on the forensics workstation. So here we can see where I sent the date command, and I got my response. I got the time, and then I look at active connections. So here we can see the local addresses that are listening, and notice I see something kind of peculiar. There is an established connection from my local machine on address 101 to a machine at address 1 on port 8080. Now, these particular entries are not unusual. These are all related to my using the send log system that I set up. And here we also see a couple of established connections. Here I can see my list of interfaces. Here's my routing table. I can see my gateway. This is my gateway out to the internet because this is a virtual machine. And here are my IP6 routes. So far, other than this one connection, nothing terribly unusual or possibly unusual seems to be going on so far. We will do some more live analysis in future videos, but that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to continue our discussions on some live response that you can do for a Windows subject. In particular, in this video, we're going to look at the PS tools. Now, PS tools is a family of tools that you can get from Microsoft. You can download it from their website. I recommend that you just Google it, So Google PS Tools, and you should see a link from Microsoft's website to download this tool. That way you will have the latest version. So I'm going to go ahead and run up my client. So I'll click on my Start button, and I'm going to type CMD. Now, instead of just hitting Enter here, I'm actually going to press Control-Shift Enter, and this will give me an administrator prompt. Notice that here I have an administrator prompt, and it tells me that in the title bar. So now I will go to my recovery drive, and you will see that I have a PS Tools directory. So I will go to this directory, and this directory contains tools which I downloaded from Microsoft's website. So the first tool that I want to talk about is called PS Logged On. So if I just run a PS Logged On /question, you will see that it will allow me to show only local logons. I can also eliminate login times, and I can give it a computer name optionally. So I'm going to run it with no options, and you see that no one is logged on via resource shares. There's only one currently logged in local user. I'm going to rerun this command, but this time I will use my little Netcat scripts that we talked about in a previous video. So first I'll set the client to point to my workstation, and now I will use the sendlog command. Another PS Tools command that you can use is the PS File command. So once again, we will run it with /question, and it tells me it will list or close files that are opened remotely. So this will tell me if a remote user is using some files on this computer. And you'll notice that it said no one is remotely using files on this computer. Once again, I could just straight away send this across the network. I'm only doing it locally first in order to show you the command and also the output that will be sent. Another program that can be used is Open Files. And Open Files will give you similar information. It's just already built in. You don't have to install it like you do with PS Tools. Still another option, you can use Net Files, and it tells me that there are no files in the list at the moment. Other things in PS Tools, I can get a list of tasks using PS List. Once again, I will run this with the question mark, and you can see that it will show thread details, memory details, process memory information, process tree information. So there are several different flags that I can use. So if I execute something like this, I should get quite a bit of information. I will go ahead and send this across the network. So far, we've managed to get who's logged in, any remote file usage, and also a process list. Some other things that we can get from the PS Tools. We can look at logs. So I can use PS Tools to get a log listing, like so. Once again, notice that this has a very long list of options that it will accept. The only one we're going to use is the -X option, which is normally going to dump some extended data. And once again, I will send this across the network. Other PS commands that you might use, PS ping. You might want to get the system ID. I'm going to go ahead and send this across. I can also use this utility to get a particular user's SID, like so. Finally, the other PS tool that you might like to use as part of a live response is PS Service. If I run PS Service without any options, it will give me information on all the services on the local computer. And once again, we will send this across the network. All right, so we were able to send quite a bit of information across the network using just this one little package. And in a future video, we'll have a look at some of those results from our forensics workstation. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to review some of the results from our PS tools that we ran against our subject system in a previous video. So the first command we ran was ps logged on, and it showed us that there was only one user logged on, and it was a local user, John. We then ran ps file, and that showed us that there were no remotely opened files. And then we ran ps list. Now, because we ran the ps list with threading options, we are getting a lot of information from each of our tasks. So we have not just process IDs and status information, but we have thread IDs and status, priorities, etc. Now here I see two different processes that seem to be running a tool called BC. Now BC does not sound like a standard Windows program to me, so it's something that bears a little bit of further investigation. Here I've listed my logs using ps log list for my subject system. I can see I have several log entries for the service control manager with timestamps. I have the event log. I have uptime for my system. And you'll notice that the vast majority of log messages from the event log are informational. Occasionally, you will see some errors. Now, in the case of our subject system, most of the messages we seem to get that are errors are related to networking and the inability to register a name for our work group. Next, we have the results of get SID. So here's the SID for this computer. And then we have the results from running PS service. We can see all of the installed services as well as their status. So here, one of the ones that I notice is running is LAN-man server. And notice it does show it as running. And there's even a nice description that tells you that it supports file print and name pipe sharing. So this is the Windows file sharing mechanism. It is running. If this was an older machine, I might want to check and see if it's vulnerable to things like MS08, 067 that hasn't been patched. If I just suspect that there's been some sort of breach, if that vulnerability exists, it'll almost certainly be exploited. Here's another important service, the Windows Firewall. It is in fact running. Now, something to be aware of, it's running, but how is it configured? This is something that you might want to check a little later, in particular if you suspect there has been a breach. Remote registry is another important service. If it's enabled, which it is not in this case, it will allow you to make remote changes to a registry. Here we can see the scheduler. It's important because it allows you to run things on a schedule. It is running, which is the normal case. If it should be running and it's not, it might be something to look into, because again, if you have some periodic processes that you're trying to run, you might have an attacker that's trying to stop those from running. As an aside, you can tell that this particular machine is running inside of a VirtualBox because it is running the VirtualBox Guest Edition service. Now, of course, if it's running in a VirtualBox, you should already know that. Here we have the Windows Remote Management service, which is stopped. If you enable this, it will allow remote management. And there you have it. So that is our results from the PS tools. In the case of this computer, it didn't reveal an awful lot, but you never know. It's hard to say from one incident to the next. So that's what we found from our PS tools. Now, in this case, we didn't find out a whole lot, and it really depends on the nature of your investigation. In the Linux platform, we're normally looking at some sort of a breach that we suspect, and in the Windows world, sometimes we're suspecting a breach, sometimes we're suspecting a malware infection, and sometimes we're just trying to get data off of the computer. And we'll talk about some of those issues later when we get into debt analysis. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to continue talking about Windows Live Response. So we're going to show you a few more things that you can use to collect some data. As a reminder, on your Linux forensic station, you want to go ahead and you want to start a listener like so. And now I've started my listeners. Back on my Windows system, I can go ahead and run a command prompt. So I'll run cmd. Now remember our little trick we've talked about before. If I press Control, Shift, and then Enter, I will run my command prompt as the administrator, which is probably what I wanted in this case. I'm going to go ahead and full screen this, or at least as full screen as Windows can do. I will change to my response drive that's already been inserted, and I will look at my appropriate directory. And now I am going to run some additional commands. So the first command that I'm going to run is net sessions. Now normally this will run like so, and it will tell me if anyone is logged in remotely. In this case, there isn't. So I'm going to go ahead and send it across using setup client, and I will give it the address for my forensics workstation, and I'll use my sendlog command on net sessions. And that's completed. Now there are a bunch of tools that you can get from system internals and or Microsoft. So if you just do a Google for some of these tools, you will find them. And the first one I want to use is called Logon Sessions. And this is going to give you information about logon sessions, of course. So let me go ahead and run this for you, and you can see how it looks. And it will give me all of the logins into this machine. Once again, I will send that across. The next tool that I'm going to show you is called List DLLs. Once again, this is available from sysinternals, so you can do Google search to get the latest version. I do a list DLLs with a help screen. It will show me the usage. So I can either list all the DLLs, or I can look at a particular process name or process ID. So here I'm just going to dump all of them. And as you can see, there was quite a bit of information. So I'm going to go ahead and repeat this, but I will send it across. Incidentally, you might have noticed that one of the command line switches for this tool allows you to list only unsigned DLLs, and that's the -U. Some other tools, yet again, something else that's available from sysinternals, handle. So what does handle do? Well, let's look at the help screen. You'll see that handle will give you information on system handles. So what are handles anyway? If you're not familiar with Windows and Windows programming, a handle is very similar to a pointer. It basically tells you about an object. It's a way of referring to an object. Pointers are kind of a C specific thing. Internally, a lot of these handles actually are just pointers, but they don't call them that. So you can get information on various processes. And once again, as before, you can get handle information on a particular process, or you can get it for everything. So I'm going to go ahead and run it, and I'm going to rerun it and send it across. Recall that if you were doing this on a system that you are investigating, you wouldn't want to do this because you would needlessly increase your memory footprint by running something over and over again and not sending the results across. There's another tool called TCP View that's available from sysinternals, and it has a GUI component and also a command line component. Obviously, we want the command line component because it's kind of hard to send a GUI across the network. So the command line component is called TCP vCon for TCP View console, and it will give us some information about our network, and in particular, it will tell us about endpoints. So who's listening, where, etc. We can also use the built-in ipconfig/all, and this will give us a lot of information such as what is our DNS server, IP addresses assigned, etc. I'll run that and send the information across. Another tool that's available, this one is actually available from Microsoft. So if you search on their website, you will find it. It's called PromQRY. It is for querying to see if any of your network interfaces are in promiscuous mode. So if I run from query, it says no interfaces are in promiscuous mode. Once again, I will send this across. Now, this next tool I want to talk about is written by Jason Faulkner. And if you do a search for it, you should be able to find it. It's called Clip Out. And what it does is it will output any text that is in your clipboard. So if I run clip out, I see that ntuser.dat was in my clipboard. Once again, I can send this across. And finally, I can check for any scheduled jobs using the @ command. It says that nothing was listed, and I will, of course, send that across as well. All right, so those are a couple of more commands that you can use if you're doing a live analysis as part of an incident response on a Windows system. We will talk about some of these results a little bit more in a future video, but that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about capturing memory images. Now, in the last few years, this has become a really popular thing to do, mostly because of a tool called Volatility, which I'm guessing most of you have heard of. So today I wanted to talk about a couple of methods for capturing RAM. Now, the first method I'm going to talk about is what you can do if you're running something inside a VirtualBox. So you might say, why would I bother to do this? What are the chances of this happening in the real world, so to speak? Well, a lot of people are using virtualization, so there is a good chance that somebody is doing something in a virtual machine, and definitely for practice, this is a very easy way to capture an image if you're following along in this course with your virtual machine. So let's start with a command prompt on our Linux machine. So here at my command prompt, I'm going to use a tool from VirtualBox that's called vbox manage. So if I do a vbox manage debug VM, it's going to complain to me and say, well, that's great, but you have not given me enough information. And here is the command that I want to use right here. I want to call debug VM, and then I need to give it a VM name, and then I will tell it, please dump the VM core, and I will give it a file name. So in my case, it is called PA-Win7 subject. So I will do a vbox manage debug VM, and my VM is called PA-Win7 subject, and I will call dump VM core, give it a file name, and my file name will be PA-Win7 subject.img. And it's going to take just a little while to run this because it's a 2 GB image. And so now that's done. I could do a quick ls, and I see right here is my file. So that's how you can do this if you have a virtual machine. So what if I don't have a virtual machine? Now I need to use another tool. Now there are a plethora of tools out there that you can use to capture Windows memory images. You can use a hardware tool, which I'm not going to talk about, or you can use a software tool. Because there are a host of possibilities, I'm just going to talk about one. And the one I'm going to talk about is FTK Imager from Access Data. Now, Access Data makes a full suite of forensics tools. There are some good tools in that suite. They also have some light versions of these tools that you can get for free. So FTK Imager you can find by going to their website. You can Google it. But one thing that's important when you do this, you say Access Data FTK Imager. You go to the download page. You'll see FTK Imager, and you will see multiple versions. You want to download, not on your subject machine, I'm just showing you this, the FTK Imager Lite version. Now, there are a couple reasons for that. One thing is you don't have to register it, which is kind of a hassle. But the other thing is that this version of FTK Imager can be run from your response drive. So I've already run this. I've downloaded it to my response drive. So if I look at my response drive, you will see an FTK Image Lite directory. And inside, I will find an FTK Imager exe. And it warns me, do you want to run this? And I do. Now, FTK Imager, as the name implies, can be used for creating images, normally of file systems. We will talk about doing that in some future videos. But if you click on File, you'll notice it also has the ability to capture memory. So I will go ahead and select Capture Memory. I have to give it a destination path. Now, this is where things can get a little bit tricky. If you're not sure where to put it and you have space on your response drive, that's one thing you can do. Now, in the past, I've mentioned that this is something you should be careful about because thumb drives and flash media in general are pretty horrible for writing. Their speeds are really slow, so they end up getting cached a lot. So you might have some issues with caching of that write operation, causing a little bit of your data from your memory image to go away. So that's a possibility. In my case here, I'm going to browse and I'm going to go to my response drive, which is F. I'm going to make a new folder. I'll call it memdump. Say OK. And now it's going to that location. I can also include the page file. I'm not going to do that. I can always pick that up later when I do a file system image. And I honestly don't have space right now on this particular drive for it either. And off it goes. Now this will take quite a while, and hopefully we will get something useful. And now we see that our memory capture has completed. Incidentally, this will be sped up a lot on the video, but this process did take about a half hour for this capture of a 2 GB memory image. So you can see this is going to take a little bit of time. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about some of the basics of making a file system image. Now, if you're doing this as part of an incident response situation, you've already gone from the initial call, determining if there was an incident, doing some live analysis, and now you've made the decision to do some dead analysis. So why would you want to do dead analysis? That's the first question. Well, despite some advances recently in memory analysis and some other forms of live analysis, dead analysis is the king when it comes to forensics. And there are several reasons for this. For one thing, dead analysis has been around for a really long time. We've been doing this for decades. So it's a very mature science. Another thing that contributes to the success of dead analysis is that you have information that's not changing, it's static, so that it's much easier to look at it and kind of take your time, if you will, and figure out what's going on. Also, dead analysis does not affect the source system at all. When you go to make a file system image, you need to start by picking out a format. Now, there are a number of formats that are available. The most popular format, and the one that I like to use, is called RAW. Now, what is a RAW image format? A RAW image is one where the first block occurs in the file, immediately followed by the next block, etc. Typically, the images that you're looking at will have 512 byte blocks. That is because the standard sector size that you're likely to find is 512. You can also get proprietary formats. Now, the proprietary formats come in two flavors. You have those that embed metadata, things like hashes, time of collection, inside the file. Typically what they do is they have a raw format, and then every so many bytes they embed the metadata. You can also have a proprietary format where the metadata is in a separate file. You might, for example, have a proprietary file that is some sort of compressed format, and then the metadata separate. Another option, if you use the raw format, is to store your hashes in a separate file. So why do I like raw format? There's a couple of reasons why I like the raw format. The raw format can be used by any tool. So even your fancy, expensive commercial tools will support importing in the raw format. You can also collect very easily in the raw format. So it's sort of the universal language. Just like English is the language of science. It's pretty universal that scientists around the world do speak English as a common denominator. So raw formats are great if you're doing an image. Naturally, there are utilities to convert between these formats as well if you need to. Another advantage of the raw format is that you can easily mount a raw image file onto your forensics workstation. So how do you create an image? One way is to use DD. Now, DD is an ancient Unix tool, not a Linux tool. It's been around even longer than Linux. And it's really a bit mover. So it will move bits from one place to another. It was originally developed to convert EBCDIC, which is an encoding used on mainframes, to ASCII. DD has a very simple format. It's just DD IF, the input file, equals, and then you give it a file or a device. OF equals, that's the output file, and then give it an image file name. You could also give it a block size of 512, although this is the default. Now, if you want to create hashes as you are collecting your image, you can use a tool called DCFLDD, which is a patched version of DD. And it has been patched to add certain forensic features, such as hashing. I'm sure that most of you are familiar with hashes, and we use hashes a lot in security and also in forensics. In forensics, we use hashes to determine that things have not been changed. And of course, this is important if you end up going into court. So DCFLDD adds these features. So I can say hash equals, and then I can give it an algorithm. The default is MD5, which I do not recommend. I recommend to use something like SHA-256 or better, a hash window. You can say, I would like to hash this every so many bytes. And why would you want to do that? You want to do that because you want an overall hash for your file system. However, what if I have a damaged media? If the media is damaged, it's possible that some areas will not read the same value consistently. If you go back to the subject media and reread it a second time and it flips a single bit, it will change the hash. And you really do not want to throw out an entire drive worth of evidence. So that's a reason to use a hash window. Another reason to use a hash window is that you will periodically recalculate hashes in order to prove you haven't modified something. And it's much quicker to rehash a small chunk of your image. And finally, there is a hash log. The hash log tells you what the file name is that will store the hashes. One more thing that we should talk about. When it comes to making images, you should do some sort of write blocking. First rule of forensics is don't modify the evidence. Preserve the evidence. Our equivalent of the medical professionals, first do no harm. Now you can get hardware write blockers. For example, you can get a commercial write blocker for SATA drives only. It'll run you around $350. An alternative to that, you can get a USB write blocker, as described here in the USB class. The plus side for that is that it's about $25 to create. The minus is that it's very slow. It uses a microcontroller that's limited to full speed only. That's 12 megabits per second. So this is a fun little device. You can put it in your pocket and you can use it in order to create images of thumb drives. But anything terribly large, you're not going to want to use it. It's just too slow. A good alternative is to use some sort of software write blocking. So you can use software write blocking using things like UDEV rules, as also described in the USB Forensics course. You could use a live Linux distro on the subject computer. You could boot it into that. And you could also boot a live Linux distro on your forensics workstation, which personally I don't recommend. I recommend that you set up your forensics workstation the way you want it and you have the appropriate tools. In future videos, we'll walk you through the process of creating a file system image. That's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about imaging hard drives. Now, so far we've talked a little bit about live response, which is something you certainly can do. In the Linux world, this is a lot more common to do because often when you're doing forensics for Linux, it's as part of a suspected breach. However, in the Windows world, that's only one of many reasons that we typically are performing Windows forensics. So we might be looking into a suspected breach. However, we might also be looking at a system in order to gather some sort of evidence on it. Regardless of the reasons, we often want to do what we call dead analysis. So in a traditional dead analysis, you're going to look at the file systems on your machine in order to gain some information. Now, I wanted to start out by showing you the worst possible way in order to collect a file system image. Now, you might say, well, why are you going to do that? This is what you can do in the situation where you cannot shut down the machine. Now, typically, if you have the machine shut down, you can take out the hard drive and image it, and that is the best situation. We'll talk about that in some future videos, but I wanted to start out with this situation. Occasionally, you do have systems that you just cannot shut down. Maybe you're not convinced that there's been a breach yet, or that there's sufficient reason to shut it down, or maybe it's central to your business. So you want to create a file system image while the machine is still running. Now, a couple downsides. Obviously, if you're doing this on a machine that's still running, things are going to change. Because things are going to change, you might have difficulty in presenting any evidence from this in court. That might not be as big of a deal as it sounds originally, because given jurisdiction issues and other reasons, it's pretty hard to prosecute a lot of hackers in court. So you might not end up there anyway. So if you want to create an image, in the Linux world, we have a lovely tool that is called DD. Now, DD is a bit mover. It was originally created in order to allow people to do conversions between EBCDIC, used on mainframes, and ASCII, used by everyone else. And it was also set up to allow you the ability to move things from place to place. There have been ports of this to Windows, and the standard DD facility, as it turns out, could not be used for this purpose. It requires you to work on a dead file system. You cannot create an image with the standard DD tool if the file system is in use. However, there is a new version that's had a few things added. It's called DCFLDD, and it has some forensics features that have been added. We'll go into some of these features in more detail in future videos. For now, we'll just tell you that you are allowed to capture a running file system with DCFLDD. There is another related utility called DC3DD, which I will not discuss today. Let me go ahead and run a command shell. I'm going to use my standard trick of pressing Control Shift and then Enter so that I can get a root shell. Now I will change to my response drive. I can get a simple help by doing DCFLDD -- help. And we see the basic options are IF, input file, which can also be a file system, OF for an output file. I can take my results and I can save them to either a hard drive or I could send these over the network. Now, we talked about how you can do this using Netcat previously. One thing you need to be aware of, if I send all of this stuff over my network using Netcat, I might have some issues with confidentiality because I'm sending all of this information unencrypted over my network. All right, so we're going to do a simple example where I'm going to copy my C drive to a file on an external hard drive that I've attached. It's been attached as my G drive. So I will run dcfl dd, and the input file has this funny format, // C:, and my output file is going to be G:/live win7.img. Now you notice that it started out very quickly and then it slowed down a lot because of caching. And so there you have it. It'll take a little bit of time, but you can make an image of a live running system. In future videos, we'll show you other possibly better ways to create your images. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, I'm going to show you how you can create a file system image if your subject system is running inside of a virtual box. This is actually a pretty easy thing to do, especially if your host operating system is Linux. So I'm going to show you how this works. So I will go to my VirtualBox directory. And here you can see that I have a VDI file. It is 11 gigabytes, and it's what I'm using for my Windows 7 system that we've used so far in this course. So how can I create an image? All I need to do is convert this VDI format file. Now, this is not the only virtual file system that VirtualBox supports. It will also support VHD and VMD, VDK, etc. So you have some options here, but what you want to do is use our friend VBox Manage. Just say VBox Manage, and you want to use the command clone HD. So I say clone HD. I won't give it any options, and VirtualBox will tell me what I should have done. And you'll see that it says, give me the medium and give me a destination. I can also give it a format. Now, the format, of course, can be one of several things, and the format is for the destination. VirtualBox is pretty smart, and it will figure out what the original format was. So what I'm going to do is say VBox Manage, clone HD, take my original VDI file, and my output will be an external hard drive I've attached. And I will output to PA win7 subject .dd, and I will tell it -- format equals raw. And off it goes. And there we have it. It has completed cloning our disk. If we have a look in the target directory, we see that our image has been created. Now notice the image that was created was actually 26 gigabytes because the original drive was expandable. So our raw image is going to be a little bit larger. So that's one option. Now, if you're lucky enough to have your virtual machine hosted under Linux, another way that you can convert your image is to use the QEMU package. Now, this is normally an emulator package, and in fact, the name stands for Quick Emulator, but it also has the ability to convert some different file formats. So if you want to know if it's installed, you type its name, and you get some results, then it must be installed. Now we're going to use a utility called qimu-img. Now this utility will allow you to convert from all of the different formats this utility understands. And there are a few, including something called 2cows that essentially nobody uses, at least as far as I can tell. And you can take your image, you can run convert, you can tell it that your source format is BDI, and your output format, -O, is going to be raw. I should probably give it a file name. And my output will be to my external drive. And it will go off and do its thing. And so there you have it. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, I wanted to talk about software-based write blocking. Namely, I wanted to talk about something called the ForDeck, which is an add-on to my Linux that runs on the Beagle family of devices known as the DEC, and it is intended to allow you to set up a magic hub so that everything that's connected to that hub is automatically mounted and automatically mounted as read-only. In order to accomplish this, I use some simple UDEV rules. If you're not familiar with UDEV rules, they handle how devices are mounted, unmounted, etc. on a Linux system. So what I have here is a basic shell script that will install the ForDeck. Now, I just recently came out with a new version of this, and the reason for that is that USB 3 hubs actually present themselves as two devices. One of them is a USB 3 hub, and the other one is a USB 2 hub. In order to handle those devices, which is something that wasn't supported by the BeagleBone, it does not do USB 3 at this time, I had to add the ability to add a second product ID to this script. Here's how it works. I have 3 possible parameters. You run the install script, you give it a vendor ID, and you give it at least one product ID, and optionally, you give it a second product ID if you have a USB 3 hub. And how this works, it creates some UDEV rules, and UDEV rules are actually pretty simple. You can get more details on this, by the way, if you look at the USB Forensics course here at Pen Tester Academy. But in a nutshell, what this does is it says whenever I add a block device and it's downstream from this particular vid and this particular PID, set an environment variable, fill mount, set another one, fill dev, to the name of the device, add a script to the scripts that are to be run, and the first script is called protmount sh, and it is passed 2 variables, the name of the device and its number. So if it's SDB3, this first parameter is SDB3 and the second one is just 3. This script, which we'll look at in a second, actually generates another script that is run. The reason for multiple scripts, when these scripts are actually ran, they do not have all the information available. So when I originally insert a drive, it is not yet ready to be mounted. So I have to add some things to be run later. And when it's removed, I do the same thing. If it's a block device, it's being removed and it's downstream from the appropriate hub. Then I run a different script, prot3 .sh, and I give it those same two parameters. Other rules say if it's a fill mount, if it's one of these special deals, then set the environment variable udisk presentation to hide. In other words, don't pop up a message. And set the hint to never, which means don't ever try to mount this. And call this script. And this script, again, was created by prot_mount. Similarly, when you unmount, it will run prot_mount for dash the partition number. So pretty simple. And then I have a second clause in this function, and its purpose is just to set up the second PID if there is one. So the first you test to see if there is one, and if there is, you do the exact same thing and add rules for that PID as well. And then these scripts get copied to etc udev scripts, and one rule is created in etc udev rules.d. And the name of that rule is right here. It's 10-protected mount rules. So how do you use this? It's very simple. I'll go out here to my terminal. So I've gone to my terminal. I need to run this as root. But before I do that, I'm going to grab my USB 3 hub. I'm going to go ahead and plug it in so I can get the appropriate vendor ID and product ID. If I do an ls USB, I will see that in fact, here's my USB 3 hub right here. And here is my USB 2 hub. So let's go ahead and install it. So sudo install --vid 05e3 --pid 0612 and --pid 2 0610. So if I plug in a drive, it should be automatically mounted and mounted as read-only. And I see it showing up here. And once again, I can type mount. And I can verify that, yes, in fact, my device was mounted right here. I can see that it was mounted. And I see that it was mounted as read-only. That was a USB 2 device. I'll unplug it. Check my mount. Notice it was successfully unmounted. And now if I plug in a USB 3 drive, it was also successfully mounted. And in this case, notice that I had 3 partitions. And all of them were mounted as read-only. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to start talking about mounting images. We've talked about how to create these images in past videos, and now we're going to show you how to mount them. In particular, in this video, we're going to talk a little bit about something called a master boot record. So we're pretty much going to start from the very beginning of your media and work our way forward from there. As a reminder, our high-level process, we started with a call. And this is, of course, the case if we're doing an incident response. We started with a call. We determined that there was probably an incident. We did a little bit of live analysis, possibly in order to make that determination. We made the decision to do dead analysis. We then acquired some images, and now we're in this bottom corner box where we are getting ready to start some dead analysis. Now, the beautiful thing about Linux, or I should say one of the many beautiful things about Linux, is there are so many tools available to you in a standard Linux system for doing forensics work, even if that subject was a Windows subject. So what is this master boot record? This master boot record is an ancient standard. It comes from the 80s, and I believe it's actually from the early 80s. So this is something that's been around for about 3 decades, and it allows you to have up to 4 partitions on a hard drive. Now, at the time this was developed, I'm sure they thought, who would ever want more than that? Who would ever want more than 640K of RAM? More than 4 partitions, what would you do with all that? Of these partitions, at most, 1 can be active or bootable. So when your computer boots, if any of these partitions in the master boot record are flagged as being bootable, then you can boot from that partition. After a little bit of time had passed, people decided that they might actually like more than 4 partitions. And so they developed this kludge known as extended partitions. Extended partitions essentially allow you to nest partitions inside of partitions. And this allows you to get more than 4 partitions. These partitions are actually stored as a linked list. We'll talk in more detail about these in a future video. One thing you definitely want to know, all of the stuff I'm going to talk about in this video is being replaced by GUID partition tables. So if you're using any modern system, let's say it's a Linux system, and you go to mount something and it has this huge number, that is its globally unique identifier. And that is where we're moving, to where every partition has a GUID, and the partitioning system keeps track of these GUIDs. And we'll talk more about that in a future video as well. So back to the master boot record. The master boot record has a certain format. Now, this is contained in the first sector of your media. Normally, our sectors are 512 bytes long. In theory, you could have something else. In practice, I have yet to see anything other than 512 byte sectors. So this begins with boot code. We have 446 bytes of it, or hex 1BE, and then we have 4 entries for each of the possible partitions. Now, it would be unusual, but it's not illegal to have the first partition be empty and then something in the later partitions. You are allowed to have blank entries and then have non-blank entries which follow. So each of these entries is 16 bytes long. I'll tell you a little bit more detail on that here in a second. And the sector ends with a signature of hex 55AA. And that's our master boot record. What about these partitions? As we said, each of these partitions is 16 bytes long. It starts with an active flag. Now, if this byte is 0, that means that this partition is not active. In other words, it is not bootable. Remember that only one partition can be bootable, at most one. it is possible to have a hard drive with no bootable partitions. Then we have some geometry information. What is the starting read-write head number? What is the starting sector and the cylinder? Notice that this cylinder is split so that 2 bits of the cylinder are stored in one byte, and then the remaining 8 bits are stored in another. And this allows you a certain size device. Now, most modern systems ignore this information. Nobody cares about cylinder head sector addressings anymore. For the most part, we only care about what we call logical block addressing. We've discussed this briefly in previous videos, but logical block addressing is simply starting at 0 for the first sector, that's LBA 0. The next one is LBA 1, etc. So this cylinder head sector information is pretty much irrelevant today. What isn't irrelevant is this partition type code. Now, in the Linux world, this is normally hex 83, which is just a code that says Linux. I will show you a little bit later, you can have different type codes in here. So in the Windows world, they use different codes for different kinds of file systems. So FAT file systems, NTFS file systems, etc. And then we have the end, head, sector, and cylinder, which again is pretty much ignored. And then we have the sectors preceding the partition. So what is the starting sector for this partition, or what is its starting LBA, if you will? This is stored in little endian format, as are most things in the PC world. And then we have the sectors in this partition. So these last 2 values are also rather important. How many sectors do I need to skip over? In particular, if I'm looking at an image file, this will tell me how far I need to skip or seek if I'm doing a file operation. And where does this partition end? There might be other partitions after me. So there you have the very basics of master boot records. That's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to continue our discussion on how to mount an image file in Linux. So here I've changed to a directory where I have a bunch of image files on an external drive, and I want to mount this image called PA-Win7 subject DD. This is a raw format file. We talked about image format files in previous videos. And here I want to mount this. Now before I do that, I want to quickly run an fdisk command. So if I do an fdisk on this file, I can type P for print, and it will tell me all about the partitions on the system. Now, you might think, why did I not have to run sudo? I don't have to run sudo when I'm doing this for an image file. Normally, if it was a partition for a physical disk, I would have to run sudo before my command, because only root can look at and mount an actual physical device. So here we can see that I have 2 partitions, and the first partition is marked as bootable. It is type 7, which is HPFS, which is the high performance file system from OS2, or NTFS, or exFAT. And the second partition is also type 7. Now, a little bit about these partition types. We said previously that my partition type, if it was a Linux system, is probably 8.3, but for Windows, they have different types available. So if I type T here in fdisk and say I would like to change the type of partition 1. I'm not actually going to do it. And it says type L to list the codes. So I'm going to do that. In here, you can see there are several codes available to me for this partition type. So I have codes for various kinds of FAT file systems, which we're going to talk about shortly in a couple of videos. And then I have various codes for NTFS and other file systems as well. So in the case of DOS and Windows, pretty much you're looking at either a FAT file system or an NTFS file system. There are a couple of other things like exFAT that you don't see much. exFAT is something you might only see on a video camera. It's something that's been optimized for storing large files such as streaming video files, etc. Typically don't find that in a desktop system. So there you have our different partition types. I'm going to go ahead and quit fdisk, and now I'm going to show you how to mount this file system. Now, first you need a place for this file system to be mounted. So I will go ahead and create a directory, and I'm going to start by switching to a root terminal using sudo -s, and I will make a directory, and it will be media PA Win7. Now, in order to mount an image file, one thing I do need to have is that offset. Where does this particular partition start? Now, there are a couple of ways I can get this. I could, again, run fdisk on my image file, and you'll notice it tells me where my partition starts. It says the first one here starts at 2048 or 2K, which is pretty typical, and the next one starts at 206,848 sectors in. So if I want to mount this by hand, I can just take a note of that, and if I quit here, I could do the mount command --help, and it tells me when I mount something, I need to give it a source and a directory. I can also give it a type, and I can also give it options. So what are some of the options I can give it? I want to set this to mount as read only. I also want to tell it, please do not update access times. So this is in particular important for some of the Linux file systems, but it doesn't hurt to do this with Windows as well, or there are some internal timestamps that might get updated if I don't tell it to not update these timestamps. So one option to the mount command is an offset option. And I'll show you a nice little trick that you can do in order to more easily mount a particular partition. So if I type mount -o for here's some options, the first one I will give it is RO. Please make this read-only, comma, no A time, do not update those access times, comma, loop. Loop says, please treat this file like it's an actual physical device, and then offset. For offset, I need to say how many bytes I want to offset for my file system. Well, I know how many sectors, but I don't really know how many bytes. I could go to a calculator and figure it out, but that's kind of hard. Or I could just use a simple trick that works here in the bash shell. And that trick goes like this. If I say $, and then 2 parentheses, and then put some sort of mathematical statement inside, this puts bash into a math mode. And it allows me to do math such as this. 206,848 times 512, then I have 2 closing parentheses. Then, now that I've finished my options, I can give it the name of my file and my destination, like so. So again, the options, read only, no access time updating. Loop, please treat this file as a physical device. Offset, how many bytes from the beginning of my file till this partition or file system starts, my file name, my source, if you will, and then my target. Where will I like to mount this? and now it's mounted. Notice what also happened in my Ubuntu system here. It said, oh, I just mounted this. Why don't I display it for you in the file manager? So here you can see I have all of the normal files I would expect on this Windows 7 system. So that is all you need to do in order to mount an image onto your Linux Forensics workstation. Really briefly, I wanted to also show you what this looks like in the RAW format. Now, you can get a free tool that's called ActiveAt Disk Editor. If you go to disk-editor.org, you can download this tool. It's available for Windows and for Linux. And let's have a look at this file in ActiveAt. So here I've opened up ActiveAt. I'm going to go ahead and open my new disk image file. I'll browse. I'll say, please look at all kinds of files. And here is my image. I'll click OK. And here you can see my image. It starts out by showing me the master boot record. So you can see here I have my 446 bytes of boot code. You'll notice there are a few messages embedded into this code. This is followed by a disk serial number. Here's my first partition, and this is nicely decoded for me. And here's my second partition. You can see the third and fourth partition entries are empty. Now, you might say, what does it mean to be empty? And for the purposes of your computer reading it and saying, yes, it's empty, all that is required is that the type of file system, that hex code, is 0. So notice that both of these had type 7 file systems, and the third and fourth entries have type 0. Normally, the rest of the entries will also be 0. And here is our signature at the end of the sector telling us that, yes, this is a valid MBR. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about mounting images with extended partitions. So we've now managed to get into our dead analysis phase, and we have an image that involves extended partitions. So let's talk a little bit more about these extended partitions. These are used when you have an MBR-based, master boot record-based drive that has more than 4 partitions. A primary extended partition stores logical partitions inside of itself. So basically, this is a nested structure. So one of those 4 partitions in the MBR is a partition type of an extended partition. So what this does is it says this guy is its own logical disk. And this logical disk has inside of itself another MBR. Now, there's a couple of things that are slightly different about this particular MBR. One thing, it has offsets that are relative to the extended partition. This makes sense if you think about it, because it thinks it's its own little happy drive inside of another drive. It doesn't really even know that it's inside of another drive. Now, it has normally 2 entries, and this is implemented as a linked list. So if I have an extended partition in my MBR, I look into that extended partition and I see the extended partitions MBR, and inside I see 1 or 2 partitions. Even though there are 4 spaces, these are not normally used. So the first space will have any partition that's stored inside this extended partition, and if it's required, additional extended partitions that are nested inside of this primary extended partition will be listed in the second spot. So essentially, if you're looking at an extended partition, you want to look at the beginning, see if there's something in the second spot. If there isn't, you're done. If there is, it should normally be another extended partition. You need to keep going until you get to an extended partition MBR where the second entry is unused. So the MBR format is the same as what we have at the beginning of our disk, except the boot code is unused and the third and fourth partition entries are also normally unused. The partition format is exactly the same. So once again, we'll have our active flag, start head sector cylinder, partition type, end head sector cylinder, and then our sectors preceding and sectors in the partition. Recall that these are relative though, so these are relative to the extended partition only. So how do we mount things with extended partitions? It's actually quite easy in Linux, and I wanted to start by showing you an image in ActiveAt Disk Editor, which we introduced in a previous video, and showing you how this looks. So we'll start by looking at an image in ActiveAt that happens to have an extended partition. So here I've opened an image in ActiveAt. Here's my MBR, my master boot record, and here I have entries. Now notice my first entry is bootable. It has the flag 80. It is file system type 83. This happens to be a Linux file system, and there's some other information as well. My next partition has file system type 5. File system type 5 is an extended partition type. So in ActiveAt, I can go ahead and click on the My Computer tab, and if I go to my extended partition and say I would like to open this in my disk editor, here's my extended partition, and notice, as we said, here's all that boot code, which is unused. And in our case here, we have a partition entry. This is type 82, which is a Linux swap partition, and its first sector is 2. Now, again, that's relative to this logical disk and the extended partition, and here's its size. So this is sector 0. If I go to sector 1 and then to sector 2, here is the start of my swap space. So what if I wanted to look at this same information in fdisk? If I just run fdisk on my image file, if I print out the information, notice it shows me my first partition, and then it shows me partition 2, which was an extended partition, and it has labeled the next partition as partition 5. And the reason that it has done this is that is traditionally where we start numbering again, because there can be up to 4 primary partitions. You'll notice that this partition starts 2 sectors into our extended partition, and it ends at the end of that extended partition. Well, that's great. So how do you mount an extended partition on Linux? Well, you're in luck, because it turns out that you don't really even care that this is in an extended partition, because tools such as fdisk will tell you where this starts relative to the beginning of the image file. So here you can see that my partition inside the extended partition begins at sector 33,556,480, and I also have its size. So I really don't need anything else. I have all the information I need, so I could mount an extended partition exactly the same way as I did with a primary partition. It is that easy to do in Linux. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to start talking about how you can automate certain things such as mounting image files with Python. Before we get into this, one thing you should know if you're not familiar with Python, first of all, I would recommend strongly the Python course at Pen Tester Academy. It's a really great class if you're not familiar with Python. Python is widely used in the InfoSec community. And why is that? Well, it's a very powerful language, and it's also very easy to learn. It's something that elite hackers like to use, and yet we teach it to children. Now, if you've used Python, you're probably aware that there are two versions of Python. There's version 2 of Python, and then there's Python 3. Now, Python 3 is intentionally not compatible with Python 2 in certain places. Now, the whole idea behind Python 3 is that it is consistent, whereas Python 2 is not entirely consistent. Sometimes something works one way and sometimes it works another way, depending on the situation. So they decided to make everything nice and consistent and kind of cleaned up things a little bit, and that's how we got Python 3. Now, if you've gone through my Linux Forensics course here at Pentester Academy, I did a lot of work in that course in Python 2. I've made the decision that going forward here in this course, I'm going to use Python 3. And why is that? Well, somewhat I want to future-proof what we have here, and Python 3 is sort of the new version. There's a lot of stuff that's been backported to Python 2 that's newer, but I think maybe this is a good opportunity if you're a Python 2 programmer to kind of make that move. All right, well, let's get started. So here I have a very simple Python script that will allow me to mount an MBR-based partition that's in an image file on my Linux workstation. So all proper Python scripts begin with a special comment with the hash exclamation, often called shebang. And this special comment, when it's present on the first line of a file, causes anything that follows to be run and this entire file to be passed to that program. So in this case, I've said, please run user bin Python 3. Now, if I just said Python on most systems, this would run Python 2. Incidentally, Python 3 may not be installed on your forensics workstation, depending on what version of Linux you decided to run. So you might need to add it. Pretty easy to do. If, for example, you're running anything that's based on Debian, which is most Linux is, all you need to do is run sudo apt-get install Python 3, and you should be done. Another thing that I will say about the Python scripts that I will present in this course, there are many ways that you can do things in Python. And what I've tried to do here is not necessarily the most efficient way at times, but it is the most straightforward way. So you will see some things you might think, well, I could probably do that more concisely a different way in Python. And you're most likely right. So my goal here is to have some simple, easy to understand Python scripts. When I teach Python scripting at the university, I always like to emphasize things that you can easily read and understand over things that are extremely concise. So here in my Python script, I start out by importing a few things. I import some libraries. One of them is called sys. Sys allows me to get command line arguments. We'll see that. OS path. This allows me to check for things like the existence of files and directories. Subprocess. Subprocess allows me to create a new process, basically to spawn a new process, which I can use for things like mounting and creating directories, etc. And finally, I import struct. So what is struct? Struct allows me to interpret packed strings. Well, what are packed strings? Packed strings are essentially just a bunch of bytes. So I have a bunch of bytes. I want to turn those bytes into numbers and strings, etc. Essentially, if I want to deal with a binary file, which an image file clearly would qualify as a binary file, then struct allows me to do that. So what I've done here is I've defined an MBR class This is the syntax for declaring a class in Python. Just say class, give it a name, and if it doesn't inherit from anything else, you give it empty parentheses followed by a colon. Now, if you're not familiar with Python, again, I highly recommend the Python course at Pentester Academy, and you will learn very quickly that one of the unique features of Python is that white space matters, whereas in most languages, you use things like curly brackets to group code. In Python, you use indentation. So everything has been indented under this class, and that makes it part of the class. Now, objects in Python have a constructor. Now, if you're familiar with C++, Java, etc., you might expect the constructor to have the same name as the class, but that's not how it works in Python. In Python, we define a constructor, and it has a name of double underscore init double underscore, and every class method in Python has a first argument of self. It's equivalent to the this pointer in C++ and Java. So this constructor takes one argument called sector, and sector is a 512-byte MBR sector. Once it has received this 512-byte sector, it will populate something called a tuple. Now in Python, a tuple is a list, but it is a list that cannot be changed. So what I have here, if you look back to the earlier videos where we talked about the master boot record, we said that it started with 446 bytes that represented the boot code. So here I'm creating a format string for use in struct unpack, and this format string says this is little endin, the less than, says please use little endin format regardless of what machine this is run on, and no alignment please. So don't try to align things on standard memory boundaries for this machine. I would like 446 bytes of a string. Now, is this really a string? No. In the case of using struct, unpack, and pack, if you say, I don't care about interpreting this, you can just say, well, these many bytes are a string value. Another thing that I've done here, as I said earlier, in Python, everything is about white space. As I said earlier, in Python, white space matters, indentation matters. I could write this as one huge line where I have a string that says less than 446s, B, etc. But that would be kind of messy. So instead, what I've done is I've used a parenthesis to say I'm starting this really long expression that might go across multiple lines. I start with 446s plus is a concatenation in Python for a string. And then I have a comment. So here I have my first comment that says, this is the boot code. Then I have another single line comment that says, this is the information for partition 1. The first thing I have is an active flag. Recall that if it's hex 80, this is active or bootable. And if it's 0, it is not bootable. And then I have a bunch of other information. Now I would encourage you to do a Google for struct in Python in order to find out what all of these codes mean. So in general, if you have a numerical type for the struct library, if you have an uppercase letter, that means it is an unsigned integer. So in this case, uppercase B means that this is a 1 byte unsigned integer, and you'll notice that we have a bunch of those that occur. We have the active flag, start head, start sector, start cylinder. Also recall that the cylinder is actually 10 bits long. So the upper 2 bits here in the start sector are actually the upper 2 bits for the start cylinder. We also said that for most modern media, we use LBAs, so we really don't care about this anyway. We had the 1 byte partition code. We have our end, head, sector, cylinder. We then have a 4 byte unsigned integer that tells us how many sectors precede this partition, also known as reserved sectors. and how many sectors are in the partition, also a 4-byte value. This is repeated 4 times for each of my possible partitions in the MBR. So here's partition 2, partition 3, partition 4. All of these lines of code just produce a big long format string, but it's also nicely documented with these single line comments. Once this is done, I have to close this format string definition with a parenthesis, and then I create a class data member, a variable, if you will, that is called underscore MBR tuple. Now in Python, unlike some other languages, I have to explicitly say self every single time I want to call something in the class or set a variable in the class or refer to a variable in the class. So it would be like using this all the time in C++, which might seem a bit strange, but that's the way that Python works. So I'm declaring a class variable here, self dot underscore MBR tuple. Generally speaking, a single underscore is used if you have a class member that you do not want people to access directly. I then call struct unpack. Struct unpack expects a format string, which is this thing we just built, and it expects a bunch of data. Now the size of this data better match up with the format string or you're going to get an error. And in our case, this should work if I get 512 bytes, unless I have an error in this code, which of course would never happen to me, but maybe it happened to me once a long, long time ago. All right, I'm just kidding. Of course, we all fat finger stuff from time to time. I've added some methods to this class, such as isActive, that takes a partition number. Again, all of these class methods have an argument of self as the first argument. In order to determine if a partition is active or bootable, I need to access this tuple that I created in my constructor. And if I check the appropriate place, and the index is just 1, plus 10 times the part number minus 1. And you might say, well, what's with this part number minus 1? Normally, we start at 0 in computer science, but for whatever reason, historically, we normally refer to these as partitions 1, 2, 3, 4. So here, I have the partition number. I have to subtract 1 because I'm using 1-base indexes instead of 0-based, and I multiply that by 10. I just check, is that equal to hex 80? If it is, then it's active. So I will return a Boolean value for that. I go through all of these fields. I return the head. I return the start sector. Now recall that it's only the lower 6 bits. So I use the modulus operator, and I divide my value by 2 to the 6th, or 64, and I take the remainder. That's what the modulus operator does. And it says, please only look at the lower 6 bits. For the start cylinder, I add them back in. So I look at the next byte, and if there was anything in those upper 2 bits, I take whatever was in that byte divided by 64. And the double backslash, by the way, here is going to do integer division. So I'm going to get an integer out, not regular floating point division. It's the complement to using the modulus operator. And this is another instance where Python 3 is consistent. So in Python 2, sometimes if you use the single slash, you get integer division, and sometimes you get floating point division. And it depends on what you're dividing. In Python 3, double slash always gives you integer division. Single slash always gives you the floating point division. Partition type is another 1-byte value. I say, is it empty? If its partition type is 0, then it's empty. And then we have the end sector cylinder. And we also have our reserved sectors and the total sectors. Finally, I define a method that checks the very last entry and says, is this equal to 55AA, my signature. Is this signature valid? Now, those of you that are familiar with Python 2 might say, what's going on here with this B? This lowercase b before my string says this is a binary string. Do not treat this as Unicode or any other kind of encoded string. It's just bytes. And this is something you have to add if you're using Python 3 versus Python 2. I also added a little pretty print function which will print out all of the information contained in an MBR. Very simply, we'll say, is it valid? So did it have a valid signature? If it did, then I have a little for loop, and I say for I in the range 1 to 5. Now, how does the range work? Again, if you're not familiar with Python, I recommend the course. But very simply, Python likes to use what we call half-open intervals. So we start at 1, and we go from 1 to 5 exclusive. So it's from 1 up to 5, excluding 5. So in other words, this will give me a list of numbers 1, 2, 3, and 4. Incidentally, there are some subtle differences on how the range works in Python 2 versus Python 3. I don't really want to go into those details here, but if you are a big Python 2 user, if you look at xrange, you will notice that is essentially the same thing as range in Python 3. So here I print out the information. If it's empty, I say it's empty. Otherwise, I print out all of its stuff. The \T's here are just to make it look pretty with a tab so that each partition is indented. So that's my class. I also defined a few functions. I defined a usage function. And what does this do? If you messed up and you didn't give me the proper arguments, I will give you the usage. So it will print out usage, and then it will give me sysargv0. This is the name of the script that you're running. And to that it says image file. Then there's a new line. So on the next line, it will tell you it attempts to mount partitions from an image file. That's what the script is about. And then it exits, passing a value of 1 back to the shell. Here I have a main method. If you didn't pass me an argument, I will call usage. If you did pass me an argument, I continue and I define a list. So here I have a list of non-supported partition types. 5 is an extended partition. 8.5 is a Linux extended partition, and there's some other partition types as well. We also have partition types for swap partitions. You normally would not mount a swap partition. So here's the meat of our script. If you did not give me a valid file name, I will print out an error message and return to the shell with a value of 1. Here, I will open the file that you gave me, right here, sysargv1. I will open it read-only as a binary file. So why a binary file? Well, it's a binary file. That's why you open it that way. Well, what's that mean? It is not a bunch of text on separate lines. So anything that's not a bunch of text separated by new lines should be opened as binary. This construct with open, and then I give it my file name and a mode as F, what this does is it opens my file and it ensures that this file is properly closed, even if something bad happens. Here I read in the first 512 bytes of my file, and I store it in a variable called sector. I use that variable to create an MBR object. So here I'm calling the MBR classes constructor. I then check and say, does this have a valid signature? If it does, then I print out a message, and then I call prettyprint, which prints out information on all of the partitions in the MBR. Once again, I have a for loop that uses range 1 to 5 to go over each of the partition entries. If it's not empty, if the partition type is in the not supported types, I say sorry, it's not supported by this script. Otherwise, I check and say, is it a swap partition, which I wouldn't normally mount. If it is, I will print a message and skip it. Otherwise, I will set a variable called mount path, and mount path is going to be /media heart and then a number. So %s says, please put a string in here. And here I've said %stir I. So this % operator in Python will take what follows and it will substitute the values that follow into my format string here. In this case, there's only one thing that's being substituted. If you have a list, you have to enclose the list in parentheses to create a tuple. Again, we're not going to get too deep into that just yet. If a directory by this name does not exist, that's what we're using OS path isdir for. So it's going to be something like /media /part1, part2, part 3, or part 4. Then I will use subprocess to shell out and run makedir to create a directory, and I will pass it mount path. So I will create the directory. I then set my mount options. Recall that we have loop. This is a file, but treat it like a device. RO, read only please. No A time. Please do not update access times. And then an offset that is equal to, and it says %s. Here again, I will do a conversion. I'm using the % operator, and I have the number of reserved sectors times 512, and that gives me my offset in bytes. Once I have mount ops defined, I will again use subprocess. I will call mount-o, and then I give it my options, and then I have sysart1 and mount path. And here I have my else statement, where it will print out a little whiny message if you did not give me an image that has a valid MBR at the start. Finally, I have here a little trick that you can use in Python. Some of you might be familiar with this, where if I want to create a Python file that can be ran or imported, if I add something like this, where I check if this variable _name is equal to the value of _main then I'm going to go ahead and run main. So if someone just imported this file, it would not run it. They would just have the code available to them from this file. So let's go ahead and run this. Now I'm going to start by running this script, which I've called mountimage.py. That's the standard extension for Python scripts, against an image for my Windows 7 subject system. And we'll see what happens. So notice it said it had a valid signature. The first partition was bootable. Here's the start head, sector, and cylinder. Partition type was 7. And sector, head, and cylinder. 2K reserved sectors, and here's how many total sectors were found. The second partition is not bootable. It has its starting head sector cylinder and ending head sector cylinder. It is also type 7, which is NTFS. Number of reserved sectors, sectors before this file system begins, and its total sectors. And partition 3 and 4 are both empty. Notice I also got an error. It said mount, only root can do that. And the reason for that is I did not preface my script with sudo. Let me go ahead and change that now. Notice this time I did not get any errors. If I go to media part 1 and do an ls, I can see this is my system partition. It's not a lot there. And if I look at my second partition, I can see that this is my C drive from my system. So we've covered a lot in this particular video, and we'll show you some more ways that you can automate stuff with Python in future videos. But that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pentester Academy. In this video, we're going to continue our discussion on automating the mounting process of images using Python. In particular, we're going to talk about mounting extended partitions. So let's get started. So here I have another Python script, and as before, it starts with the proper shebang comment on the first line saying please run Python 3 for this one. I import the same libraries, sys for getting command line arguments, os path for knowing if files and directories exist, subprocess for creating external processes to make directories and mount, and struct for packing and unpacking binary data. We have our same MBR class as before. Nothing has changed here. Our usage statement has changed slightly. The only real change is that this tells you that this script is for mounting extended partitions. Now, we could have integrated this into our first script if we wanted to, and if that's what you prefer, feel free to take what I have here and modify it. I just thought it would be a little bit cleaner to separate mounting of things in extended partitions from things in MBR-based partitions or primary partitions. We do the same check to see, did I get a command line argument that has the image file name or not? If not, you get the usage. I have my list of extended partition types and also swap partition types. So I begin as before. I read the first sector that contains the MBR. I open the file as read-only binary, and I get the main MBR. I iterate over the 4 possible partitions as before. In this case, I check and I say, if the partition type for one of these partitions is in my list of extended partitions, then I'll print a message saying that I found an extended partition. I set a variable bottom of rabbit hole equal to false, and this is a variable I used to determine if I have reached the innermost nested extended partition. As we discussed before, extended partitions are stored in a linked list. So if I look inside that extended partition, there is a mini MBR, if you will, that only has the first 2 fields at most populated, and those fields will have any real partition in the first entry, and the second entry, if it exists, will normally point to another extended partition. And I have to keep going until there is no second partition in the extended partition's MBR. So if it was an extended partition type, I print the message. I set the start of my extended partition equal to the number of reserved sectors for this partition, because recall that inside the extended partition MBR, these numbers are all relative. So I need absolute numbers in order to properly mount my partitions. I start my numbering at 5 for extended partitions, and I say, while I'm not at the bottom of the rabbit hole, I reopen my file. I seek to the start of my extended partition. I read in my 512 bytes for my extended partition MBR, and then I close my file. I do a little sanity check. I say, is this 512 bytes? If it's not, then I've somehow gotten to the end of my image or something else is wrong. I create an extended partition MBR object using that 512 bytes. If the partition type is one of my swap partitions, I'm going to skip mounting it. If not, I'm going to proceed as before. I'm going to set my mount path equal to /media part and then a number. In this case, it's the extended partition number, which will start at 5. And if my directory does not exist, I will create it by calling makedir and giving it mount path. I will set my mount options as before to loop, read only, no access time updating, and I will set my offset. My offset is going to be my reserve sectors for partition 1 plus the start of my extended partition. All of that times 512. I print a message telling you that I am attempting to mount this partition. I call mount exactly as before. The command is mount -o says here's some options. Here's my list of options. I give it my image file name, and then I give it my mount path. If my extended MBR partition 2 is empty, if there's nothing in that second field in the MBR, then I'm done. I set bottom of the rabbit hole equal to true, and I say that I found the bottom of the rabbit hole. Otherwise, I update extended partition start by adding the length of reserve sectors for that second partition, and I increment the extended partition number. And this will keep going while bottom of rabbit hole is not true. I use the same trick for my main. I check the variable _name _ to see if it's equal to _main _, and if it is, I call main. So let's go ahead and have a look at this in practice. I'm going to run my script, and I will run it against an image that has an extended partition just to see what happens. And you'll see that it found a swap partition, and it also found the bottom of my rabbit hole. And it said, okay, we're done here. If I run the same script on something that does not contain any extended partitions, it just exits like so. So those are extended partitions. As you can see, it's really not that much more difficult to mount an extended partition. You certainly could do this manually, but why would you want to do that when you can get Python to do it for you? Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about GUID partitions. So globally unique identifier partitions. Now, their information for these partitions is stored in something called a GPT, a GUID partition table. This is the new way. This is the system that's replacing this antique MBR-based system, and it has a lot of nice features. This comes standard if you buy a new computer today, especially if it has a 64-bit chip and it's come pre-installed with some version of Windows. It is guaranteed to use this system. So we're still talking about some dead analysis. We've gotten our images, and now we are seeking to do some dead analysis. So what's the story with this GUID partition? Well, these are actually part of a new booting system called UEFI. It's a universal system that is replacing the BIOS system that you're probably familiar with. And some of the nice features. This allows up to 128 partitions. It's not 4 and some horrible kludge in order to have a few additional partitions. It's 128. So more than you would ever really need. Why would you want so many? Well, you probably don't, but I can think of some really cool things that you could do with all of these partitions. For example, if I wanted to secure my system, let's say it's a Linux system, because let's face it, if you want to secure your system, you probably don't want to run Windows. I could do something such as giving every user their own partition and only mounting that partition when they log in. That way, if someone compromises your account, my files are not even accessible to you on that system. It's just an added level of security. It is also very simple. we've seen that the extended partitioning system is a huge kludge, and it's not very simple or straightforward. It is the new standard, and it is something that you're going to get on any new 64-bit computer you buy. So what does it look like? It looks like this. Every GPT-based media starts with our old friend, the MBR. And you might say, well, why would you want to do that? This MBR is what we call a protective MBR. It has a single partition that covers the entire disk, and that single partition is of a type that no legacy system that is trying to use MBRs is going to mount. So the partition type is unknown, so the system will not try to mount it. And it's called a protective MBR because it says, I don't know what this whole partition is, so I shall ignore it. Then in the next block, we have something called a primary GPT header. And I'll show you what that format looks like here in a little bit. And then we have a bunch of entries. Now, if our blocks, our sectors are 512 bytes, which they do not have to be, I will have 4 of these entries every sector. In other words, they're 128 bytes long. So I will have my entries through entry 128. That will take me up to logical block 34, again, assuming that I have 512 byte sectors. Then I have my partitions. At the end of my media, I have a secondary GPT. This is sort of backwards in that my header is at the very end, and my entries come before it. Now, why would you do this way? There are a couple of reasons to do this. If this table was to become corrupted, it could become very difficult to recover your partitions, and there could be a lot of them. So it's a good idea to back this up. Now, unlike some of the things that we'll talk about later with things like FAT32, where they said, let's back up some stuff, but only 6 sectors later, the people that designed this system were a little bit smarter. They said, let's back it up far, far away from where the primary is. That way, if a portion of this disk were to become damaged, it's unlikely that the secondary would also be damaged because it's on a different part of the disk. Another reason that this is smart, it's easy to find the beginning or ending of a media. So putting stuff at the end does make it simpler and a little bit more reliable. So what do these records look like? They have a partition type GUID. This partition type GUID is 16 bytes long. This is followed by a unique partition GUID, then an 8-byte or 64-bit logical block address where it begins, and another 8-byte logical block address for the last block in this partition. Notice you will not find cylinder head sector addresses. Those are completely gone. They said nobody uses those anymore. Let's not waste any space with them. We'll use nothing but LBA. We also have 8 bytes worth of attributes. Finally, we have 72 bytes for a partition name. You might suspect that this partition name is going to be stored in Unicode, and you would probably be right. Because, again, this is a modern system. It's meant to work for everyone, not just people who speak English and similar languages. The attributes can contain things such as whether or not this is a system partition. So the first bit says this is a system partition, which means please do not mess with it. Bit 1 says this is some EFI firmware. This is something that is used by the firmware to boot this system. Again, this is part of the UEFI system. So any operating system should ignore this partition because by the time the operating system is running, it's irrelevant. Bit 2 is used to say this is the boot partition. So this is a legacy BIOS boot. It's equivalent to having hex 80 in the master boot record active flag. Bits 3 through 47 are reserved at this time, so they should be zeros. And then in bits 48 through 63, you have type specific attributes. So each partition type is allowed to say this is an attribute that works only for my partition types. So this will vary from one partition type to the next. Now, some of these that we will see bit 60 being used to say this is read only, bit 62 to say this is a hidden partition, and bit 63 says please do not automatically mount this for Windows. In a future video, we will show you how you can automatically mount GUID-based partitions on Linux. But that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about using Python in order to automate the mounting of GPT-based media. So here I have a simple script. I'm importing the usual things. And here I have a long list of supported partition types. So these are all the GUIDs for partition types that Linux supports. And as you can see, the list is quite long. I've defined a couple of helper functions in order to print out the GUIDs. We are using our friend struct unpack in order to do this. So first, if I want to print a GUID, I check to see if the length of the thing that you passed me is 16 bytes, and then I will use unpack in order to print out this information. Now you might wonder what's going on here. I've got less than L for a 4-byte string, less than H for a 2-byte string in little indent format. Same thing, little indent format. And then I have these two values, greater than H, which says a 2-byte value in big indent format, and then greater than Q, which gives me a 8-byte value, unsigned integer, of course, because these are all uppercase, in big indent format. Well, it turns out that the GUID parts, the first half is in little indent format, and then the second half is in big indent format. Why? Who knows why? This is just the way it is. Now, another thing that you'll notice about this little helper function, I'm going to print out each of these values as a string that is 0 filled so that it has a minimum length of 4. And why do I do this? Well, it's quite possible that some of these values contain zeros or do not require all the places to be printed out. If you look up in our script, we'll see some examples where you do need to do some zero filling. Now, this value here probably looks a bit strange. And what looks a bit strange is I've appended 2 bytes to the front of my string. Why did I do that? The reason I did that is that I need to create a value and I have 6 bytes of input. However, there is no format string in pack and unpack for a 6-byte value. There is one for an 8-byte value. So I use unpack and I add leading zeros to my value, and then I zero fill it so that it is at least 12 characters wide. In this case, it'll be exactly 12 characters wide. I created a new class for the GPT record. It accepts the set of records and an offset, a partition number. It then calculates the offset into the set of records. Recall, each record is 128 bytes long. It says it's not empty, and then it checks for the empty GUID, which is all zeros. If it finds it, it sets that to true. It determines the partition's GUID, uses unpack to get the first LBA and the last LBA. It also gets the attributes. Now this part here is another little trick where I'm searching for a null. This is a Unicode null, 2 bytes of zeros. And the reason that I'm doing this is I found that sometimes these strings are null terminated and sometimes they are not. And that can lead to some issues when you try to take the raw bytes and turn them into Unicode. So here I take my set of bytes and I call decode. I tell it what sort of encoding to use, UTF-8, and I tell it if there's a character that you're not sure what to do with, replace it. I made a little print part function to just print out all this information succinctly. This is our old friend, the MBR class. Now, incidentally, I should probably take this and put it in a separate file, which gets imported. And this is something that we will likely do later. For now, since we're just going through this, it's a little bit easier to include everything in one file. And here's my main method. My main method we'll see is much simpler now. I first check to see if the file is able to be opened. I then open it and read in the first sector, and I create an MBR object. I check for a valid signature. Then I check for the existence of this protective MBR. So this protective MBR should have a type of EE. If I didn't find it, I print a message and I exit. Next, I will look for the header that I should find in my GPT. So I will open the file. I will seek ahead one sector. So this is going from the protective MBR to the GPT header. I read that next sector, and the very first 8 bytes better say EFI part. If they don't, I say something's wrong and I exit. If everything's good, I tell you that. I open the file again. I seek 2 sectors in, and then I read 32 sectors. 32 sectors is how much I need in order to read in all 128 possible partitions. I create an empty list called parts by saying parts equals empty square brackets, and then I have a for loop. I say for I in the range 0 to 128. Now why do I go all the way to 128? It would be a little bit unusual, but perfectly valid to have some empty entries in the middle of this table. So you cannot just rely on the fact that I hit an empty entry and I'm done. So you need to go through 128 of them. I create a GPT record. If it's not empty, I print it out and I add it to my list of partitions. Once this is done, I go through my list and I say, is this partition a supported type? If it is, I print a message, set up my mount path as before. If the directory doesn't exist, I create it with makedir, passing it the mount path, and I call mount after I set up my mount options, and they're the exact same options as before. Loop, this is a file, treat it like a device. RO, read only please. No A time, do not update access times. And here's the offset. So what's that offset going to be? It's going to be the first LBA times 512. And I call mount. And that's it. So you can see this is much more straightforward than the other 2 cases where we had an MBR with primary partitions, and definitely a lot simpler than the MBR with extended partitions. Let's go ahead and run this. So I'm going to run this. Now before I do that, I'm going to run a tool that's called PartEd. PartEd is the replacement for fdisk when you have GPT-based media. I'm going to say sudo parted on dev SDA. I'm going to say print list, and this will list my partitions. And you can see that I have several. I'm going to quit, and now I've made a partial image of this hard drive. If I try to run part-ed on this image file, it's going to complain to me because it's going to say it doesn't find certain things, like my secondary GPT. It says end of file while reading success. Do you want to ignore? Sure. The backup table's corrupt, and it still had some problems. So it yelled at me and it said, I don't like the fact that you don't have the entire image. Just to test our script, I'm going to go ahead and run it. And you see that I've detected the same 7 partitions. They're listed in a slightly different order from what part-ed listed them, but that's okay. And if you look at them, you'll notice that they are not sequential. And that is the reason for a slight change in order with part-ed. And of course, the mounting failed because I did not have permissions, but it was going to fail anyway because I do not have a complete image of my hard disk. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about the FAT file system. FAT is something that has been around for a long time. It's been around since DOS. There are 3 flavors that you might see. FAT 12, which was the original system seen on floppy disks. You can have it on hard drives as well. It's not terribly common, but it is a possibility. And then we have FAT 16 and FAT 32. Now, these are named for the number of bits in a FAT entry. So a FAT is a file allocation table. We'll talk a little bit more about that later in this video. So 12-bit FATs have 1.5 bytes, or a byte and a nibble if you prefer, for each entry. And FAT 16 has 2 bytes and FAT 32 has 4 bytes. So obviously FAT 32 can have a larger number of clusters than FAT 16, which can have more than FAT 12. It is a de facto standard. It is used everywhere. So if you buy a thumb drive, it's probably pre-formatted as FAT, although some of the larger ones do come pre-formatted as NTFS. Now, modern versions of Windows, version 7 and higher, will not install on a FAT file system, because the FAT file system does not have some features that they require. So you might question, why are we still talking about it then? The reason that we're still talking about it is that you will still find FAT file systems. Just because the operating system cannot be installed on a FAT file system doesn't mean that you won't encounter FAT file systems. They're also a little bit simpler than the NTFS file systems, which we will talk about later in this course. So what does a FAT file system look like? It starts out with a volume boot record. Now, in the FAT 12 and FAT 16 file systems, this is 1 sector long, and it is normally 32 sectors long in the FAT 32 file system. We'll talk more about that in a bit. This exists primarily to answer the question, tell me about yourself. It's the file system's way of telling the operating system how everything is laid out. Then we have our file allocation tables. Normally we have 2 of these. They have a primary FAT and a backup FAT. These are updated at the same time, and the size of these FATs is going to vary depending on the size of your media. In general, it's going to be the total number of clusters divided by the FAT entry size, which is either going to be 1.5, 2, or 4 bytes, and that divided by 512 bytes, which is the standard sector size. For FAT 12 and FAT 16, the next item is the root directory. The root directory is not stored here for FAT 32. Now, there are some advantages to having the root directory stored in one particular place and some downsides as well. We'll talk about those in a little bit. Then we get to the data clusters, the sectors that actually store files and directories. Now, for various reasons, the numbering actually starts at cluster 2, not 0 or 1. We'll talk more about this in detail later as well. So the volume boot record, as I said, it allows the file system to tell the operating system about itself. It contains some necessary information and also some extended parts that contain nice to know human readable stuff. It is 1 sector long in FAT12 or 16, and normally it's 32 sectors long for FAT32. Most of these sectors are empty, and you could have other than 32 sectors, but that is the default. The file allocation table. This is where the file system gets its name. And what it does is it gives you status for every cluster in the file system. So a cluster is a collection of sectors. It is the smallest allocation unit for a file system. Some file systems may have a cluster size of 1 sector, but that's pretty unusual today. So you will normally see some power of 2 for a cluster size. And every cluster has an entry in this allocation table that tells you, is it available? Is it currently unused? If it is used, is this cluster the last cluster in a cluster chain that makes up a file? Or is there another cluster? We'll talk more about these details in future videos. The first 2 entries in this FAT are special. We said that the cluster numbering starts at 2, and there's special information stored in the FAT for cluster 0 and cluster 1. And these are used in order to create a cluster chain, a list of clusters that make up a file or directory. Normally, the 2 FATs are updated at the same time. You can change this behavior with FAT32, but I have never seen anyone do that. Directory entries. In the case of FAT12 or 16, we have the root directory that precedes the data clusters. In the case of FAT32, the root directory has been kicked out into the data clusters, which has some advantages. One advantage is that the size is not capped. You can have an unlimited number of entries in the root directory. Typically, the root directory for a FAT32 system at least starts in cluster 2 because of when it was created, and often cluster 2 is all the storage that you need because a lot of people don't have a lot of stuff in their root directory. So each directory entry contains metadata, things like modified, accessed, and created times, or MAC times, as we say in forensics, file size, how many bytes does it take, how many clusters does it consume. It also contains the starting cluster. We said the FAT allows you to build a cluster chain, and the directory entry tells you where that chain begins. So there will be a pointer to the first cluster, and after the first cluster, the operating system has to follow the cluster chain in the FAT. It also relates file names to these cluster chains. And finally, we have the data clusters. This is where all the files and directories live. I say all the directories. If you're dealing with FAT12 or 16, all of them but the root directory live there. And it's the only part of the disk that isn't overhead. All the other things we've described are just overhead that you need in order to use these data clusters. And they're nothing but a collection of sectors. So there you have it. There's an overview of the FAT file system. We'll dig a little bit deeper in some upcoming videos, but that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to start looking at some FAT file systems using a tool called ActiveAt Disk Editor. Now, ActiveAt is a free tool that's available from LSoft, and if you go to disk-editor.org, you will see where you can download this tool. You can download a version for Windows or for Linux. And this is a very nice tool that you might find useful. The only things that it doesn't allow you to do is it doesn't allow you to do things like copy files on images and things like that. If you want to do those sorts of things, they do have some commercial products that will do that for you. But I have to say, it's pretty nice for a free tool. So I've already gone ahead and downloaded and installed this tool. So let me go ahead and fire it up for you. So here's our tool. It will come up to this screen and will give you the option to either open an actual disk or a file if you just want to use it as a hex editor, or to open a disk image, which is probably what you want to do. So I've selected open a disk image. I'm going to go ahead and click on the ellipses to browse. Now, when you first say you want to open a disk image, it's going to look for a certain file type, and you probably want to say all files. Now notice, it will open a virtual PC disk image, a VMware disk image. For reasons unknown, it will not open up a VDI file from VirtualBox, but you can easily create a raw disk image from a VDI file. So if I click on all files, I will see a bunch of possibilities. I will just pick one of these and open it. So if I look at an image, you'll notice that it tells me a little bit about it if I click on disk image. And it says that its label is no name. It is a FAT 32 volume. Here's its total size, total sectors, and beginning sector. If I click on the partition or volume, I will get some more information, including the different file names. Now, to get the most out of ActiveAt, you want to click on your partition and then click on Open in Disk Editor. So what does this do for you? By clicking on Open in Disk Editor, you get a logical view of your disk. And you will see here it says no name volume. So you're not looking at the raw data view, and you might say, so what? Some advantages, things like clusters. Clusters are a logical construct. So when I say cluster 2, that relates to a set of sectors. If I don't always want to calculate those offsets, then I probably don't want to use just the raw view. So let's go to this raw view for a second. And here I can see the raw information at the start of this disk. Now, there's a couple of things that you should know about this tool. One of the nice things about this tool is that it supports templates. So over here on the left, I have a template view that is showing me a nice highlighted version of what's over here. And if I click on this drop down, you'll see that I currently have a master boot record as my selected template. So if you recall our previous discussions, we talked about what the master boot record looks like. And here we have all of this boot code that it begins with, followed by a disk serial number. Notice that it has tool tips. So if I mouse over things, it will tell me what they mean. And here is my first partition entry, and there are no further partition entries in my master boot record. And I have a signature of 55AA. I can also click over here in my master boot record, and it will highlight items in my hex view to the right. It will also interpret those items for me. Now, one thing that can happen sometimes, you click onto a new item and ActiveAt might get a little confused. If it ever does, if you click on the start of your item, usually it's a sector, and you right click and say set template position, then it should correctly display your items, assuming of course that you've selected the proper template over here. If you're not seeing this template view, if you click on View, Windows, you can tick the box next to template, and then it will show up again. Now, something you will use a lot is the navigate. The navigate button will allow you to go to different parts of your disk or volume. So if I click here, I'm in the raw data view, which is the entire disk. To navigate, you'll notice it says, would you like to navigate to the primary FAT partition, its boot sector copy, the first FAT, the second FAT, or the root directory. You can also go to unallocated space. It's not unusual to have unallocated space in your file system because things didn't work out nice and evenly, or there's some other reasons like alignment on various boundaries that will cause you to have a little bit of leftover space sometimes. Now I'm going to shift over to my logical view, the volume view, and notice that once again I still have navigate, but I don't have the ability to navigate to things like the MBR because it doesn't exist inside this partition. Also notice that the sector numbers are different because these are sectors within the partition. If I went back here, notice that my file system begins 63 sectors into the drive. Whereas here, of course, it starts at 0. I can go to my boot sector. In this case, since I used the navigate button, it did update my template. If that didn't happen, if you got there some other way, you can always, again, click on the start of the sector, tell it to set the template position, and make sure you have the proper template selected from your dropdown. So here I can see my boot sector. And once again, the template interprets things for me because it's FAT32. There's a backup boot sector that is also interpreted. We will talk more about these items in future videos. I can navigate to my FAT. Here's my first FAT and my second FAT and also my root directory. So that's how you can navigate around. Other ways that you can move around. You can go to a specific sector. Now, you probably don't have to click on the More button for this. The only reason I have to do this is that I have my font set kind of large so that you can more easily see this on the video. So if I click on Go to Sector, you'll notice it says, give me a sector number or give me a cluster. So I want to go to cluster number 2, which is where my root directory is. If I go back here to the raw view, you'll notice when I say go to sector that the cluster is grayed out. And the reason for that is that a cluster, again, is a logical construct. It is a collection of sectors, and you need the information from things like the volume boot record in order to know where a particular cluster is relative to sector numbers. And how did I get that? Logical view, once again, if I went to my computer and I clicked on the partition and then clicked on Open in Disk Editor, that is how I got this extra tab. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to dig a little deeper into the volume boot record. Now, the volume boot record is used to describe the file system. We said before that this allows the file system to answer the question from the operating system, tell me about yourself. Now, there are a couple of different variations on this volume boot record depending on which version of FAT is in use. However, the first 28 bytes are the same for all versions of FAT. In the case of FAT12 and FAT16, this is one sector long, and in the case of FAT32, it is multiple sectors. Normally 32 sectors, although this can be changed from the default. In FAT32, in the volume boot record, you have a backup of the boot sector. You also have space for more boot code, which I've never seen being used. And there's some other extra information that we'll talk about later. So what are some of these first parts? The very first thing that you'll see is a jump to bootstrap code. So there are 3 bytes allocated for this. This allows you to have a long jump if required. For those of you that have taken the assembly course, you know what I'm talking about, but a long jump is a jump of more than 128 bytes, either direction, either forward or back. Now, this jump code is put into place in order to skip over some of the information about the file system, some of the different parameters. The reason it's done this way is that you want all of the parameters to be in a standard place, because you're not always going to boot from this file system. You might just be mounting it. The third byte in these 3 bytes is always going to be hex 90, which is the NOP code. Those of you that have done some shell coding are definitely familiar with a NOP and what it does. It's a no instruction. It's just a spacer. So something to keep in mind. Then we have something called an OEM name. Now, an OEM name is the name of who created this file system. And we'll see some examples of that in a bit. Then we have the number of bytes in a sector. It's very likely that this is 512 or hex 200. Then the number of sectors per cluster. This could just be 1, or it will normally be some power of a 2, with 2, 4, 8, 16 being the most common, but you can have much larger numbers as well. Then we have the number of reserve sectors before the file system begins. Now, this is normally 1 for FAT 12 and 16. It says, here's how many sectors are on this partition before you get to an actual file system. There's 1. It's the one that you're in right now. In FAT32, it's normally 32. Then we have the copies of the FAT. I've never seen it be anything other than 2, but again, it is allowed in the specification to have something different. We also have the second parts. How many root directory entries are there? Now, for FAT32, this will read as 0. And the reason for that is that FAT32 moves the root directory out into the data clusters. FAT12 and FAT16 need to know how many root directory entries there are, so they know how many sectors to skip over to get to the data clusters. If the number of sectors in this file system is less than 64K, in other words, if it will fit in 2 bytes, then it is stored next. Then we have something called a media descriptor. This says, what kind of media is this? F0 indicates a floppy, and essentially everything else will be F8. Then we have our sectors per FAT. Now, this again will show as 0 for FAT32 because it's only a 2-byte value and it's not large enough. Then we have our sectors per track and the number of heads. So far, all of this is common to every version of FAT. Now, here we start to diverge a little bit. If we're talking about FAT12 and FAT16, we next have the number of hidden sectors. Now, this is a 4-byte value. So these are sectors before this partition. They're called hidden sectors because they're not to be viewed by the operating system, at least as part of this file system. Then we have the file system sectors if it is over 64K sectors. Next, we have something called a logical drive number. So the first drive is hex 80, the next one is 81, etc. Then we have an extended boot signature. The extended boot signature has some information that people might like to know, but the computer doesn't need it at all. After the extended signature, we have our bootstrap code. Now, this is actually 16-bit assembly code because this is really old again, and it has to be backward compatible with an ancient, original IBM personal computer. And at the end, we have 2 bytes, 55AA, as a signature. Going back to the extended signature, the first byte is hex 29, and that indicates that yes, there is an extended signature. Then we have a 4-byte partition serial number. Recall that we have a disk serial number as well. Then we have a volume label, which is either 11 bytes maximum of text or no name. So if you didn't give your volume a label, it gets the one of no name. And then we will have a human-readable file system type. So it will say FAT12, FAT16, FAT32, etc. This file system type is never used by the operating system to determine the file system type. This is just here for the humans to make it a little easier for you. So it is certainly possible that someone could modify this in order to try to fool you somehow. So back to FAT32. FAT32, after the common 28 bytes, has the number of hidden sectors as a 4-byte value. Then it has the file system sectors as another 4-byte value, followed by sectors per FAT as a 4-byte value. So here you can see, because FAT32 has 4-byte cluster numbers, it also has 4-byte sector numbers. Then we have a mirror flag. Now the mirror flag will tell you if a single FAT is in use. This is very uncommon, but if you have bit 7 set to 1, that tells you that you have a single FAT in use, and then bits 0 through 3 will tell you which of the FATs is in use. We also have a file system version, and then an entry for the first cluster of the root directory, which is likely cluster 2, because the root directory was created immediately when the file system was created. Fourth parts. So what comes next for FAT32? There is an entry saying which sector in this reserved area is something we called an FS info block. An FS info block will give you certain information, and we'll go over that in a little bit. There's also the location of the backup boot sector. Usually it is sector 6 in this reserved area. We have the logical drive number, just as before. We have an extended boot signature, which is exactly the same as the FAT12 and 16 case. It's just in a different place. Then we have our bootstrap code. Notice we have slightly less space, only 420 bytes. And then we have our same signature of 5588. Now there is slightly less bootstrap code. However, there is an additional sector allocated for bootstrap code if you need it, although I've never seen it be used. So finally, let's talk about this FS info block. The FS info block contains some additional information. So it starts with a signature RRAA, and then it skips many bytes, and then it has a marker RRAA with the exact opposite capitalization, and then it has two 4-byte values. The first one is the number of free clusters, and the next one is the last allocated cluster. So what is this all about? These are here to give the operating system hints on where to allocate more space. With FAT32, you have bigger file systems, so it's a little bit harder to find some free clusters. Where's the best place to look? Well, you can start with the last allocated cluster. It is likely that the next cluster is available. Also, knowing the free clusters helps you. So if I try to copy a file to your file system and the file size exceeds the number of free clusters times the cluster size, then it will tell me straight away you do not have enough space to store this. There is also the possibility of having all F's in these values, and that indicates that it is unknown. So this is not authoritative information, but it is just used by the operating system for a little bit of optimizations. And we'll talk more about that in some future videos. So there you have the volume boot record, which again is used to describe a file system to the operating system. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to examine the volume boot record in Active@, Disk Editor. We talked about this in a previous video, what it looked like, and we're going to show you it in action. So I've already loaded a disk image, and from my Computer tab, I can see that this is a FAT32 file system. Remember that you want to click on the partition and then say Open in Disk Editor, which I've already done, and that will give you your logical view, which will have a tab that starts with the volume name -volume. Once you've gotten here, I can click on Navigate, and I will go to the boot sector. I will make sure that my template is set correctly, and it is, and I also have the correct position for my template. I can verify that by clicking here if it doesn't look right and click on Set Template Position. As we said in a previous video, this begins with our jump instruction. So this jump instruction, EB is a short jump, 5.8 is how far to jump, and this code 90 is a NOP, a no operation. It's just there for padding. So if you do a little bit of math, 5.8, if I didn't have this jump instruction, the next operation would be here at 2. If I add 2 to 5.8, I get 5A, which should give me the beginning of my bootstrap code. And sure enough, if I go here to byte 5A, you will see this is where my bootstrap code begins. Next, I have my OEM ID. My OEM ID is MS-DOS 5.0. So what does that mean? Microsoft did something really strange where they used to say MS-DOS, and then they said MS-Win for a while, and they went back to MS-DOS, and they've gone back and forth. And now, with the new versions of Windows, they all run NTFS, and it just says NTFS. So here's what some possible values you might see mean. If you see MS-Win 4.0, that means Windows 95. 4.1 means Windows 98, and MS-DOS 5.0 means everyone's favorite version of Windows, Windows XP. It's possible that something else could be here. For example, if I created this file system with Linux, it might have MKFS DOS or VDOS, saying that that was the utility that was used to create it. Next, this yellow block is a bunch of BIOS parameters. So these are the things that you need in order to properly load this file system. The first item is the bytes per sector, which, as we said, is normally hex 200. It's in little endian format. That's why it's reversed here, which is 512. The number of sectors per cluster, here we have 16. The number of reserve sectors. Notice that this is actually 34. We said that it's usually 32, but for whatever reason in this case, it was 34. The number of FATs, 2. There's a little bit of padding here, and then we get to our media descriptor. I say there's a little bit of padding. Actually, those are 2-byte values that do not pertain to FAT32. So it says F8, which means something that looks like a hard drive. And then we have our sectors per track, 63, 255 read-write heads, the number of hidden sectors. So this is how many sectors before we get to this partition, how many total sectors we have, how many sectors we have per FAT. You can see we have quite a few, 10,219. File system version is 0. As suspected, the root directory is in cluster 2. Notice there's a hyperlink here in Active@, so you could follow this to the root directory. I'm not going to do that right now. Where's the system information? Where's this FS info block? It says it's in the very next sector, sector 1. What about this backup boot sector? We said it's usually in sector 6, and sure enough, it is. Then we get into our extended BIOS partition information. So you can see we start with our drive. Our drive number is 80. It's the first drive. We do, in fact, have an extended signature. We have the value hex 29 or 41. Here's our serial number. Here's our volume label, which is spelled out as no name. You can see that right here. And our human readable file system type is FAT32, boot code, and then our signature. So here's our signature of 55AA. Recall that back here we said that the system information or FS info block was in sector 1, the next sector, and here it is. So here we have our signature, RRAA, and then we skip many bytes. We have our signature here again that marks the beginning of the actual information, and then we have our two 4-byte values. So here's the first one, and here's the second one. So you might say, well, I don't want to convert all that from hex. Well, you don't have to. If you look over here, you'll see the data inspector window. And if you scroll down to 32-bit unsigned, you'll notice that if I move my cursor and I click on a value, it will decode it for me. Now, if you don't have this view, go to View, Windows, and make sure you tick the box next to Data Inspector. According to this FS info block, I have 700,163 clusters free, and the last allocated cluster was 994. This sector will end with a signature. You might say, why is that? This is that extra boot code space that I told you about that is rarely used. In fact, I've never seen it be used, but it is available. So that is sector 2, 3, 4, 5, and 6. So here is sector 6, and we said that sector 6 is the backup boot sector. If I click on the start of the sector, I can right click and say set template copy position, and now you will see that it's nicely decoded for me, color coded. I get tool tips and all that good stuff. And you'll also notice that this information agrees with the main boot sector. Another interesting thing to note, if I go to the next sector, once again, I have my FS info block. However, I don't have good information here. It tells me how many clusters are available, and it has all Fs for unknown, and it tells me the last allocated cluster was cluster 2, which makes sense. I created the root directory in cluster 2, and that's when I stopped updating this FS info block. Recall that it's only here as a hint to the operating system to help it more quickly allocate space on the file system. So if I scroll down here, notice again, I have my signature. That's my extended boot code. And then I will have many sectors that are empty until I get to the beginning of my file system. Now I could easily get there by navigating to my FAT, my first FAT. Notice it was 34 sectors in, which makes sense because that's how many reserve sectors I had right here. It said 34 reserve sectors. So that is how you can use ActiveAt in order to examine a volume boot record. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pentester Academy. In this video, we're going to show you how you can use some Python in order to interpret the VBR that we've talked about in previous videos. Now, first you might have a question, why would you want to do this? What we're trying to do here as we go along and as we learn is to develop a library of Python code that might be very useful later on when we're trying to investigate various file systems. So what I've done here is I've created a new class, and this is a VBR class, a volume boot record class. Now this file, which I've called vbr.py, starts out very similar to our code for the MBRs that we use to mount MBR-based partitions. You'll see we have the same imports, and we have something new. We say from MBR, import MBR. So this is a different syntax for the import statement. And what this does is it says from this file, which is going to be mbr.py, the .py is implied, please import just this class. I could also import various functions, and I could list a bunch of functions and classes as well. Or if I was super lazy, I could say import star to import everything. Now, one thing that this does differently, unlike this kind of an import which we used before for struct, when I do this sort of an import, I do not have to preface every call to something from that module with the module's name. So I don't need to say mbr.mbr, etc. This next line is actually related. If I have a module, which is nothing more than a Python script, which can be imported for use in other Python scripts, if someone uses import star, it will look for this list, _all, _, and if it finds it, only the things from that list will be imported. So here, just this class will be imported and not things like the main method and the usage method, which I defined further down. So what is in this class? It begins with a constructor as before, _, init, _. Recall that every class method has self as the first parameter passed to it. This calls a helper method called getVBR that takes that buffer. I have also defined a bunch of accessor functions that will give you attributes of this VBR. We'll skip over those for now. We'll come back to them. And here's the meat of this class. Recall that we said the first 28 bytes are the same no matter whether it's FAT12, 16, or 32. So what I've done is I've defined a format string for the start. They are all little endin with no alignment, please. We have the 3 bytes for our bootstrap code, jump, 8 for an OEM name, and then we have bytes per sector, sectors per cluster, etc., as we described in previous videos. That leads us up to the part that differs. Now, if it is FAT32, which is most likely what you're going to deal with most of the time, it continues with 4-byte values for hidden sectors. So remember that capital I is a 4-byte unsigned integer. And if you don't remember these different format strings, if you do a Google for struct in Python, you will find out all of these different values. Then we have the number of sectors, which is definitely going to be more than 32 megabytes or more than 64K sectors because the value is not able to fit in only 2 bytes. Sectors per FAT, mirror flags, etc. Using the information that we talked about previously, if you have a FAT12 or 16 system after the common 28 bytes, you will have, once again, the number of hidden sectors, the total number of sectors, if the other value was not large enough to hold this, and a logical drive number. An extended boot signature, which we talked about. So it exists either way. It's just in different places. And we have our file system type, the human readable form, bootstrap code, and our signature at the end. So one of the things that you need to do inside of this method is you need to figure out, is this FAT32 or not? Well, there's a really easy way to do that. If you look at the reserved sectors, the sectors in this partition before the file system starts, recall that for FAT32, you would have a number greater than 1, whereas for FAT12 and 16, it would be exactly 1. So I do a really quick check here, again using unpack. I say if I unpack this little endin 2-byte value, which is stored at this position in my buffer, and that is not equal to 1, then you have a FAT32 partition. So what I've done here is I have used something called a slice. A slice is a substring, if you will, from a list. So starting at position 14, which is at offset 14 from the start, and if I look up in my reference material where the reserved sectors comes in, it starts at 14, and it's 2 bytes long. So it's bytes 14 and 15. So here I have the starting point colon the ending point. Now you might say, but you said it was to 15. That is correct. However, in Python, all of the intervals are half open. So the first item is included, and we include everything up to, but excluding the last item. So if this is a FAT32 system, I set my format string to the common start plus this other string, FMT32. Otherwise, I set it to the common start plus FMT1216. I then use unpack to unpack this entire buffer, this entire sector, into a tuple. If I go back to my different accessors, you will see that all I'm doing is to say which index in this tuple do I want. The jump code comes first, then the OEM name, then the bytes per sector, sectors per cluster, reserve sectors, copies of the FAT, etc. And everything is all happy for a little while, and then when I get down to total sectors, I have to check. I have to say, is the value able to be stored in 2 bytes? If it is, then return those 2 bytes at position 7. If not, then the value at position 7 will be 0, and here I will return the value from position 13. And we'll see similar things further down when we look at sectors per FAT. And there are several values that are stored in one place if it's FAT32, and a different place, or not at all, if it's not FAT32. For example, the file system version is in position 16 for FAT32. Doesn't exist otherwise. So if it's not FAT32, we return none. Root directory cluster, same story. Root directory is stored outside of the normal data clusters for FAT12 and 16. So that doesn't make any sense. There is no fsinfo block for older versions of FAT. No backup boot sector. The logical drive is stored in different places. You can see I've accounted for that here. Serial number, same thing. Volume label, same thing. And also the file system type. The boot code is in a slightly different place, as is the signature. I also created a function called isFat32 that just returns that flag, and we have mirror flags for FAT32 only. So that's my VBR class. Looking at how this is used, I have a usage where I expect you to give me an image file, and this main method is very similar to what we had before. I go through each partition, and the only difference is for each partition, I don't try to mount it. Rather, I will try to load its VBR by opening the file, seeking forward the number of reserved sectors as listed in the MBR for that partition, times 512, the standard sector size. I read in the sector, and then I pass that to my VBR class. If I have found a valid signature, then I print out a little bit of information. So right now I'm not doing all that much with this code, but that will change in the future. So let's go ahead and run this code really quickly. So I will just run this on a FAT32 file system, and you see that it found a FAT32 file system. It was type FAT32, and it had the volume label of no name, and it contained 20,948,697 sectors. As I said before, we will do a lot more with this class in some future videos, but that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. See you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit more about the FAT, the File Allocation Table, from which the FAT file system gets its name. Now, previously we said the FAT was used to tell you about clusters, and clusters, of course, are collections of sectors, so one or more sectors that are treated as a unit by the operating system. Allocations are done on a cluster basis, not a sector basis, and the file allocation table keeps track of what's going on with each of these clusters. So I've gone ahead and I've loaded an image here in ActiveAt. You can see that this image is a FAT32 image. We'll start with this. Also recall that when you originally add an image, you might want to go to the My Computer tab, click on the volume, and then click on Open in Disk Editor, which will give you the logical view that you probably want of that volume, which will do things like interpret cluster numbers for you. So here's my volume. It begins with the volume boot record. We've talked about this before. In this case, every cluster is 16 sectors long. There are 34 reserved sectors, etc. Now I can very easily navigate straight to my FAT using the Navigate button. Say navigate to FAT1. I could also navigate to FAT2. In theory, they should be identical, but I'll just go to FAT1, which is, of course, 34 sectors in because there are 34 reserve sectors. All right, so here we are. This is our FAT. Now, we said previously that the first two entries for cluster 0 and cluster 1 are not used. Now, if I just showed you this in a screenshot and said, what is this thing you're looking at? You could look at this and say, well, it is obviously a 32-bit FAT. And you might say, why is that so obvious? Well, there are a couple of reasons why I can say that this must be a 32-bit FAT. First of all, it starts with F8, a media descriptor, and then we have FF, FF, 0F for the other bytes in the first entry. The second entry is all Fs, and we'll come back to what this is in a bit. If I look down a few lines here, you'll notice that everything is nicely aligned on 4-byte boundaries. So here I have the value 5, 6, 7, 8, etc. So I could look at this and say, this looks an awful lot like a 32-bit FAT. So let's go back to this first entry. The first entry, the very first byte, has one of those media descriptors, which will almost always be F8. If by some chance you're actually looking at something like a floppy, it would be F0. The remaining bytes in the first entry have some sort of filler, and then the entry for cluster 1 is always going to be all Fs. So here we have 0, then 1, and then we have cluster 2, the very first cluster. Recall that in earlier videos we said the way this works is that you have an entry for each cluster telling you whether or not it's used. If it's not being used, you will have 0 in that cluster's entry. If it's being used, and this is the last cluster in a cluster chain, you will have a certain marker value. Now, in the case of 32-bit FATs, that marker value is FF, 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 0. So it's all Fs except for the very first nibble, because of course this is stored in little endian format. And that means that whatever is in cluster 2, that chain ends there. Now you might suspect that that chain also starts there. You don't actually know that for a fact. There's some other ways you could figure that out, but that's a pretty good indication. So that's a super simple case. You have something probably starts there and ends there. Recall that most likely that thing is, in fact, the root directory. We'll talk about directory entries in a future video. So that's the entry for cluster 2. Well, let's look at the entry for cluster 3. Here's my entry, and it says 4. So what does that mean? It's not 0, so that means this cluster is being used, and whatever is stored there continues to cluster 4. If I look at cluster 4, you'll notice that Cluster 4 continues to cluster 5, which continues to 6, which continues to 7, and this will continue for quite some time. So there's a very large file that starts here. It could actually be a paging file. It's very likely that it is. Now, how can you find the end of that huge cluster chain? Of course, you should really go through it by hand. We'll show you later how you can use Active@, to go through this in an automated manner. So you can look at a file and it will rebuild the entire cluster chain for you so that you don't have to. But one way you could easily do this is to use the find. So I would like to find the value FF, 0F, searching downward. I don't want to do a per block search in this case. So let's see, where is the next end of chain marker? And we see that, in fact, this did go on for quite a while until we finally got to our end of that cluster chain. And then we see several shorter files where things are only one cluster long. Well, that is somewhat easy, but what if I wanted, I'm going to navigate back to the start of my FAT here. What if I wanted to find the position for cluster 500? That's a lot of counting to do. Well, of course, you could use your calculator, and you could easily do so like this. So if I have cluster 500, it is 500 entries into my FAT, and it's FAT 32, so each entry is 4 bytes. So I have 500 times 4 is 2000. So that is my offset into my FAT. Now I will convert this to hex, and I see that in hex it's 7D0. If I add this to the start of my FAT at 4400, I see that I want to go to offset 4BD0, and that will show me cluster 500. So I will say go to offset 0x4BD0 from the beginning, and here you have it. This is my entry for cluster 500, and you can see it's in the middle of a file. Let's do another example. This time, I'm going to go to cluster 10,000. So once again, I have 10,000 times 4. That's my offset. I convert that to hex, and I add 4400 to it. I get E040. If I'm lazy, I can copy this value, and then I can go once again to an offset 0x and hit Control V to paste. Here I can see that once again, I'm in the middle of a cluster chain. And of course, if I wanted to, I could also work backwards. So I could take a position, such as this one, and I could subtract the start of my FAT, and then divide this by 4. So this is my cluster number in hex. I prefer decimal. I can see this is cluster 16,416. And if I wanted to see what is in that cluster, that's also very easy to do. I can click on Go to Sector and then just paste my value into the cluster. Again, you need to have the logical view in order to do this because clusters are a logical construct. So if you do not open the volume in Active@, you will not get this new tab, and you will not be able to search by cluster number. And here you can see what is inside this cluster. And you will notice that there is a bunch of Unicode text inside this particular cluster. And then it ends. It's the end of a large file. One last thing I should point out, let's just click on back here to go back to my FAT. Don't work too hard. Don't try to manually figure out what all of these values are. Use the data inspector here in Active@. So for a 32-bit FAT, you need a 32-bit unsigned value. So here from my cursor, this is 16,418. This is 16,420, 21, 22. So this tells me that there is a file here that's a little bit shorter. It starts here and it ends here. Now, chances are that you will never have to deal with FAT12 file systems, but just in case you do, I wanted to point out how they work because they're a little bit strange. So what makes them so strange? Well, let me show you what's going on with those. So I'll add an image. I will open it in the disk editor. And here's my image. It's a volume that has a label of Wombat. If I navigate to my FAT, you'll see that it looks quite different. So what's strange about FAT12? Well, the biggest issue with FAT12 is that it has an entry that's 1.5 bytes long. So if you ever have to deal with FAT12, which hopefully you never will see that things align on 3-byte boundaries. So these 3 bytes here actually tell me that this is the entry for 0 and this is the entry for 1. So this middle byte here, how does this work? Well, the left nibble goes out to the end this way, and the right nibble crosses over and goes out here. So once again, for the first entry, entry 0, the first byte is F0, which is a floppy in this case. And here we have all Fs in the second entry. Here's my next 3 bytes. So this left nibble goes to the end here. The right nibble goes to the front. So cluster 2 has an entry of 003. Cluster 3 has an entry of 004. What this means is whatever is in cluster 2 continues to 3 and continues to 4. If I look at the next 3, this 0 goes out here out front, and this becomes 02C. This one goes to the end, and it becomes 006. So whatever in cluster 4 continues to cluster 2C, and whatever is in cluster 5 continues to 6. You'll notice that that continues to 7. Again, the 0 goes out here. The 8 goes to the end, which continues to 8, to 9, to A, to B, to C, to D, to E. And then here in E, this F comes over here. That means that that file ends in E. And this one comes over here, which means whatever is in F starts and stops in F. Looking at the next set of 3, this F comes over here, which gives you FFF, end of the cluster chain. And this one comes over here and gives you 012. As before, I can go to a sector and say I would like to go to cluster F or 15. And here we have it. I have a file with some text in it, and everything is contained within that cluster. In the case of floppies, clusters are normally 1 sector long. Here's the next one and the next one, which seems to be housing an executable file. We'll talk later in this course how you can know that. But Microsoft executables begin with MZ in the first 2 bytes. So that is how you can examine a FAT in ActiveAct. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to show you how you can use a little bit of Python in order to interpret the FAT. Now, I want to start by a couple of additions to our VBR code from earlier. So I've added a few more useful methods to our VBR class. And the first one is sector from cluster. So what this does is it uses the information that is stored in the volume boot record in order to give you a sector number inside of a volume given a cluster number. So how does it do that? It first determines the location of cluster 2, and then it adjusts from there. So where is cluster 2? Immediately following our VBR and any reserve sectors, and again, this is normally 32 or more for FAT32, and normally 1 for FAT12 or 16, I have to go across the two FATs. On the off chance that I have something other than two FATs, I've used my copies of FAT function here. So however many FATs I have times how many sectors I have per FAT. I then add in any reserved sectors. And if I have FAT12 or 16, I have to add in the root directory entries, those sectors. Now, how many sectors do I need? We haven't talked about directory entries yet. We will get there very soon. But there are 16 of those per sector. So I do an integer division on the number of root directory entries. I divide by 16, and that gives me the number of additional sectors. Recall that for FAT32, this will return 0, so this works for all cases. So now I have gotten to cluster 2, its sector, and from here, I will take the cluster minus 2, because we start from 2 for reasons unknown, times the number of sectors per cluster, and that gives me the final sector value, which I then return. I also created a method called offset from cluster, and it does the exact same thing, but it multiplies the result by bytes per sector, which is probably 512, in order to give you an offset into your image file. Similarly, I did the reverse, clusters from sector, a little bit of algebra here. You can reverse this process. So here you can see that we have all of these values. We subtract from the sector the things that we calculated up here, copies of the FAT times sectors per FAT, reserved sectors, root directory entries divided by 16. So we take all of these things and subtract them from the sector, and then we do an integer division, and we divide that by the sectors per cluster, and then we add 2 at the end because we start from 2 instead of 0, and I return that value. Similarly, I created a method called cluster from offset, and all it does is call cluster from sector, where I have the offset with an integer division of bytes per sector. I created 2 more little helper functions that will give you the sector for FAT1, which is just the same thing as the reserved sectors, and the sector to FAT2. So those are just some additions to our VBR class. I've also created a new class. The new class is called FAT, and it will read FAT entries. How does this work? Well, we start out with a constructor. Recall that constructors in Python are named double underscore init, double underscore. I have self, and then I have buffer. Buffer should contain the entire FAT. The first thing you want to do is figure out what kind of a FAT you have. We said that in all cases, the first byte is a media descriptor, which is usually F8. If it's a floppy, it will be F0. And just because it is certainly possible that you would have something other than F8 for FAT16 and 32, and it's also possible to have a FAT12 system on a hard drive. I skip over that first byte. So here I'm using a slice. Remember that a slice has a starting point and an ending point, and it includes everything up to but excluding the endpoint. So bytes 1 through 7 are compared to this value. Now, if I have a 32-bit FAT, I should have FF0F, and then 4 more Fs. Now, if it's FAT32, I should have FF0F, and then 4 more bytes of Fs. Notice that FAT16 has 3 bytes of all Fs. So this is one reason that 0F is put in this position for FAT32 in order to distinguish it from FAT16, which would have all Fs. Well, if it's not FAT32 and it's not FAT16, it must be FAT12. Once I've determined the type, I store the entire FAT in this class variable, underscore FAT, and then I defined a few other functions. First one I defined is called fat bits. It just tells you how many bits you have in your fat. The next one is called fat entry. So it will take a cluster number. Given a cluster number, it will tell you its entry in the fat. Now, I start out with a little sanity check here, and I say, if you didn't give me anything at all, if cluster was defined to be none, then I return none. That way, if you do something silly, like try to find a fat entry for none, it doesn't crash. And then I say, how many bits of fat did you have? If you have 32 bits, the most common, then I'm going to use my old friend unpack. I'm going to unpack a little ending 4-byte unsigned integer with no alignment. And where do I start? I start at the cluster number times 4 because there are 4 bytes per entry. And I go from there to that value plus 4. That gives me the appropriate slice. Recall that unpack will return a tuple. I only want the first item. It's the only item 0. So that's pretty simple. I have something very similar in the case of FAT16. Here, I have a 2-byte unsigned value, and I multiply by 2, but I have the exact same thing going on. The only thing that looks a bit odd is this guy. If it's FAT12 is kind of weird, and we talked about this in previous videos. So here I want to get my 3-byte chunk. My offset is my cluster number, integer division with 2, times 3. Now, if this was evenly divisible by 2, using the modulus operator here, it says I divided by 2 using integer division. The remainder was nothing, so it was even. Then it's the left entry in my little 3-byte chunk. In that case, I want to take the first byte. I use unpack again. Incidentally, there are other ways that I could interpret this 1-byte value that are perhaps a little simpler, but I thought for consistency, I would just use unpack. So here I get the first byte, and I need to get the lower nibble of the middle value, multiply it by 256, and add it to the other byte. So how do I do that? Here, I convert the value into a unsigned integer between 0 and 255, just as I did before with unpack. Then I only want the lower nibble. So if I do the modulus 16 on that value, recall that that means if I divide by 16, this is the remainder. So that is everything that's left when you divide out that upper nibble. I take that value and I multiply it by 256. Why do I do that? Because I'm going to prepend this nibble to my value if the cluster number was odd. Then I'm at the right entry. So how does this one work? Well, now I need to get that third byte here, offset plus 2, and I use unpack to get that value. But now that value has to be multiplied by 16 because the upper nibble of my middle value, which once again I'm getting here, just as I did in the other case, has to be added to the end. So essentially I need to shift over these two nibbles 1 nibble to the left. So I multiply them by 16, and then I add the upper nibble of the middle byte. So the inverse of what I did here, here I use the modulus 16, here I use integer division 16. Don't worry if some of this math seems a little confusing. You will likely never encounter this. I only included it for completeness. I also defined an isAllocated method. It says if the cluster is defined, again, if you did not give me a cluster that's equal to none, then I will return whether or not the fat entry for that cluster is 0. So recall that if it's not 0, it's in use. Otherwise, I return false. That means that you gave me a cluster of none. Next cluster. What is the next cluster in a chain? Once again, I have the sanity check. I say if the cluster that you gave me was equal to none, then I return none. Otherwise, I get the entry using fat entry that we just talked about. And then I want to find out, is this the end of the chain? Well, if you gave me a cluster that wasn't even allocated, then you're definitely at the end. If it was 32-bit and that entry was equal to this value, then there is no next cluster. And here's the end of file marker for FAT16 and FAT12. So if any of those conditions are true, I return none. Otherwise, I return the fat entry itself. I also defined a method called isEnd. Is this cluster the end of a chain? And that's equivalent to saying, does next cluster return none? Well, that's great having something that will give you single cluster entries, but what you really want is a cluster chain. And that's where this method comes in. So cluster chain, if you give me a starting cluster, which hopefully is the first cluster in the chain, I will return a list of cluster numbers. So how does this work? First, I create an empty list. Recall that in Python, if I want to create a list, I enclose comma-separated values in square brackets. We also have tuples, which are enclosed in parentheses. And recall that tuples are immutable. They do not change, whereas lists can be changed. I set my next cluster equal to the cluster you gave me, and I enter this while loop. I say while is allocated whatever the current cluster is. If it's allocated, append it to my chain. Then I will try to get the next cluster, and I will set next C equal to that cluster. Here it will say, is that thing allocated? Well, next cluster, if there isn't one, will return none, and is allocated on none returns false. So it will drop out. It'll keep going until it gets to the end, and until it gets to the end, it will keep on appending. When it's done, it will return my list called chain. As before, I define a usage and a main method. I've just modified what I already had. So I go through my partitions. Here I check to see if it's a valid VBR. If it is, I print out a little bit of information, and then I go ahead and grab the fat. So here I first seek to the right place. What is the right place? I need to go forward the number of reserved sectors as disclosed in my MBR, sectors that precede this volume, times 512. And then I go from there, from the start of this volume, to the sector of FAT1 times 512. I then read in 512 times the sectors per FAT, and I use that raw FAT in order to create a FAT object, and then I print out two values. I print out whether or not cluster 2 is allocated, and then I also print out its cluster chain. Let's go ahead and do a quick test of our new code. Here you can see that cluster 2 was allocated, and the cluster chain was pretty boring. It was just cluster 2. If you go back to some of the older videos, you can see that in fact cluster 2 was just storing the root directory in a single cluster. You might be suspicious of my little function here, my cluster chain function. And first of all, shame on you for suspecting that my code doesn't work. But just to show you, I'm going to go ahead and redo this for cluster 3. And there you can see that it still works. Obviously, cluster 3 had that really large file that we said was probably our paging file stored in it. And onward all the way up to cluster 344,998. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about FAT directory entries. So FAT directory entries, what are they? Well, they contain a file name. Now the file name is stored in what we call 8.3. 8.3 means that you have 8 characters for a file name, then 3 characters for an extension. The period or dot is not stored in the file name, and you have only 8 characters for the main file name. So you can't steal characters from the extension if you're not using the extension, etc. In most cases, that is. Now, you might question why such a short file name, and you have to remember the FAT file system is very old, goes all the way back to DOS. And with DOS, if you were storing things on a floppy disk, space was at a premium. And you will see several instances where extreme measures were taken in order to save some space. You need only look at the FAT12 system at all to realize that that was obviously done in order to conserve space to the maximum extent possible. Other things in directory entries, the MAC timestamps, the modified, access, and created timestamps, the file size, and the first cluster. Talked about cluster chains in previous videos when we talked about the FAT, and this is that tie-in. This tells you where that cluster chain starts. Each of these entries are 32 bytes long. In the case of subdirectories, the first 2 entries will be dot and dot dot, which stand for the current directory and the parent directory. So the only directory that is not a subdirectory of something else is the root directory. So it lacks these 2 entries. You might wonder why would you store these? And if you look into it in the way that you can easily traverse a file system, these certainly come in handy. Remember that all of this stuff is very old, and when it was designed, computers were not very powerful. So even though storage was at a premium, storing these 2 entries made it much simpler to search through a disk. There was also a kludge for long file name support that was added in order to lift the restriction to 8.3 file names. So what do these directory entries look like? They begin with our 8.3 file name, which of course takes 11 bytes to store. From there, we have an attribute bit vector. So how does this work? It's a bit vector. So it's a series of bits, and if a bit is 1, that attribute is present. If it's 0, it is not present. So starting at the least significant bit, bit 0, these attributes are read-only, hidden, system, volume label, subdirectory, and archive. So here, hidden and system are often used together. So hidden just means that it normally is not displayed if you were to do a dir command. System means this is part of the operating system, so you probably shouldn't be touching it. I very rarely have seen a system file that wasn't also hidden. Volume label is a sort of a strange one. We talked about the volume label before and where it can be present, and it can also be present as the very first entry in the root directory. Sometimes you will see it there, and sometimes you won't. It is 100% optional for it to be there, obviously, and I have seen it disagree with what is in the VBR before, and that normally indicates that someone manually changed that information. The archive bit is used to assist in creating backups. The idea is that as soon as you modify a file, the archive bit becomes set. So it's very common to see this set for almost everything. Now, how this used to work is that you would back up your system, and if you did an incremental backup, it would look for files that did not have the archive bit set. Once it found those files, it would back them up and then unset the bit. Following the file's attributes, we have a creation time and date. That's the first of our MAC timestamps. We then have a last access date. In this case, we do not have a time, and you might say, well, why not? Well, there's a couple of reasons why that probably is true. Number one, there's not a lot of space here. Number two, if you are dealing with something like a floppy disk, you probably don't want to write to it every single time that someone accesses a file. We then have the high word for the starting cluster. Now this is only used for FAT32 because FAT12 and 16 are obviously able to be contained within 2 bytes. We then have a modified time and date, then the starting cluster low word, which will be the only part of the starting cluster for FAT12 and 16, followed by the file size in bytes. Directories always have a file size of 0, which might seem strange because they do, of course, take space up on the disk. However, you can see what space they take up because there's a directory entry for the directories. So the directory entry for the directories will give the directory starting cluster. And how do you know how many clusters it uses? Well, that's where you go to the FAT, and the FAT will tell you that. A little bit more about these time and date stamps. They're stored in a somewhat compressed format. The time and the date each take 2 bytes. If we look at the times, we will see that they store the hours in the upper 5 bits, minutes in the next 6 bits, and then double seconds in the lowest 5 bits. Now you might say, what's up with the double seconds? Again, they had to save space. You would need an extra bit in order to store times to the nearest second. And when they designed this system, they said, no, that's not worth it. We can't spare an extra bit, and that would make this extra complicated if we did. Why would you care as a forensics person? The reason you would care is that if I'm creating a timeline on a FAT file system, I only know what happened within a 2-second period. So I can have an awful lot of files that have been touched within 2 seconds on my system. And there's no way of knowing which of these files was touched first. So this can make it a little bit difficult to build a timeline. Later in this course, when we talk about NTFS, we'll see that it has much better timestamp fidelity. And of course, it's not as good as the Linux timestamp fidelity, which those of you that have gone through our Linux forensics course know all about, because Linux will record down to the nearest nanosecond. The dates store the years since 1980. This is sort of the DOS or Windows epoch. Some of you are likely familiar with the Linux or Unix epoch, which started in 1970, but they only go back to 1980 in the case of DOS, because in 1970 it didn't exist. We then have the month and the next 4 bits, and the lowest 5 bits store the day. Let's talk about these long file name entries. These were added in Windows 95. These entries are also 32 bytes long. So this was done so that all of the entries in a directory are the same length. Previously, when we talked about the FAT, we said that there are 16 entries per sector because each of these is 32 bytes long, and 512 divided by 32 is 16. So these long entries contain no metadata. It's important that you remember this. All of the metadata, all of the good stuff that you probably really care about is stored in the single short entry. The only thing that these contain is the file name, the long version of the file name. Now these long file names grow upward from the single short entry. So you can have multiple entries depending on the length of the file name. Now, I will say this, I'm not aware of anyone that was ever condemned to prison or lost a lawsuit because of how they named a file. It's normally what's in the file that matters, not what you call the file. So let's get a little bit more detailed about these long file name entries. They start out with a sequence number. The sequence number says which long file name entry is this. So bits 0 through 4 have the sequence number. Then bit 6 has a flag. Bit 6, which has the hex value of 40, is a flag that says this is the final part. So if I have a file name and it's not terribly long, it's short enough to be contained within a single long file name entry, the sequence number will be 41, which says this is the first and the last. If it needs 2 entries, the first sequence number would be 01, and the second one would be 42, etc. So that's how the sequence number works. We then have 10 bytes for part of the file name in Unicode. 10 bytes is, of course, 5 characters, because Unicode requires 2 bytes per character. Then we have 2 bytes that will always be 0F00. You might wonder why I have these values. If you look back at our previous slides, you will realize that it's set here as a marker, because if I have this stored in this position, it is invalid, because this is the attribute position. I then have a checksum for the short file name. This is another double check. So I calculate a checksum for the short file name, and if I have a bunch of long file name entries that are supposed to be for the same short file name entry, the checksum should be the same in each of these. I then have another 12-byte chunk of the file name, 2 bytes that are always 0. These are the starting cluster. Again, starting cluster of 0 is invalid. I then have the last 4 bytes in this entry as part of the file name in Unicode. So if you do a little bit of math, you'll find that I have, of the 32 bytes, 26 that can be used to store a file name. So that's 13 characters. Now, if I reach the end and I don't use all of them, you will normally find either 00 as the last 2 bytes, a null terminator. You don't have to have a null terminator. So for example, if you exactly used up the entry, no null terminator is required. I have also seen Fs placed in unused positions. So you might see either of those if you start examining your directory entries directly. Finally, a word on deleted files. When you delete a file, the first byte in its directory entry or entries is changed to hex E5. The first clusters are marked as available in the FAT, and depending on the version of Windows, if you have FAT32, it might zero out the high word for the starting cluster, which can make it a little bit difficult to get your file back. So if you have FAT12 or FAT16 system, it's actually extremely easy to get your file back. In some cases, we will talk about this in detail later in this course, different ways of trying to recover deleted files. We will also examine the directory entries inside of ActiveAt and using Python and some other tools as well. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to examine some directory entries with ActiveAt. So I want to start by adding an image. Click on Add Disk Image. Recall that you'll need to say all files, most likely, for your disk image. And I'll go ahead and open up this guy we've looked at before. If I click here, it tells me that this is a FAT32 file system. I will click on the volume and then select Open in Disk Editor. And here you can see I have my volume. I will navigate to the root directory, and you'll notice that it's displayed kind of funny. And why is that? For whatever reason, ActiveAt did not update my template. So I'll just go over here and say, please select FAT directory entry. And now we can see our first entry. Now we said before that the first entry can be a volume label. In this case, it is not. If I use my template, I can decode the information here pretty simply. It's telling me my file name is page file and its extension is sys. Its attributes are hex 26. I can expand that and I will see that this is a hidden system file. As we said, these are often found together. It is also an archived file. So the archive bit has been set. If you do a little bit of math, you will find out that bit 5 is 2, 20 in hex. So whenever you see an attribute that says 2 and then something else, it is probably an archived file, which is most of the files. Here we have a creation date and time. We talked about how this is stored internally, but of course we've used our tool here to decode that for us. As we said before, there is no access time, only a date. And then we have the first cluster, the high word, modified date and time, and the first cluster, low word, and the file size. So this is a fairly large file. It's about 2 gigabytes. Notice that this file started in cluster 3. So if you remember some previous videos, when we examined the same file system, when we looked at cluster 3, we saw a very long cluster chain. And that's because we had a very large file there. A little tip here in ActiveAt, if I click on one of these hyperlinks, it will take me to that cluster. So this is cluster 3. If you don't believe me, you could always use the go to sector function and go to cluster 3 and you will wind up in the exact same place. But I won't do that right now. I'm going to click back to go back to my directory. Now, ActiveAt provides these up and down arrows that will allow you to scroll back and forth through a directory. So if I click the down arrow, it will go to Windows. So this is a Windows file. If I look at the attributes here, I will see that this is actually the Windows directory. I can see its creation dates, times, access date, modified date and time, etc. Notice that this does not have the archive bit set because it's never been changed. It was created and stuff was put in it and that was it. Here I have the NT loader, which is another system file, ntdetect.com, yet another system file, boot INI. Not surprisingly, a lot of these files are hidden system files. If I go to the next item, you will notice that ActiveAt was smart enough to say, oh, this is a long file name entry. So as we said in previous videos, if you have a long file name, all of the metadata is in the short file name entry at the bottom. So if I scroll here in my template, I will see the file name is documi-1, and it has certain attributes. The file size is 0. And why is that? Because this is in fact a directory. So how does this long file name work? We said that it begins here, right above, and notice the sequence number is 01. So this is the first one, and there's more to follow. And then here we have in Unicode, documents, space, and then we go to the next entry. It has a sequence number of 42. It's the second one. It starts with a 4. That means it is also the last entry. So we have documents and this starts with a space, x2000. Recall that to go from ASCII to Unicode, all you need to do is add 00. It's stored in little endian format, so it's technically 0020, but it's stored on disk as the ASCII code followed by a 0. So here we see documents and settings. And as I said before, once we get to the end, here's the last character, we have 00, and the remaining bytes are filled with Fs. We also said that there will be 0F, 00 in these two positions. And what comes next, this next byte, is a checksum for the short file name entry. And sure enough, I have 4A here and I have 4A there. So this all agrees. If I click on the down arrow, you'll notice that it just skipped over another entry right here. So this is a little glitch that I found in ActiveAt. This is actually something that we've reported to the maker of ActiveAt. Who knows? Maybe by the time you're watching this, they will have fixed this little glitch. It's somewhat annoying, but easily gotten past. So if I go to the start of this entry and I right click and I say set template position, now all is happy again. Once again, it will show me program files is the long file name. Incidentally, if you scroll and you look at the Unicode, you might notice that it's not showing up correctly. To be fair, the reason that it's not showing up correctly over here is that the alignment is off. Because this starts at position 1 instead of position 0 or even position 2, the alignment is not what is expected by the editor, so it does not show up accurately the Unicode in the long file names. So just something to be aware of. Once again, it skipped over a couple of entries. What about this entry here? Here is another glitch that I found in ActiveAt. If I have a long file name and I delete the file, E5 gets put into all of the directory entries, including the long file name entry. So ActiveAt appears to interpret this incorrectly as a very long sequence number. So because it thinks this is a very long sequence number, it says, wow, this is a really, really long file name. So it will go to the maximum of a file name's length. This is the longest possible file name that you can have in Windows. So another thing to keep in mind if you're using ActiveAt. So I'm going to go ahead and click on the short file name entry, set my template position here, and now it looks a lot happier. Another thing to note, if you do have a long file name and you delete the file, normally you would lose the first character of the file name. However, because the file name is offset by a byte from the start of this entry, you can recover that first character. So I can say, yes, this first character was definitely a C. It says so right here. So this file used to be called config MSI. How large was the file? 8K. The low word for the first cluster was 49,983. What about the high word? It says the high word is 0, but remember the little caveat I told you about. I said sometimes, depending on the version of Windows, for FAT32, it's going to zero this out. So how do you know if it's been zeroed out or not? One way is you can try the hyperlink. And I see that this is a Microsoft executable. And I can ask myself, does that make sense? I can also look at the FAT and see if this cluster has been allocated or not. Click back. You can see that this file config MSI has been deleted multiple times. See multiple entries for the exact same thing. Here you can see another directory, Castle Wolfenstein, etc. So that's the root directory. So if I want to look at another directory, I can just look at its entry. Here it says that this is stored in the cluster with a high word of 9 and a low word of 6848. If I click on the hyperlink, it will take me to this directory. I will set my template position, and notice, as we said before, the very first entry will be dot. It points to itself, and it says, here's where I'm stored in this cluster that I'm currently in. I have a file size of 0, etc. If I go to the next entry, it says, you are my parent. Now, in this case, you might say, why does it say 0 for the cluster? 0 for the cluster means that this is the root directory. Even though the root directory is usually stored in cluster 2, it will be registered as cluster 0. This is partly for backward compatibility with FAT12 and 16, and also the fact that the root directory could be moved. to another cluster. So the fact that it started with dot and dot dot immediately tells me I'm looking at a subdirectory, and here I have my various entries. And once again, I have a deleted file, which is really making this unhappy. I can make it happy again by setting my template position on the short entry, which is the only important one anyway. If I click on this hyperlink, it will take me to the cluster, and I know that this high word has been zeroed out because this is definitely not a Word document. Again, we'll talk about that later in this course. We talk about file signatures, but you can see pretty clearly that this looks more like a text document and definitely not a Word document. So I'm going to click on back, and you can see here is my entry. So that's FAT32, which again is most likely what you're going to see. Just to show you, I'm going to go ahead and open a floppy image that's FAT12. Open it in the disk editor, navigate to my root directory, reset my template, like so. Now notice, in this case, the first entry was in fact a volume label. So it did come up as Wombat, and it has the archive bit set, which we said is not unusual. I can scroll through my directory entries, and here you will see that I have a deleted file. This one was probably called file1.txt. We'll talk more about recovering deleted files later, but you'll notice that this has a starting cluster of 832. If I click on the hyperlink, it tells me that here's my file. So it would appear as though this deleted file was a text file that had a secret password for the day. I should really verify this by going to the FAT and looking at it. We will do more of that kind of work later, but I just wanted to show you that in the case of FAT 12 and 16, sometimes the file recovery can be easy. It certainly is easier than the case of FAT32, where someone zeroed out the high word for your starting cluster. Here we have a new folder, and it has a name. Again, starts from the bottom and works its way up. So I have sequence 1, 2, 3, and 4, 4. And it says this is called new folder with a really, really long and silly name. If I try to go to the next entry, once again, it will get confused. And why is it getting confused? It's getting confused because I have a deleted file with a long file name. If I set my template position at the start of the short entry, it gets unconfused. Once again, I can click on the hyperlink here and say, is this actually a directory? Obviously it is. It starts with dot and dot dot. So you can see some interesting information in this old directory entry. I'll go ahead and go back. And here I have another deleted file. Again, if I click on the hyperlink, I will see that this looks like a text file. So there you have it. There's the basics of looking at directories inside of Active@ Disk Editor. And we'll do some more examining of these things with Python and some other tools in the future. But that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to show you how you can use a little bit of Python in order to interpret FAT directories. So I've added a pretty good chunk of code here in a new file. So I just wanted to go through this with you. As usual, we start out with some imports of previous code and some system code. I have my all list, which is used in order to say if someone does from my file directory import star, what is included with that. I define a couple of helper functions. We'll come back to those. And then I define a few classes. So the first class I've defined here is called directory entry or dir entry, and this is used for the raw directory entries. Recall that these are 32 bytes long. They can either be a long file name entry that has nothing but a name, or a short entry that has a short file name and all of the metadata. So this particular class represents the raw directory entries. So you create a dir entry object by giving it a buffer. That buffer should be 32 bytes long. The first thing I do is I check that first byte. And if that very first byte is equal to E5, that means that this is a deleted entry. Then I check and say, is this a long file name entry? Well, how do I know? There are a couple of easy ways to tell. The easiest way is to look in position 11 and 12 and see if we have the value F00 in those 2 bytes. If we do, then it's a long entry. Long entries begin with a sequence number. As we said previously, we could translate this single byte into a value other ways. For consistency, I've used unpack as before. So I get my sequence number, and also, you might remember, if a certain bit is set corresponding to the value of 40 hex, that means that this is the last entry. So I will check for that as well. I next get the checksum out of my entry, and then I create the file name by adding together the 3 different buffers. So I have the first part from position 1 through 10, then 14 through 25, and then 28 through 31 at the very end. I concat all of that together. Then I check for nulls. Nulls will just get interpreted by Python and added to my string, and I don't want that. So what I've done here is I've used the find method. Find works on strings and also byte strings that we have here, and it will return the index of a value if it is found at all. So if it returns a number that's greater than 0, meaning that it found nulls in this string, then I'm going to look at the slice of this byte string from the beginning. Notice this part is blank in my slice, up until where I found this +1. You might say, why is the +1 there? Recall that when we convert ASCII to Unicode, we have the ASCII value and the next byte is 0. So we will typically have 3 zeros in a row, and that would cause us to be slightly off. So we have to include that 0 byte that is part of the last character. I then call decode, and I tell it, here is my Unicode encoding. Now this is the world's simplest Unicode decoding. It's called UTF-16. It means that I need 16 bits in order to encode a character. It's not widely used for most things because it's not very compact. I also check for the all Fs that you might also see in some of these entries, and I do something very similar. Otherwise, I just go ahead and decode away, and I convert my byte string into a normal string. So that's the long entries. If I look at my else clause, now I'm looking at a short entry. I first set long entry to false. I will check to see if this is a deleted entry. And the reason I do this, if I just try to convert my byte string to a regular string, and the first character is E5, it's going to complain. So to prevent that complaining, I check for that special case. And if it's an E5, I will put an underscore in the place of that funny character that I normally would get. And then I start at position 1 and I decode the string. Now here it's UTF-8 because it's just ASCII. And this is a very easy way to convert between Unicode and ASCII, or in this case, you're converting from a byte string to a typical, normal, if you will, ASCII string. A file extension we can easily decode. We shouldn't have any issues there. I check to see if there are any nulls in the name, and if so, I will remove them. Once again, I'm going to use my find. I read in my attributes from the entry. I don't interpret them here. We'll show you how to do that later. Then I do something that, if you're not a Python programmer, might look a little strange. I've actually assigned 3 values at the same time. So how did I do that? On the left side of my equal sign, I have created a tuple by enclosing 3 values in parentheses. And on the right-hand side, I have called a function, fat time. I pass it a buffer, the appropriate 2 bytes for the creation time, and it will return a tuple. This is one of the helper functions that we skipped over previously. I do the same thing for the date. I call my helper function access date. Remember that there is no access time in the FAT file system. I do this as well. I do the same thing down here for modification times and dates. So let's have a quick look at these helper functions. Here's my fat time function. What it does is it extracts the 2-byte value for the time, stores it into val. As usual, I've used unpack, and then I want to get the various parts. So how do I do that? The seconds, or double seconds, are stored in the lowest 5 bits. So 2 to the 5 is 32. If I take my value modulus 32, remember this is the remainder when you do an integer division by 32, that will give me the lowest 5 bits. And also recall that I need to multiply by 2 because these are only stored as double seconds because there wasn't enough space. For hours, I want the upper 5 bits. So to get the upper 5 bits, all I need to do is divide by 2 to the 11th. That will get rid of the lower 11 bits. 2 to the 11th is 2048, or 2K. So if I do an integer division, that knocks off the top. That leaves me with minutes. How do I get the minutes? Here is what's left after we take off the top 5 bits. And I want to take that value where I use the modulus here, 32, in order to get rid of that part, the seconds, and extract just the middle 6 bits. I do an integer division of 32. Once I've done all of this, I return a tuple that contains the hours, minutes, and seconds. My fat date helper function is very similar. I also need the lowest 5 bits to get the day. The upper 7 bits give me the year, to which I must add 1980. Recall that that's the epoch for Windows. To get the upper 7 bits, I have to remove the lower 9 bits. 2 to the 9th power is 512, so I do an integer division with 512. As before, I can get the lower 9 bits by doing a modulus 512, and then I get rid of the lower part and extract the middle 4 bits by dividing by 32. And once again, I will return a tuple. So let's go back to a couple of the remaining values here. We have our starting cluster. Recall the starting cluster is stored as 2 words, and each word is stored in little-ended format. So what I've done here is I've taken 64K times the value in the high word, and to that I add the value from the low word, and that will give me my starting cluster. The easiest one of all, of course, is the file size. which is a 4-byte unsigned integer at the very end of the entry, and I just use unpack in order to get that entry. I have a function called long entry, which tells you if this is a long entry or not. Similarly, I have a method called deleted, which will tell you if this is a deleted entry. And I have a method called file name that will tell you the file name. If it's a long entry, it just gives you the name that's stored. If it's a short entry, it will give you the base name plus a period plus the extension if there is an extension. Otherwise, it will give you just the base name. Create time will give you the creation time if it exists. Similarly, create date, modify time, modify date, access date. Also, you can return the start cluster if there is one. If it's a long entry, none of these values apply, and I return none. And I also can return the file size. So that is my simple class for the raw directory entry. I also created a file entry class. Now this class represents a file entry. Now a file entry can contain multiple raw directory entries. If a file has a long file name, there will be more than one raw entry that make up a file entry. Now I did make a design decision, and if you have a deleted entry, it is stored as just that deleted entry. The reason that I did this is that it's certainly possible that you delete a file with a long file name and later you create a new file, and some, but not all, of those entries get reused. And it would be kind of complicated and it might lead to some weirdness if you tried to recreate that long file name. And as we've said before, you probably don't care what files were called anyway. It's usually what's in the files that is going to be condemning people and not so much what they were called. So this constructor takes a buffer. Now it's assumed that this buffer contains the entire directory, which could be multiple clusters. It also will take an offset. The offset is defaulted to 0. And how does this work? It creates a list called dir entries that is initially empty. It then checks to see if the first byte is 0. If the first byte is 0, this is an empty entry, and I just return. That creates an empty list inside of my object, which is fine. If this first entry is deleted, then I append it to my list and I return. Because as I said, if it's a deleted entry, I'm just going to store it separate. Is it a long entry? If it's a long entry, I'm going to scan forward until I find a short entry. So I set a variable, offset, which is my offset, plus 32, plus the length of an entry. While the current entry is a long entry, I'm going to append that entry to my list. I will then check once again to make sure that I don't have a 0 entry as the next one in my list, which this shouldn't happen, but this is just kind of a little sanity check because occasionally bad things do happen to directories. I then use my offset value to get my next directory entry. I add 32 to it to go to the next value, and then I get back to the top of my while loop. It's going to once again check and say, hey, is that guy a long entry? If he is, I keep going. Now, if I get to a short entry, it's going to fall out. It's going to end this while, and I will append that entry to my list. So this list is in the same order as what you have on disk. You have all of the long file name entries that come first and the short entry at the end. Also, remember that these long file name entries build upward from our short entry. So everything will be, in terms of the file name, in reverse order for a long file name. If it was just a short entry, I simply append that, and that's the end of my constructor. So at the end of calling my constructor, I should have a list that is populated with all of the entries that pertain to a certain file in the exact same order as they are on disk again. I created a method called entries that tells you how many entries are in this list. I used the len or length method. I had a method to determine if it's empty or not, and also if it's deleted. If it's a deleted entry, then the very first entry and the only entry will be deleted. I created a method to determine if it has a long file name, another one to determine if it has a short file name. If the first entry is a long entry, it has a long file name. If the last entry, so I look in my list at index, total number of entries, -1, and I say, is that a long entry? If it's not, then it has a short file name. I return the long file name by first checking to see if it has one. If this is a single deleted entry, I simply return the file name. If it is not a single deleted entry, I need to scan through the different entries, and I want to go from the number of entries -2, that's my starting place. So from the second to the last entry to -1. You might say, well, that's kind of weird. Why am I going to -1? Well, it's because I'm using my range function. Now, it has a third parameter that we don't use a lot, and I don't believe we've used it so far in this course, which allows you to have a step. So I'm actually stepping backwards through this list. Why am I doing that? Remember what we said before. These long file names grow upward from the short entry. So we have them in reverse order in our list. So we traverse that list in the reverse order and use that to build our file name, which we then return. Similarly, we will return the short file name, which is the last entry, unless it is a deleted entry that contains a long file name fragment. We can also return the attributes. We first check to make sure it has any, and if it does, we return them from the last entry. I also created a bunch of helper functions which will tell you whether or not the various attributes are set, such as read-only, hidden, etc. And here I'm using the bitwise AND operator and saying I'm going to do a bitwise AND with a certain bit that corresponds to that attribute. And if the result is not equal to 0, then it has that attribute. I do something very similar to retrieve creation times, dates, etc. I go to the last entry if it has a short entry, and then I use the methods from my dir entries class in order to get those values. I also defined a pretty print method, and this is just a nice convenient way of printing out these different file entries. And I go through the different attributes. Is it empty? Is it deleted? Does it have a long file name? If so, print it. Does it have a short file name? If so, print that. I print out the starting cluster, file size, the attributes when it was created using another helper function that converts my tuples to a nice pretty string. I print out my date and time for that, date that it was accessed, and date and time that it was modified. Finally, I created a directory class, and this class represents a collection of file entry objects. So this is created by passing the constructor all of the appropriate clusters for a directory. So how does this work? It creates an empty list. I set a variable called offset, and I say, well, the offset is less than the length of this buffer. So while I'm not at the end of this list, let's add stuff. I do a little quick check here to say, is the first byte 0? If it is, we're done. We've gotten to the end. Otherwise, I create a file entry at the offset that I'm currently working with. I increase my offset by 32, the size of each entry, times the number of entries in the current directory entry, the current file entry. And I will append to my list. And I keep going till I either hit an empty entry or I get to the end. I defined a couple of methods here. Entries just returns how many things are in this directory, and list lists them using the pretty print function that we defined earlier. So here I've defined a main method as usual, and the main method will take an image file, and essentially this is going to build on what we've used previously. So I'll just scroll down to the new parts. So in a previous script, we had grabbed the FAT and we printed out a couple of things like, is this cluster allocated or not? And now I'm going to grab the root directory. So how do I do that? I get my cluster chain, which I store in C chain by calling cluster chain for cluster number 2 from my FAT object. I define an empty buffer that is a byte string, and for each cluster in that chain, I will seek to the start of my file system, which was the MBR's reserved sectors times 512 plus 512, my sector length, times the VBR's sector from cluster. This is a method we talked about in a previous video. Once I have that, I append to my buffer by reading from my file. How much do I read? 512 times the number of sectors per cluster. Now that I have my buffer, RD buffer, read in correctly, I create a root directory object by calling the directory constructor, and then I list it out. So now we're ready to try out our new script. Go ahead and run it on an image that we've seen before. And voila, it works just fine. So here you can see the various entries in the root directory for that image. Now we will make better use of this new code in some future videos. For now, we've pretty much just used some Python in order to interpret some directory entries, and you might say, well, what's the big deal there? And honestly, it's not a huge deal because we haven't really put it to use just yet, but we will in the future, I assure you. And besides, it's always good to know how things work. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, I wanted to show you how to use a tool called the Sleuth Kit in order to investigate some images. Now, those of you who have gone through our Linux course might recall that in the case of Linux, the Sleuth Kit and Autopsy, which is the graphical environment based on the Sleuth Kit, are not terribly useful in the Linux environment, primarily because they haven't been updated in a really long time. However, the situation is a little bit different in the Windows world. So I wanted to show you how you can use some of these tools as an alternative to some of the other things that I've shown you so far. So first of all, how do you get the Sleuth Kit? Well, if you're running Linux, then it's pretty easy. All you need to do is something like sudo apt get install Sleuth Kit, and that should be all you need to do. You can also build it from source, which you don't necessarily have to do. But if you just want to run the Sleuth Kit tools, It's very easy to install. So what are these tools? The Sleuth Kit is a command line toolkit, and you will see a bunch of tools. There are some tools that work at the disk level, and then there are those tools that work at the file system level and then at the file level. So let's start at the top. So if I want to look at the disk level, those tools begin with MM. So if I type MM and hit tab, you can see I have a couple of tools. Now, all of these are not part of the Sleuth Kit. The ones that are MMCat, MMLS, and NMStat. So let's start with MMLS. I do an MMLS --help. It will tell me a little bit more about this tool. Now, this tool is used to list. ls is the list command in Linux, kind of like dir in Windows. So I can use MMLS in order to find out more about a file. So I will go ahead and run this against an image. And here you'll see that it's listed out the partitions. Now, this might look a little strange to you because of the way that the Sleuth Kit numbers partitions. So we have our primary table, our MBR, which is in partition 0. Then we have unallocated space, those reserved sectors. And then we have partition 2, which has our FAT32 file system. And then we have partition 3, which is a little bit of unallocated space at the end. Now notice that I can look into an image. I can look down into the partitions and get a little bit more. There are a few switches for this command that I can use as well. What about the mmstat command? You can see that mmstat will take an image file again, and it will give you some information on that image. So let's go ahead and try this. And it says, yep, that's a DOS image. So by default, it doesn't really tell you much. What about mmcat? This will actually cat out to standard output part of the disk. So I can use this to stream a disk. So I'll go ahead and start this. I'm not going to go too far, but I'll once again go ahead and cat partition 2 from my image. And you can see here it is. So that's not normally something you would want to display onto the screen, but that is how the tool works. It lets you stream a partition from an image. So those are tools that work at the disk level. What about tools that work at a lower level? These tools start with F. So if I do an FLS, for example, --help, it will tell me that this will allow me to do an ls on an image file. Now, if I have an image that contains multiple partitions, which most of them will, then I need to give it an offset as well. So if, for example, I do an FLS-O, and then I give it my offset, 63 sectors to the beginning of my volume. I give it my image file name. You will see a listing of my root directory. So you'll notice there are a bunch of directories, such as my Windows directory, my page file, we said was started in cluster 3, and there are some other entries as well. Here, where you see an asterisk, the asterisk is telling you that this file is deleted on this image. There's an fstat command that will give some statistics on a file system, which I honestly don't use very much. There's also a find command, ffind. Once again, we'll bring up the help, and you can see what it is that you're trying to find. So, for example, I can do an ffind, offset 63 again, my image file, and I want to look at 2. That's cluster 2. Now, by the way, if you look at some of the documentation for the Sleuth Kit, it might refer to things as inodes. those of you that have done the Linux course know, are a Linux file system thing. So wherever you see inode, you should replace that with cluster number in the case of using a Windows file system inside of the Sleuth Kit. So here I've said what's in cluster 2, and it said the root directory. I can repeat this and say what is in cluster 3, and it tells me it's that page file. I can say what's in cluster 10,000, and now it's working really hard to figure this out. And the answer might be nothing. There is a FCAT file. FCAT allows you to output the contents of a file. So I'll go ahead and do another FLS. And notice that I have an autoexec.bat file. So now I'm going to do an FCAT on autoexec.bat for my image. And it printed out nothing, probably because I believe that file was actually empty. So let's try another file. And here you can see what was in this short file. So this would work for longer files as well. So that is the FCAT command that will allow you to get the contents of a file. A couple of other useful commands in the Sleuth Kit. There's a command istat. Istat will tell you about a metadata structure, which normally means an inode, but in the case of a Windows file system, it means a cluster. So for example, I could say, tell me about cluster 2, and it says cluster 2 is the root directory. It has a size of 8K. It is one cluster long, and it has null times for its written, accessed, and created timestamps. Here are the sector numbers that correspond to this file, which is actually a directory in this case. And that's another thing that you can do with the Sleuth Kit. Now, there are some other commands in the Sleuth Kit that deal with blocks. And all of these commands begin with BLK. So if I say BLK, tab, you will see I have a block calc, cat, ID, ls, and stat commands. So let's try the stat command. And we see, as normal, we need to give it a offset and an image file. And here it's giving me a sector number, but I might want to use, instead of a sector number, a cluster number. So how do I go from one to the other? Well, for one thing, remember that we saw what sectors we had in our root directory. So the cluster 2 started at sector 20,472. It tells me that this sector is part of cluster 2, and it is in fact allocated. What about BLK LS? Once again, it accepts the standard parameters such as an offset and an image file. We can use block cat. So block cat will output the block that you specify. And here you can see that I've output the first sector for the root directory. It, of course, doesn't look pretty because I have a lot of binary data, but you can see that the first file listed is page file sys. I also have my Windows directory and a few other recognizable names as well. Those are just a couple of commands that you can use from the Sleuth Kit. There are certainly more commands in the Sleuth Kit, and of course Autopsy has a lot to offer as well, but I just wanted to show you some alternatives to looking at the file system at a higher level on the command line inside of a Linux system. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, I wanted to give you a little introduction to Autopsy. Now, Autopsy is a graphical environment that is built on top of the Sleuth Kit. So the Sleuth Kit can be kind of powerful, but at the same time, a little bit cumbersome to use. And so the developer of the Sleuth Kit, Brian Carrier, has developed a product called Autopsy that runs on top of it. A couple of things you should know about Autopsy. Autopsy was originally built in Linux, and then support for DOS, Windows, and Mac were added. Over time, as the product has developed, the support for Linux and Mac has been a little bit less than the support for Windows. So I can install Autopsy by doing the normal sudo apt-get install Autopsy. Unfortunately, that will give me Autopsy version 2. Now, Autopsy version 2 will create a web server that I can use in order to do some forensics. The current version of Autopsy is Autopsy version 4. So there's quite a difference in functionality between version 2 and version 4. So you probably want to run version 4. So what are your options? There are a couple of options if you would like to run version 4. Option number 1 is that you can download the Windows version and run it inside of a virtual machine. If you just want it to work and you want it to be super easy, that certainly is a possibility. I don't think it's necessarily the best solution if you think you're going to use it a lot, but it certainly would work. The other option that you have is to download the source code for Autopsy and build it from there. So how does that work? If you go to the Autopsy GitHub, which is at this address, github/sleuthkit/autopsy, and from here, if you click on the file called building.txt, it will give you some detailed instructions on how to build Autopsy. So what do you have to do first? The first thing you need to do, per the instructions, is to get the JDK version 1.8. Now, one thing you should be aware of as of the time where I'm recording this video, it says that you'll need this version 18066 or greater. Well, this is the absolute latest version of Java available. So if you go to Oracle's website, you will see version 18065, which is the standard version, and 66 is a development version. So you have to be certain to download the correct version of Java. Once you've downloaded that, you have to set a variable called JDK home and set it equal to your JDK root directory. So in my case, what I've done is I've created a JDK directory in my home directory. So I would export JDK home equals home fill JDK, etc. There are some optional items. I found that you don't need to do these at all. Then you want to get the code for the Sleuth Kit. So how do you do that? You get the code for the Sleuth Kit by going to this address, github/sleuthkit, and you can clone it. So I'll go ahead and repeat that process real quickly for you. This is not what I did before. I already did this. I did a git clone of, and it tells me that that already exists. So when you do this, it will take just a little bit of time. Once you've downloaded it, you're going to need to build the Sleuth Kit. So the first thing you'll need to do is download the Sleuth Kit. Now here's a big tip for you. You definitely want to know this. If I go to the Sleuth Kit and I read the install, you'll see that it says this is super easy to do. All you need to do is run, make, and then make install. Well, that's not quite true. First, you have to run this tool called configure. Now, this is a standard thing to do on a Unix or Linux system. Configure will find out if you have the appropriate dependencies, and then you can run make. So configure will create the make file. Now, it is likely that if you did a git clone, you will not have a make file. So you will need to run a bootstrap script. Before this will work, you need to have these three packages installed: automake, autoconf, and libtool. So you would install those with sudo apt-get install, automake, autoconf, and libtool. And in my case, it says that I already have them installed. So that's the first thing you're going to need to make sure you do. Once that's installed, you can run the standard configure, and it will create a make file. Once that's completed, you can run make. Once that's completed, you can run sudo make install. Next, it will tell you to create a jar file by typing this command. Ant is a Java tool for building things usually. It can be used for other stuff as well. Dist-PostgreSQL in bindings Java. So here inside of my Sleuth Kit, I need to go to bindings Java, and then I need to run that command, ant, etc. You have to make sure that you set TSK home to be the root of your Sleuth Kit directory. So once again, as soon as this is done, you should now have your make file here. And if you do a sudo make install, it will install all the appropriate libraries. Export TSK home equals home fill Sleuth Kit or wherever you installed it. And now you're ready to build Autopsy. How do you get the Autopsy source? Once again, you do a git clone. Here's the address, it's given. And then you can build it using ant inside of the Autopsy directory. So now you can switch to wherever you downloaded Autopsy and you just type ant, and that will build Autopsy. Now I say it will build Autopsy, likely it will fail. And what I found, at least when I did this, is that it failed because it complained it could not find a certain file. So I'm going to go back to the Sleuth Kit here for a second. Go to the bindings, Java, and notice there is a dist directory. If I do an ls on dist, there is the file TSK data model that was created. Now in my case, as soon as I try to run this make using ant for Autopsy, it complained that it didn't find this file, TSK data model underscore PostgreSQL.jar. All I did was copy this file, which I believe is the correct file, over to this file name as well using CP. Once I did that, I ran ant. It completed successfully. In order to run Autopsy, you need to go to the Autopsy directory and run ant run. So I know that seemed like a little bit of work, and it was, but again, if you don't want to bother with this, you could just run Autopsy in a virtual machine, or you could run the really old version of Autopsy if you choose to use it at all. All right, so once Autopsy opens, notice that it says it's open, extensible, and fast. I'm not sure how many people would agree with the fast part, but it certainly is open and extensible. You can create a new case or open existing cases in Autopsy. We'll go ahead and create a new case just to show you the process, and I'll call it test. You can give it a case number, and this is something that you can assign. I'll just say test 1. You can also enter an examiner's name and go ahead and click on finish. And it says, well, you probably have some data for me. So give me a source image if you would. I will go ahead and browse for a file. I can select a time zone, click next, and there are a bunch of ingest modules. So ingest modules are just different things that are run whenever you import a new image. And you can add to this, you can get some extended modules, you can make your own, and all of that. I'm going to go ahead and unselect PhotoRec, but you can see we have things like recent activities, hash lookups, file type identification, EXIF parsers, so I can get EXIF information from my JPEGs. I can do keyword searches, parse through email, look for mismatched extensions. Got some Android verifiers I can use. And you can decide what you want to use here. Once you click on Next, then it will take a little bit of time as it goes through this image and it tries to run all of these different modules. So now I've loaded up my image and I've actually let Autopsy chew on this for quite a while, about 6 hours or so, in order to ingest my image. So, they do claim it's fast. I'm not sure what their definition of fast is, but at any rate, I wanted to give you a little bit of a tour of Autopsy. So once you've imported your items, you added your data source to your case, you will get a view that looks kind of like this. At the top, you will have the data sources. The data sources will include any image files, such as the one that I imported here. If you expand those, you will see the various volumes. And again, just like with the Sleuth Kit, these are a little bit weird in that you have volume 1, which is that 63 sectors of reserved space before you got to the real volume. And you also have another volume that's a little bit of unallocated space that follows your file system. If I click on my FAT32 file system, you will see in this window, I have a list of files. The ones with the little red X's are deleted. So we can see this config MSI file, which is actually a directory, has been deleted multiple times. I can get the file metadata. I can look at my files, such as my boot INI file. I can look at the hex. I can also extract the text that is available. And I can do this for all of my files. So this view is really, in a way, similar, at least in terms of functionality, to what you get with ActiveAdd. The biggest difference being that here it shows up deleted files. Now, in ActiveAdd's favor, it doesn't take anywhere near as long to load your image. So you can have instant access instead of waiting up to several hours while the ingest process is going on. It's possible to do some work with Autopsy while it's ingesting files. However, I found that sometimes some weird things happen if you try to do that. So that is the data sources. That's kind of the raw view, if you will. Then we have views. Views allow you to see your files by file type. So we can see there are a couple of classifications here. I can expand this. One nice feature of Autopsy is that it'll give me file counts. So I can see there are 14 video files. If I have the appropriate codecs to play a file, if I click on the file, the media tab here will be enabled and I can look at that file. So it would appear that I don't currently have the appropriate codecs installed in order to watch any of these videos. I, of course, could extract the files and watch them externally if I thought they were of interest. Here I see some of the WAV files, which I am able to play. My computer's not currently set up to play MIDI files. I can see various archive files. Mostly I have cabinet files, but I do have some zip files and some jar files, which are Java archive files. So that can be a useful view if I'm looking for a certain kind of file. I can also look at documents. Here's a rich text file, executables, and deleted files. Notice that there are over 3,000 deleted files on the system. That is not at all unusual. Another feature that you might find useful here is the size filter. So I can look at files based on their size. You might say, why would I want to do that? If I look at things like graphics files and video files, they tend to be large. Notice on this system, there is only one file that is more than a gigabyte, and that is the page file. There are 28 that are in the 200 megabytes to 1 gigabyte range, and 13 in the 5 to 20 megabyte range. So in other words, on this entire file system, we have less than 50 files that are larger than 50 megabytes. So this can help you to find some files that are suspicious. Under results, we'll talk more about this in later videos, but this is where you can get some information from those various ingest modules that you've run. So I can get EXIF metadata from my JPEG files that have that metadata. So you can see here a picture. So here's the picture. Here are the results. This was a device type of a Nikon D5100. That was the camera that was used to take this picture. There's no geotags in this picture, which would have been nice. And here we have another tagged file. Not geotagged, unfortunately, but at least there is a little bit of metadata embedded into it. We can also get files that have mismatched extensions. This is a common way of hiding information on Windows because Windows, unlike every other operating system, is pretty dumb about handling files. The only thing that Windows can do is look at the file extension, and it uses that to determine what kind of file something is. We have various user accounts, recently accessed documents. We'll talk more about these things in future videos as well. Bookmarks, web cookies, things that were downloaded from the web, web history, and search history. So you can see this user searched for GPG download. Here they search for Google Chrome, some DEF CON pics. They did some searches on DEF CON 20, FTK Imager, free games, Castle Wolfenstein, etc. So those are some of the things that you can easily find out using Autopsy. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about deleted files. Now, we briefly mentioned this before, but what happens when you delete a file? The first byte in the directory entry or entries, if it has a long file name, is changed to E5 hex. The clusters are marked as available. In other words, entries in the FATs are changed to zeros. And in some cases, if you have a FAT32 system, the high word of the starting cluster might be zeroed out, which can lead to some complications. So if I want to try and recover my deleted file, there are three basic scenarios that you might face. We'll start with the easiest possible scenario. The easiest possible scenario is a file that lives in only one cluster, ideally not on a FAT32 file system. So if the file size is small enough that it can live inside of a single cluster, you have guaranteed recovery if the cluster has not been reused. If someone recently deleted the file and the cluster wasn't reused for another file, you can probably get it back. Even if it's FAT32, it's still pretty good chance that you can get it back. It's going to be a little bit harder, but not too bad. So that is the best case scenario. A not quite as good a scenario is this. You have a file and it's larger than one cluster, but it's contiguous. It's not fragmented. So it is stored in a sequential bunch of clusters. And of course, ideally, it is not FAT32. So the recovery in this case is pretty likely if the clusters have not been reused, and it's still possible if you have FAT32 and it's zeroed out the high word. Now, we'll talk a little bit later about some ideas on how you might be able to recover the FAT32 situation. But, this is not too bad. So what about the scenario that you really don't want to have? So the scenario you really don't want is a file that's fragmented. If you're extra unlucky, it's not just fragmented, it's also stored on a FAT32 file system, and the high word has been zeroed out for the starting cluster. So here you have to rely on your best guess of cluster allocations. Now, normally, the most common situation is that you have a file. It was allocated originally, probably as a contiguous set of clusters. Perhaps it grew later, and you have another cluster, or hopefully a contiguous group of clusters, and it's fairly simple to figure out where the file is in this case. And why is that? The biggest reason for this is that unless your disk is very full, and depending somewhat on the version of Windows that was ran, it will allocate clusters and it will just keep on going until it gets to the end of the disk. It doesn't tend to go back to pick up unused clusters. Why doesn't it do that? Well, that's about guaranteed to create fragmented files. Remember, we talked about the boot sector for FAT32. And we said the boot sector for FAT32 had an fsinfo block, and in the fsinfo block were two pieces of information: the number of free clusters and the last allocated cluster. Normally, it will try to allocate a cluster just after the last allocated cluster, if it can. So you kind of have to guess, basically. Now, if it is possible, you might have to do some manual intervention, especially if it's FAT32. So you might have to come up with some candidates for a file. If you are guessing at the high word for the file, you might just have to say, well, here's a possibility, here's another possibility. When we haven't talked about some of these issues yet, we will very soon. We'll talk about things like file signatures and what do files look like internally. And using that kind of knowledge, you can say, well, this is more likely the real file than this other one. So how can we try to recover deleted files from a FAT file system? Well, here's one technique. There's different techniques. There are tools out there on the market that you can buy in order to undelete files. This is a decent technique, I think. So the first thing you can do is you can ask the question, is this thing less than one cluster long? If it's not FAT32, check and see if that cluster, the starting cluster, the only one, is marked as unallocated. If it's marked as unallocated, you can reverse that process and put a end of file marker in that position and be done. Now, if it's FAT32, you can scan through the possible clusters and you can look for unallocated cluster and data of the appropriate size. This is another topic we haven't gotten to yet, and we will get to this one soon, but for now, just be aware that when you have a file that does not completely consume a sector, not a cluster, but a sector inside of that cluster, the remaining bytes in the sector past the size of the file, its logical size, if you will be zeroed. Now, if there's more than one cluster, first you want to say, is it not FAT32? If it's not FAT32, and there is a group of unallocated clusters starting at the start cluster that is stored in the directory entry, that's probably my file. So what if it is FAT32? if it is FAT32, I would look for a block of clusters that has the stated or stored cluster low-word, and I would look for that same block of unallocated clusters, and I would also check that the data size matches the last partial sector appropriately. In other words, if there should be 12 extra bytes in that sector, that last one of padding, I should have nothing but zeros in those last 12 bytes. And that would indicate to me that this is likely the right scenario. What if you tried these things and you don't have any luck? Your chances of success are getting a little bit lower. If it's not FAT32, it's still not hopeless. I would look at the starting cluster and search forward for unallocated sectors. As I said previously, if you have a file that's been laid down on a somewhat empty file system, normally the clusters are an increasing function as you go through the file. If the file was recently deleted, this is a pretty good scenario. Of course, if someone has just deleted a whole bunch of files and they were all fragmented, well, you're probably going to be out of luck in that scenario. We will talk about some ways of possibly getting files, even if you have something that dire. I've had a thumb drive that didn't look like a FAT file system, NTFS, or any discernible file system, and yet I was able to get a large number of files for them because the files were mostly contiguous. We'll talk about those sorts of things later in this course. All right, so what if you have the absolute worst case scenario? It is, in fact, FAT32. Here again, I'm going to look for possible solutions, and I'm going to weight them based on solutions with the largest number of contiguous clusters. So whoever has the largest set of contiguous clusters, especially at the beginning of the file, that are unallocated, also not empty. Obviously, if I scan out to the end of my disk, I might have some unused sectors, and those are not what I wanted. Then I will weight it based on that. I might, if I'm trying to write a script, for example, have the user choose, or I might just say, here are a couple of candidates. Let me store them. So this has been kind of a gloomy video, but there is some good news. The good news is that FAT file systems are primarily used for removable media and not for internal hard drives. Because they are used mostly for things like thumb drives, people tend to write things to their thumb drives, and often they don't erase those things, so there's not as much thrashing of that file system. Of course, a internally installed hard drive is going to have a lot more thrashing going on, where files are deleted, new files are created on top of them, etc. The other nice thing is that we will learn that NTFS undeletion is much simpler, and I mean much simpler. You'll be amazed at how simple it is compared to FAT when we get to that in this course. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to continue our discussion of deleted files. So I've already loaded up an image. This one happens to be for a floppy disk. Recall that one of the first things you want to do in ActiveAt is click on your image and select Open in Disk Editor, and that will give you that logical view. So let's have a look at the disk. So I'm going to start by navigating to my root directory, and here I see several file entries. And I see my first entry is a volume label. If I check my attributes, I can see that this is in fact the case. It has that attribute of volume label set. And I see a few other items as well. So if I scroll down, I eventually find some deleted files. So here is my first deleted file. It looks like it used to be called file1.txt. If I look over here, I can see that it has a file size of 45 bytes, and I can see that it has a starting cluster of 832. Now, because this is a FAT12 file system, the high word is not populated. So the fact that this is 0 is not concerning. I can go ahead and click on my hyperlink, and I see it says the secret password for today is blooming. So I'm fairly certain that this is the correct file. Now, other things that I can check. I can check to see if this is in fact 45 bytes long, and it is. If it went through the end of this line, it would have been 48, and I see I have 3 empty bytes, so this is the correct length. Now, if I really wanted to check and make sure that this is the correct file, I could also check the FAT and see if the entry for this cluster was unallocated or not, which I'm not going to do right now. Of course, if I did want to restore this deleted file from this image, I could adjust the FATs. Normally, that's not what we're trying to do, though, in forensics. In forensics, we just want to get the information that was deleted. And of course, one of the basic rules of forensics is don't change the evidence. So we probably wouldn't go back to the FAT and manually rebuild it. So that was an easy one. Let's see if there are any other deleted files in this image. Here I see something that looks like it used to be called new fol or new folder. I see a long file name here. It's been deleted. So once again, I can look at the appropriate cluster. If I look at this cluster, it looks like a directory. How do I know that it's a directory? It starts with dot and dot dot, so that's a good sign. And what is in this directory? Here I see that I have meeting agenda 071715 txt. And I have file1.txt. So let's have a look at this meeting file. I will click on its hyperlink, and I see that sure enough, it looks like I have an agenda. Its file size is 278, and that seems to match with what I have. I'll click back. I can look at file1, and I get back to that same file that was marked as deleted. So that is the super simple case. Let's look at something slightly more complicated. In other words, let's look at something that's FAT32. Now I've opened a new image. As always, I'll go ahead and open it in the disk editor, and let's navigate this image. So let's start by going to the root directory. We'll see if there are any deleted directories. Other than this config MSI directory that was created and deleted multiple times, I don't see anything there. So let's go ahead and we'll just browse this image. I'm going to Documents and Settings. I see there's only one regular user, Joe. And let's have a look in the My Documents folder. And I see there are a couple of files, and I might wonder if there are any deleted files. Well, we can start by getting the cluster number for this directory. So I will inspect the file record, and I can see that the cluster number is 25B2C. So I will go to cluster hex 25B2C, and this is my directory. I will reset my template position and have a look. I see a deleted entry here. Notice that the clusters are all zeroed out. And here is another deleted file, a PowerPoint file. So the first thing I want to check, notice this is a huge file. So if I wanted to recreate this fat cluster chain by hand, it might take me quite a while to do that. But let's start with this. If I click on the hyperlink, I can say, does this look like a PowerPoint file? And in fact, it does. Now we're going to talk more about file signatures very soon when we start moving into file forensics, but I can tell that this is a compressed file because it begins with PK, and if I look into the file, I can tell from things like this right here, where it says presentation XML, that this is in fact a PowerPoint file, a PPTX file. I'm going to click on back. So there's a file that I could possibly recover. Here's another deleted file, and this has a starting cluster. Now this does not look anything like a PowerPoint file. So if I were to look in the FAT, I could tell whether or not this entry is marked as available for this cluster. As a reminder, how do we do that? Let me go ahead and pull up my calculator, and I can see that my cluster number was B, and then here's the low word, 1B. Remember, it's little ending, so you have to reverse the order, D4. That's my cluster. If I multiply that by 4, because it's FAT32, that will give me my offset into my FAT. I can navigate to the FAT, and my FAT begins at offset 4000 in hex. So I can add 4000, and this is my new offset. If I copy that value, I can now say, take me to this offset. My offset is 0x, Control V, and sure enough, I can see that this cluster is being used. The space that was being used for my PowerPoint file is being reused in a new file. I'm going to go ahead and go back to my directory, and we'll have a look at another file. Now this file is not deleted, and here's the entire entry that includes the long file name. This one is deleted, and once again, I can check in the appropriate cluster. If I click here, it takes me to something that does, in fact, look like a presentation. And it tells me right here it is an open document presentation. I'm going to click back, and that makes sense because this is an ODP file. Again, we will talk about these file signatures in some videos that are coming just around the corner. I know we've been talking about FAT for a while, but we're almost done with FAT, and then we will begin talking about something new. Here's a PDF file that was deleted. Here's a file that looks like it was called to-do.docx. Notice that the clusters are all zeroed out here, so there's no way to recover that. And here's one of those cases I warned you about, where we have the high word that has been zeroed out. So if I click on this, it's going to take me somewhere random because I strongly suspect the high order word is not 0 here. So let's see if I'm right. Yeah, this is something that is definitely not a Word document. I'll click back. Another file where the high order word has been zeroed out. Now, if I was going to try to do this manually, I would probably start with a high word of 11 or B. And the only reason I would do that is that files in this directory that are listed earlier had that as the high word for their cluster number. So that might be an indication that I should start looking there. Here I have a deleted text file. It is less than a cluster long. However, this does not appear to be a text file. It appears to be a continuation of what was in the previous cluster. Let me go ahead and go back. And once again, I can verify that this is no longer present by calculating the offset into my FAT and going from there. So my offset is 9. That's my high word, B495. Times 4, it gives me my offset, and I will once again add 4000. And sure enough, you can see that this cluster is being used, and it also appears to be a continuation of what came in the cluster before it. Here again, we have another entry that's been all zeroed out. Let's have a look at one last image. So I've gone ahead and opened a new image, and I see that there are a few nondescript files, and I can also see that this particular directory is stored in cluster 15648. So I'm going to go ahead and go there. Here's my subdirectory. I will set my template correctly, set my template position. I see the dot entries. I see a deleted file here, and it's had all of its entries zeroed out, so that's not really going to help me. I see a second deleted file. This is not a Word document, so in this case, if I wanted to retrieve this file, I would likely have to scan through the different clusters that have this value for a lower, and I will have to select or cycle through various high word values in order to try to find an appropriate cluster. And if I look at all of the files on this file system, I'll notice that all of them have had these values, at least the high word values, zeroed out. And that is often the case when you're dealing with FAT32. So what have we learned in this video? We've learned that it's somewhat easy to identify a deleted file using a tool like ActiveAt Disk Editor. And if you have a FAT12 or a FAT16 file system, it's often pretty easy to get your information back. And if you have a FAT32 file system, it's normally fairly difficult because the high word of the cluster number tends to be zeroed out on you. In some future videos, we'll show you how you can use a little bit of Python and automation in order to make this process easier. But that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about using Python in order to discover and potentially recover deleted files. So I've written a little bit of Python here, and I created a new file. This one's called delfat because we will have a different Python module for dealing with deleted files on NTFS later in this course. It starts out with the usual shebang user bin Python 3. We import some of the usual suspects. We also import our somewhat new directory file that we talked about in a previous video. We've listed out the items that will be imported if you do a from delfat import star, and those are a couple of classes. So the first one is called deleted entry, and here we have something new that we haven't talked about so far, and that is inheritance in Python. So in Python, like many other languages, you can have an object which inherits from or extends another object. So here, a deleted entry is a kind of file entry. So it extends the idea of the file entry we talked about previous video. We have the standard constructor right here. Now here's something new. We are running the base class constructor, the deleted entry constructor, right here. So right here we call super. Super returns the parent object. We run init, the constructor on it, and we pass it buffer and offset. We have added a couple of additional items. FAT32, which is a flag that says I have a FAT32 file system. Now, you'll see later that we could have gotten this information from the VBR, but it didn't seem like a great idea to store this in every single entry just for performance reasons. We also have cluster size. Cluster size is defaulted to 4K. So it's the cluster size in bytes, and we will use that when we're examining an image file later. So we store those two new parameters, FAT32 and cluster size, and that is the constructor. Pretty simple. Now you will see that I have not defined a lot of methods in these classes, and that's because all of the methods that are in the base class are inherited. So all of the things to get out the file names, etc., have been inherited from deleted entry. I created a method called definitely not recoverable. So if you have a hopeless situation, it will tell you there is absolutely no way that this file can be recovered. So what are those situations? Well, first of all, if it's not deleted, you can't recover it. Sorry, you have to delete it first. Also, if it has a long file name, it's not recoverable. Recall that we made the decision to store deleted entries in their own directory entry, their own file entry. And the reason we did that is that it's certainly possible for a file to be deleted and only some of the long file name entries to get repurposed. We then check and say, is it not FAT32 and is the starting cluster 0? So if the starting cluster is 0, then it's definitely not recoverable. It's been completely zeroed out, which occasionally you will see. Why do I check for FAT32? Because it's always possible that you have a FAT32 file system where the upper word is not 0 and the lower word just happens to be 0. So that occasionally will happen, and so you don't want to incorrectly say that something is not recoverable. Also, if the sector is allocated, again, if it's not FAT32 and you don't have to worry about the high word being zeroed out, then you know that it is not recoverable if that sector has already been reused. A final case, if it is in fact FAT32, but that high word hasn't been zeroed, that's what this test does here. It says, is the start cluster greater than 64K? Then, if the cluster is marked as allocated, you know that it's definitely not recoverable. In what situations is it definitely recoverable? It's definitely recoverable if it's less than a cluster long and the cluster is unallocated. If it's not deleted, we'll return false. If it's not FAT32 and the file size is less than a cluster size and that cluster is not allocated, then you should definitely be able to recover it. If it's FAT32 and that high word hasn't been zeroed and the file size is less than a cluster and that starting cluster hasn't been allocated, then you should definitely be able to get your file back. As we said before, this is unlikely, but if that is the case, then you should be able to get your file. And if none of these are true, we return false. Here is another new item. If you define the stir method and someone tries to print your object, it will call this function, if it exists, and get a string and then print that. So here, if you print these, it will just print out del before it prints out the file name. So notice here, once again, I'm using super and calling stir. If I go back to directory, I see that I have a stir method defined here. If it's a long file name, it will print that out and then print out the long file name. Otherwise, it just prints out the short file name. Then I have a method called recover file. Recover file will take an image file name, the offset to the beginning of that partition within the image, a FAT object for checking the allocation status of clusters, a VBR object in order to get information about the partition, such as sectors per cluster, total sectors, etc. I also have a high word guess. Now, what is this used for? In the case of FAT32, I'm going to guess that the high word for the cluster number, if it's been zeroed out, is probably the same as the high word for the cluster of the directory that contains the file. That's a good guess. So I default it to 0. And here I just split my function. If it's definitely not recoverable, I say 0. I return the number of candidates recovered, and that would be none. Here I will call recover file FAT32 if it's FAT32. Otherwise, I call recover file FAT16. So let's have a look at recover file FAT16 first, because it's a little bit simpler. Again, it's simpler because we don't worry about the high word being zeroed out. So here I have a file name I'm going to set it equal to the short file name for my entry. And if it's definitely recoverable, that means it's less than a cluster long, I'm going to open my image file as read-only binary. I will seek to the beginning of my file system plus the offset from the cluster of the starting cluster for my file. I will then read in an entire cluster, and I will then open my new file, writable binary, and then I will write it out. I then return 1, saying I returned 1 candidate file. I do check for definitely not recoverable, even though I should never have gotten here. But just in case someone directly called this method, even though it started with an underscore, which is Python speak, again, for please don't call this directly, I want to double check. I create a candidate cluster chain. I call a little helper method called getCandidateChain. If the length of that chain returned is 0, then I didn't get anything. So in the case of FAT 12 and 16, I can say sorry and I'm done. If I got something, I'm going to, as before, open my image file and then get my output file. And now I'm going to go through this chain. I'm going to start by going to my image. I'm going to seek to the offset to the start of the partition. And then I'm going to get my offset to my cluster in the chain. I'm going to read one cluster, and I'm going to write one cluster at a time to my output file. And once again, I will return 1. Otherwise, I return 0. I got nothing here. We'll come back to the recover FAT32 method. I wanted to first have a look at this get candidate chain. So how does this work? First of all, it determines how many clusters a file requires by taking its file size and dividing it using integer division by cluster size. Now, unless this was exactly a multiple of a cluster long, you probably have to add 1 to the clusters. And that's what we're doing here. We're saying, is the remainder, that's what the percent does, the modulus operator, equal to 0? If it's not equal to 0, then I increment clusters. I then calculate something called RAM slack. We haven't talked about this yet in detail, but RAM slack is the leftover part in the last sector that's been used. And normally this should be filled with zeros. So I can calculate that RAM slack by taking my sector size, 512, minus the file size modulus 512. So this here gives me the part of the sector that's been used. I start with the total sector size here, 512, and then when I subtract, I get the RAM slack. File slack is the number of sectors that are not being used by the file. So these are leftover sectors, whole sectors. And a very similar calculation here. I start with my cluster size and I subtract my file size, modulus, the cluster size. That integer division of 512 gives me how many whole clusters I have. I then create an empty list, candidate chain, and I say if this start cluster is allocated, then I'm going to return this empty list. So notice here I've used the modulus operator again on 64K, and I add the high word times 64K. Now, the high word should always be set to 0 when I'm doing FAT 12 or 16, and if you look at the recover file method, you'll notice that is the case. I set the number of found clusters equal to 0. Once again, I will check here and say if it's not FAT32, or if it's FAT32 and the start cluster has a high word that's not zeroed, then for I in the range of starting cluster to total sectors divided by sectors per cluster, so from here to the end of the drive, If my cluster is not allocated, I add it to the candidate chain and increment the number of found clusters. If my found clusters is greater than or equal to the number of the clusters in the file, I break out of my loop here. At the end, I return my candidate chain. So if we've made it this far, this is for FAT32. So I say for I in the range of starting cluster plus 64K times the high word to total sectors divided by sectors per cluster. If the FAT is not allocated again, so if this cluster is not allocated, once again, I'll add it to the chain, increment found clusters. Now, if found clusters is greater than or equal to clusters, I'm going to do another check. I'm going to say, open the file, and for every cluster in this candidate chain, I'm going to seek to that cluster. So again, I have the offset to the start of my file system plus the offset to that cluster, and I'm going to read that cluster. If the entire cluster is empty, it's all zeros, then I'm going to return an empty list. If I made it this far, now I'm going to look and I'm going to see to the start of my file system plus the offset to a cluster. Well, what cluster is that? It is the candidate chain, the last entry, which is the number of clusters, minus 1 is the index because we start at 0. That cluster plus 1. So I want to start at the very next cluster. Then I want to subtract 512, the sector size, times my file slack, and then subtract my RAM slack. And I want to read that RAM slack, and if it's not all equal to zeros, then I'm going to return an empty list. Otherwise, I'm going to return my candidate chain. If we go back to our recovery for FAT32, this one is just slightly more complicated. We first do a quick check to say, is it definitely recoverable? And if it is, then we get the one cluster as before, and we write it out, and we return 1. If it's definitely not recoverable, then we're going to return 0 as before. Otherwise, we're going to call get candidate chain. Now we're going to start with our high word guess. The high word guess is passed in as the high word for the cluster of the containing directory. So we're going to start there. And we're going to look as before, and we're going to say, is the length of my chain greater than 0? If it is, I will open my image file, open my output file, and I will go ahead and go through the cluster chain and read and then write cluster and return 1. Now, if it wasn't my high word that I guessed, the next most likely option is that it was that number plus 1. So I call get candidate chain again, and this time I say high word guess plus 1. I have the same logic as before, and if that didn't work, now I'm getting kind of desperate. So here I'm going to have to cycle through the different high words. So I say for I in the range 0 to total sectors divided by sectors per cluster divided by 64K, I want to get my candidate chain, and here I'm going to pass it I, my high word, which I'm iterating over. And if the length of the chain is greater than 0, that means I got something. I increment my candidates, I open my image file, and then I will open my output file, and I will add candidates to the end of the name, and I will read in a cluster and write out a cluster as before. And then I return the number of candidates. So that is our file recovery. I also created a new class called deleted list that is based on directory. Here, the init, the constructor, is a bit different because I don't actually call the directory constructor. I create a file entry, then I check and say, is this a deleted entry? If it is, I will create a deleted entry from it and add it to my list, and then I skip to the next file. And that's it. Everything else in that class is defined in the base class. Here I have a usage statement. Looks very similar to what we had before, but this little test script that I wrote takes an image file and a cluster number. It looks at the directory with a given cluster number, and then it's going to print out some information. So here I've just added to my previous main method. I get the directory, and then I create a deleted list from that directory. Then I iterate over the entries in that directory. I first print them out, and then if it has a short file name, I will print out whether or not it's definitely not recoverable or definitely recoverable, and then I will attempt to recover the file. So it's pretty simple, and this will likely recover a pretty good quantity of files that are recoverable. So let's go ahead and try to run this. So let's start out with our root directory. Now we see there are quite a few files. Were any of them definitely recoverable or not recoverable? And the answer was no. Now, this is not surprising because this is, of course, a FAT32 file system. Now, I do see that there were a couple of files that were recovered by this script. And I know that these were recovered by this script because they started with underscore. Recall that deleted files, we started all of them with underscore as the first character because the E5 character would cause some problems. It's not easily printable in some situations. I'm going to rerun this file on a subdirectory, and we'll try another subdirectory. And notice here it said that this particular entry was definitely not recoverable. So let's have a look at this .doc file, and I can see that this is in fact a Word document. I can tell because it starts out with docf11e0 or docfilio, which we'll talk about this really soon when we start talking about file signatures. But this shows me that yes, in fact, this is a Word document. Here's another temp file. This one looks like a executable file. And this, in fact, looks like a directory. Recall that we had a bunch of config MSI directories, and this is one of those. Of course, we've only scratched the surface here, and I'm just trying to give you some ideas on how you could pretty easily use some Python to recover these files. There are lots and lots of utilities out there as well for undeleting files on FAT file systems, but that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to start a new section, and we're going to talk a little bit about file forensics. So what is file forensics? Anyway, it is looking at individual files. So far, we've talked for quite a while about the FAT file system and how it's organized, and now we're going to start looking into the individual files. Now, this information, these techniques that we're going to discuss, can be used to find hidden information, including things that are hidden in mismatched file extensions. So in the Windows system, Windows is pretty dumb about handling files. If you use something like Linux or OS X, it knows what a file is by looking at the file itself, whereas Windows is not so smart. So it relies completely on the file extension to determine what kind of a file something is. And I can just change the file extension and it will appear as though a file is corrupted. And this is a very common way of hiding information. We can also see things that are hidden in slack space. We'll talk a little bit later about what that means. And unallocated space. There might be unallocated space on your partition. You can also have unallocated sectors on a drive. We have page or swap files. So you might find information that is stored inside of those. Primarily, we are going to rely on file signatures. Now, many files have standard headers. The exception to this rule would be standard text files. Now, if the entire world used nothing but text files, it would be super easy to be a forensics person because there are all kinds of tools for searching through text, etc., that you could use. Some of these files also have standard footers, and that can be useful as well when you're trying to look at these files and figure out what they are. So what good are file signatures? Well, they help you do a few things. Identify mismatched extensions. They help you retrieve files from swap and memory. And it also can help you, if you undelete a file, you can verify that your undeletion was correct if you know what the file should look like internally. Gary Kessler has a really nice list, and it is at the URL given. We also have slack space, that leftover space in a cluster when the file size is not an exact multiple of a cluster size. Now we break this up into two different categories. One of them is called RAM slack, and that is a partial sector of slack. So there will be usually a sector that's only partly used, and what remains in that sector is called RAM slack. Any full sectors of slack are called file slack. Now, to calculate the total slack, we need to first calculate what percentage of the cluster, the last cluster, is being used, and that is just this, the file size modulus the cluster size. That gives us the part of that cluster that's being used. We said that slack space was the unused portion, so we just take our cluster size and we subtract the total space used in the last cluster. A little bit more about RAM slack. RAM slack gets its name because a long time ago, this is what followed your file. So if you have some data in memory and you needed 512 bytes to write to a sector, if there was any additional bytes that came right after your data, that just got written to disk. Now, pretty quickly, they figured out that this was a really bad idea when it comes to security because you were randomly writing memory items to the disk. So you're permanently storing who knows what. Who knows what could be passwords, it could be confidential data, it could be virtually anything. So today, it should all be zeroed out. And how long have we been smart enough to zero this out? I would say approximately 20 years. So if today you see anything in this RAM slack, you should be very suspicious. So if I want to look at the last sector, just as I calculated the used portion for my total slack, I just take my file size modulus 512, and that will give me my used portion. To get my slack space, I start with my sector size and I subtract the used space. File slack. File slack are those whole sectors, and why do we care about file slack? Well, file slack can contain fragments of old files. So we said that we zero out the RAM slack, but we do not zero out the file slack. How do you calculate the file slack? Well, it's the total slack integer division with 512, and that will give you the file slack in sectors. So if we substitute in our value for the total slack, cluster size minus file size modulus the cluster size, we take that entire quantity and we do an integer division with 512. We should get the file slack. One last thing I wanted to mention. We have something called file carving. Now this is used to find files in swap space, unallocated clusters within a partition, or unallocated disk space, space that's not inside of any partition. There are a couple of general carving tools out there that are pretty popular. One of them is called Foremost, and there's another tool called Scalpel. And we'll show you how to use some of these tools in future videos. There are also some specialized tools. So if I have a particular file type, for example, a video file, I might only have fragments of that video file. If we look at slack space, we said that file slack can contain fragments of things. So it makes sense that we would want a tool that could take those fragments of video and put them back together into a reconstructed video file. So that's one example of many specialized carving tools that exist. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about file signatures. So what I've done is I've gone ahead and opened up a disk image, and I'm going to browse into it. I see there's a user Joe, and he has some files. He has a My Documents folder. So I wanted to look at his My Documents folder and just look at some of these different files and see if they are what they claim to be. So we'll start with this file that claims to be a docx file. So this is an XML-based format. Now, one thing I will say, a lot of the Office documents, and that's not just Microsoft Office, that's also LibreOffice, are moving toward an XML-based format. And because it's very wordy, what they do is they compress it. So you will see a compressed file, and if you look inside of it, it will be XML. So I will look at this file. Now I can either ask to preview the file, or I can open it in the disk editor. So if I say I would like to preview the file, it will pull up preview like this. If I say open in the disk editor, it'll bring up the full file. So preview, if it's an image or something that's recognized, it might bring up the image. Otherwise, it's going to show you the first sector. So the question is this a docx file? And the answer is, it is not. We talked in a previous video how you can look up the different file signatures at Gary Kessler's website. And this is %PDF dash, then a number, and then a %. So this is the standard header for an Adobe PDF file. And of course, you could verify this, if you don't believe me, by going to that website. This particular file format also has a footer. So if I go to the end of this file, I should be able to see the footer, which is %EOF. Now, because of the resolution that I'm showing you this video in, it's not cooperating with me, and it's just past the bottom of the screen. But trust me, it's actually there. So that is one file. Let's look at some other files here on this file system. Here's a file called buddy.doc. If I click on preview, I can see how it starts out. Now in this one, I'll go ahead and open it in our disk editor, and I see that it says DOCF11E0, or docfilio. It then is followed by A1, B1, 1A, E1. Now, often you'll hear people say that this is an Office document. That's not technically correct. There could be some other document types, but this is an OLE document. It's got object linking and embedding, and it is a Microsoft format for such files. Just happens to be what they use for the old Office documents. Now, if it starts with docfilio, you know that it's some kind of Office document, but you don't know which one. And one of the easiest ways to find this out is normally, if you go through the file, in particular, if you go toward the end, you will see some information that will tell you about the file. So, for example, here I have workbook, root entry. So if I have a workbook, that sounds like something related to Excel and not Word. Here you can see it says Excel links, and there's some other text in here that leads me to believe that this is actually an Excel document. Now here's another clue. If you're wondering what kind of a document it is, you might say, well, how can I tell? You don't really need to know what kind of a document it is if you're running Linux. And we'll talk more about this later. But one of the things that you can do is open it in LibreOffice, and it doesn't matter what kind of Office document it is, it'll just open it. Unlike Microsoft Office, that won't open something with the wrong extension. So another advantage to using Linux. So far, this user has been hiding a few things. Let's have a look at this bitmap file. If I click on Preview, it shows me a bitmap. So what does it look like inside? If I open it in my disk editor, sure enough, it starts out with BM for bitmap, F, and then we have other data inside. And that's a bitmap file. Here we have something that claims to be a PDF file. If I preview it, I see that it starts out with the appropriate header, %PDF-1.2 period %. So this, in fact, looks like a PDF. Once again, if I open it in my disk editor, I can see that it looks to be an actual PDF file. Another clue is that you will see lots of text. So Adobe likes their % signs, as I like to say. So if you look inside of a PDF file, you will see a lot of things that have percents in front of them. This file, mystery JPEG. Is it a JPEG or not? Well, I did a preview and it didn't show the JPEG, but that doesn't mean that it's not actually a JPEG. I'll open this in the disk editor, and this has an interesting header. There are different kinds of JPEGs out there. There's 3 different kinds of JPEG files. There are 2 that are much more common than the others. So I'm going to go ahead and bring up Gary Kessler's site, and here we can see 3 different kinds of JPEGs. They all start with FFD8, FF, and then the next byte will vary. You'll either have E0, 2 bytes that represent a size, and then JFIF. So here's what the ASCII looks like, and here is the actual hex. So you'll have JFIF and then a null. The other common one has FFD8, FFE1, once again 2 bytes for a size, and then EXIF. Recall that EXIF is used to store additional information inside of a JPEG. So things such as the camera that was used, the date, possibly the location, etc. So these are the 2 most common formats, and we'll show you how you can find these later using a tool such as ActiveAt. And here we have the uncommon format that starts out FFD8, FFE8, then 2 bytes, and then SPIF, the still picture interchange file format. Generally speaking, with the 2 common formats, a JFIF is produced by something like Photoshop. An EXIF is a raw photo from your digital camera. That's not strictly true, but that is kind of the general rule when it comes to JPEGs. So back to our file, we can see there's a couple of bits of EXIF information, and of course there are various tools for extracting this. So that is a JPEG. Notice that all 3 of these also have a trailer of FFD9. Here's something else that claims to be a doc file. It does start out as docfilio. Let's open it in our disk editor. I will go down toward the end once again. I see document summary information. I see Word document. And if this is an actual Word document, I would expect to see quite a bit of text, and that is in fact what I do see here. There's a file called Nothing to See Here. It starts out with PK. PK means it's a zipped file. As I said, there's a move toward using XML files, which are always compressed because they would be way too huge. So for a compressed file, you can look at the very start, and you can also look at the end to get some ideas what it really is. Now, of course, I could extract this file and unzip it, and that's another way that you could go. But you usually don't have to do that. So here I see it starts with PK. it is a zip file. And then I see that it says MIME type application, and then it says open document text. So I know right away that this is really an ODT file. Other ways I can tell, if I go to the end, you will see some configuration information, various settings, etc. So ODT files and all of the open document format files are actually pretty easy to see what they are. This one is called nothing.dat, so it could be practically anything. Now, in this case, it's a compressed file of some sort. I can tell because it starts with PK. And let's have a look. I see PK and I see it says SigeWin1 DLL. Let's look at the end and see if we can get a better idea. So if you look at the end of a zip file, why are we looking at the end? We're trying to see some of the manifest information, the listing of what is inside this file. So here you can see repeated references to RIFIUT and then some things under that directory. So this is actually a utility for recovering files. A little later, we might get into what kind of files those are. But this is a forensic utility that has been zipped up. This is supposed to be a GIF file, and it appears as though it might be. At least it's an image file. So let's have a look. If I open it in my editor, sure enough, it starts out with GIF, G-I-F, and then there will be a version number, either 87A or 89. Because this is a really old format. So it's either the 1987 version or the 1989 version. And that's a GIF file. Here we have something else that claims to be a PDF. And I say it's not because it doesn't start with the correct header. If I click on Open in Disk Editor, I see it says FFD8FFE0. Then we have 2 bytes for some size information, and then JFIF, followed by a null. So this is one of the 2 most common forms of a JPEG. Notice that I have the string Adobe in here. So we said that this form is the one that you get most often when someone has edited a picture inside of something like Photoshop, which is of course made by Adobe. Here's something that claims to be a JPEG, and it actually is. It looks like an extremely handsome man giving a presentation in southern India. Just a guess, though. So if I open it in my disk editor, I see that it was a graphic, but it in fact is not a JPEG. This is a PNG, a portable network graphic file. So once again, this is an attempt to confuse people by giving it the wrong extension, and in the case of Windows, you'll be successful because Windows won't handle this properly. You know, a Linux system would just open this file. Here is a new format, PowerPoint. If I preview it, I can see that it is some sort of compressed file. I'll go ahead and open it in the disk editor, and we said that often you want to zip to the end. Now in this case, I can see right away there is a file inside of it called presentation XML. That's a good sign. If I go to the end, I see things under a PPT directory, slide masters, lots of XML files, PPT theme, PPT media image, etc. So this is most definitely a new format PowerPoint file. This is a text file, and it is, in fact, a text file. Here's a file that says safe to run. I'll preview it, and it looks correct. I don't know that it's safe to run, but it does look like an executable. Well, how can I say that? Microsoft executables start with MZ, which are initials for the guy that created this format. But, forget that guy. Here's how you can remember it. This is a Microsoft executable file. So it will start with MZ. Now, what comes next will vary depending on the file. This one says this program must be run under Win32. So this format is the same when it comes to DOS programs, Windows programs, etc. They all start with MZ. So this program, if you tried to run it under DOS, would immediately give you this error. Or if you tried to run it under a version of Windows, a really old one that was 16-bit, not a 32-bit version. So those are executable files. And these are not just executable files. These are also DLLs and Microsoft installation files. Here I have another file, secret, ODT, and this, in fact, is an ODT file. Once again, I can see it starts with PK, and it has, right at the start, open document text. What about this file? This file claims to be a PDF file. It clearly is not that. So what is it? Well, if you've confronted with something and you don't know what it is, you can try to go to Gary's website. And we'll do a search for FTYP, and I see various kinds of media files. And this one was FTYP ISOM. So I had FTP ISOM, etc. And here I see the string MP4, and then I see H264, MPEG-4. So that's a codec. So this apparently is a movie. It's an MP4 video file. Finally, let's have a look at this file. This one claims to be a docx. It's at least a compressed file. So let's see what's inside of it. Starts with PK. We go to the end, and I see Word, and then a bunch of things under Word. So yes, in fact, this is a Word document. So there you have it. There's an introduction to file signatures, and you can see that it's pretty easy to use file signatures to figure out what kind of files things really are. Of course, we can do some scripting to automate this if we'd like. You can also do some fun things with active at, such as search for a particular kind of file. So let me show you how you can do that. I'm going to go ahead and open this in a disk editor, and now I'm going to use find, and I am going to find the string %PDF. And I'm going to search from the beginning of each block. I'm going to click on Find All, and it's off and searching. I'm going to go ahead and stop it. And down here, you can see my find results. So here's a PDF file, here's another one, and here's another. So it's pretty easy to do. And that's just one example. Of course, you could use any of the other headers instead for your search. I can search for hex, so I can actually search for JPEGs with FF, D8, FF, and let's say I want to search for the ones that go E0 next, or I could just search on these first 3 bytes as well. And here you can see some of my results. So that's some pretty simple stuff you can do with file signatures inside of ActiveAt. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to talk about using some standard Linux tools in order to do file forensics. So we'll start by mounting an image using a script we developed earlier. So we've now mounted our image, and you'll notice it's automatically brought up my file browser here in Linux, and I can see all of the different files. Now, I'm certainly am free to just browse around. I see one user, Joe. I can look at his My Documents folder and see what's there. Now, as we said before, Linux is much smarter in how it handles files than Windows. So it does not care what the extension is. It will automatically open the correct application for your file. How is it able to do this? Well, one way that it's able to do this is that it has a utility, the file utility, which is built on top of a library that is built into Linux. And this is the file utility. So let me go ahead and give you an example. Here I'm in the Joe Users My Documents folder. I can see what's in the folder, and I can run the file command. It's very easy. I can say file, book, docx, and it says this is actually a PDF version 1.6. So it doesn't just tell me what it is, it tells me exactly what it is. Even gave me the version. So obviously this is a lot simpler than going into Active at or some other disk editor and manually opening each of the sectors as we've done before. Of course, if it's a deleted file, it's not going to automatically show up this way. So there is a downside to that. But we've seen in other videos how you could easily extract a deleted file and then you could use the file utility on the extracted file. I can do this command on an entire directory. And here you see the level of detail that I will get. So let's walk through these really quickly. We've done this before in a previous video, and there we looked at just the file type. So notice right here, I have something that claims to be a docx, and it's a PDF. Something that claims to be a doc file, and it comes up with composite document file version 2 document, little indent, etc. That is the docfilio header that we talked about. Here, notice it says name of creating application, Microsoft Excel, and it also gives you other information such as when was it last printed, and so on. We have a desktop INI file, which is an ASCII text file with carriage return line feed line terminators. That is the standard for DOS and Windows. Everyone else uses just a new line. Downloads is a directory. This gray BMP is in fact a bitmap file, and it tells you the format and the size. Here's another PDF. This one is version 1.2. Mystery JPEG is in fact a JPEG, and it uses the JFIF standard. Another Office document. This one's a .doc file, and this one has the correct extension. It was created by Word. Nothing.dat is a zip file. Nothing to see here, ODT, is in fact an open document text file. A GIF file is a GIF. However, the PDF is a JPEG. The JPEG is a PNG file, and the PowerPoint file is a zip archive. This is in fact a text file. This exe is a portable executable 32-bit. That's what PE32 means. It's saying it's a GUI executable for Windows. This PDF file is in fact an MPEG-4. This last document file is a Microsoft Word document. So you can see very easily I can get lots of information from this utility. What if I wanted to get a list of a whole bunch of these files? What could I do? Well, I could certainly go to each directory and run file star. That might become a little bit tedious. What could I do instead? Well, I could always write a little simple script. That's an option. Now, normally you can use a for loop in a bash script in order to very simply get a list of files and do something to them. Unfortunately, that's not so easy to do in the case of Windows files, in particular because people tend to put spaces in the files, and that has a tendency to kind of mess you up a little bit. So one solution to the issue of having spaces in file names is to use the find command. Now, the find command is a great utility for finding things. Its syntax is find and then a starting directory. We can use dot for the current directory, and by default, it will just print out the names of the files it found. So if I just hit enter here, it will print out all of the file names. Now I want to print out all of these file names, but instead of putting them on separate lines, I will print nulls at the end of each. So I will use -print0 for please put a null, which is not easily displayed here in my terminal. And I will take these results and I will send them using my standard Linux philosophy and Unix philosophy of combining multiple utilities together. I will send this to a while loop that says read from standard input using a delimiter of a null. That's what $, and then in single quotes \0 will give me. I will call this file. That's what each of the items passed into my while loop from find will be called as I iterate over this loop. I will do the following. I will run the file command on $file. I close the while loop with done. Now you can see that my file named nothing to see here, ODT, was handled properly. Now you might say, so what? That's not a big deal at all. And you're right. If you're only going to look at a certain directory, you could certainly just change to that directory and be done with it. However, I can take my little one-line script and do this. I can go to the very top level directory. I will bring up my little one-liner in my command history. And now I am running this command on every single file in this image. I'm going to go ahead and stop that because that might take a little while to run. But here is where it gets to be a little bit more interesting. Now, I'm going to, for sake of time, change to the Documents and Settings folder. And I'm going to rerun this command. And I'm going to pipe this to yet another command. And that command is grep. Now, grep is the GNU, that's GNU, which stands for GNU is not Unix. Regular expression parser, also known as grep. So I can say grep. Now, a regular expression is a matching pattern. We will talk a little bit more about regular expressions later. For now, we're going to have the absolute simplest regular expression, a literal string. I'm going to say, take all these results and only print out JPEGs. So what this should do is this should give me a list of all the JPEG files inside of the Documents and Settings folder. So all the users' JPEGs will be printed out. So we can see this ran fairly quickly. Of course, if I was doing an investigation and there was a reason I wanted to see all of the different JPEG files, I could capture this information inside of a text file of some sort. And that's pretty easy to do. How do you do that? You just redirect it, just like you would do with Windows. So I can say greater than, and then I can give it a file name. And that would give me a list of all of those files. If I wanted to append to a file, I can use double greater than. Another nice thing I can do in Linux is that I can pipe it to a program called T. T will T it so that it goes to the standard output and to a file. So I'm going to use T. Please send this to the standard output and to this file. // that's my home directory. I'll just say jpegs.txt. And there you have it. It's already done. And that will tell me which of these has a JPEG inside of it or not. I could very easily use this to check for a mismatched file extension. I could say, does the file extension match JPG or JPEG, which are the two common ones? And if not, I could print out a little warning, or I could easily create a script that would search for only one of those things. So if I wanted to know how many of these I found, there's easy ways to do that as well. One of them is to use WC. WC is a word counter, and it will also count lines. So I will count just the lines. I'll use WC-L, and then I'll give it this file name, JPEGs TXT. And it tells me there were 283 lines in that file. So that's how many JPEGs were found. I can repeat my search. This time I can look for PNG files. I'll send this to PNGs. Once again, I can count them. And there were 240 of them. If I want to find Word documents, you can see that there were only a couple of those that were found. So there are just a few very simple things you can do with the file utility, which again is built into Linux, so there's no need to install anything. You just have to mount your image, and you can very easily tell exactly what kind of file everything is. You can, of course, use the graphical file browser to browse around, as you might want to do initially at least as well. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to show you a very simple shell script that you can use in order to detect mismatched file extensions. Now, you might ask the question, why a shell script? And that's a legitimate question. The reason for a shell script and not a Python script is pretty simple. The file utility that we showed you in a previous video is very powerful, and it is true that you could use the same library in Python, but why? Why would you want to go through all of that work? So I'm going to show you a very simple shell script that you can use in order to detect mismatched extensions. Just like our Python scripts, we start out with shebang, in this case bin bash, and then we go through the various files and we use the find command. Find will search through a given directory in all subdirectories for a file. Now it has a whole bunch of flags. I recommend you look at the help screen for find. Look at the man page, and you will see it has quite a few options. So let's go ahead and let's just do a very simple help on find. Then you will see there are all kinds of options for what are you looking for, how deep do you want to go. You can search based on name, etc. The default behavior is just to print the name, and we're going to print the name with a null at the end. We've done similar things before. And we're going to take that output and pipe it to while that will read this input that's being piped to it using a delimiter of a null, and everything that it gets, it will put into file. Here we have a little do loop. Now this might look familiar because we did something similar in our one-liner. We just kind of expanded it a little bit here. So here I'm taking the response from this command, file, and then the file name. Now why did I quote the file name? I quoted the file name because Windows files tend to have spaces in them, and the quotes fix this problem. In general, if you have a command in bash and you enclose it inside of parentheses preceded by a $, it will run that command and return the results, which you can then set equal to some shell variable. Here, I will get just the file name from the complete file name, including path, and I'm going to use this command, base name. So base name will return just the file, not the directory leading up to it. Once I have the file name, I do this little trick to get the extension. I have the file name, which is in my variable file name. Now, in general, I can use $file name, $file as I've done. The more safe way to do this is to enclose those variable names inside curly brackets. When I enclose my names in curly brackets, there are certain transformations that I can do. And this combination, 2 hash signs, star, dot, will give me any file extension. So this strips the file extension off of that, and then I check for a mismatch. So how do I do that? I use an if statement inside of bash. So in bash, I can have a test, and the test is normally included inside of single square brackets. One thing I should warn you about with shell scripts, spacing is important. So having this white space between brackets and my tests is required. You can't just smash everything together in shell scripting and expect it to work. So here I'm doing a comparison. I'm comparing the extension that is changed to uppercase. That's what these 2 carets do. They say, please give me uppercase. Is it PNG? Does this thing claim to be a PNG file? If that's true, then, now you might wonder why I have the semicolon. Remember when we did our one-liner, we said that if you threw a semicolon in, it would say, go to the next line, but I don't want to hit return here. And this just allows this to be a little more compact. Otherwise, I would have to put then on the next line. So here, I'm going to do a second test. Now this one, I have the double square brackets. So this is a bash condition. So this is an extended condition. It is not just a standard shell test. Standard shell tests are things like, does this file exist? Does this string equal this string? So this is an extension that is available in bash. And I'm saying if this condition is not true, well, what's the condition? I want to look through my response, and I'm searching for this string. I'm searching for the string PNG image. This syntax might be familiar to some of you if you've used things like Perl, but this will do a regular expression search within this. So if I search for PNG image in the response from file, and I don't find it, then there's a problem. There was a mismatch. It will print out a message, and then it will give me the response, which will tell me exactly what that file really is. And this is pretty much this entire script. I check for JPG. That should be reported as a JPEG image. I also check for JPEG. Now, it certainly is true that I could have combined these 2 conditions together. I chose not to because my philosophy is that it is better to have very simple, straightforward scripts than to have ones that are perhaps slightly more efficient but harder to understand and read. Check for GIFs, check for MP4s, PDFs, and then it gets a little different when you start talking about doc files. A doc file, recall, should start with docfilio, which is a marker for composite document file. Now, depending on the exact version of Word that was used, it will come up and say composite document file, and it will say that it was created by Word, or sometimes it will say Microsoft WinWord file. So here I check for the most common one first, the docfilio. If that's not the case, then I check for the less common situation. The docx is a little bit simpler. It will come up with a string Microsoft Word 2007 plus. The Excel files, very similar, and PowerPoint also is pretty much the same thing. So one last check that I do here is for an executable. It should be reported as some kind of an executable. Otherwise, it's mismatched. Are there other extensions that you could test? Certainly there are. This is very easy to add to. Maybe you decide that you would like to do another file, like maybe MP3 files. All you need to do is figure out what those are reported as by file and then just add another clause. So I'll go ahead and I'll just show you how easy this is. I will add MP3. So if you want to expand this, just copy a section, paste it. This is MP3. Now, this will be reported as an MPEG. Normally, it will be reported something like MPEG, and then some sort of encoding layer, usually layer 3, version, a bit rate, whether or not it's mono or stereo, etc. So that's an MP3 file. So I'll go ahead and save this, and let's try this. So I've already mounted my image, and I'm just going to search in the documents folders. So I'll do a quick ls for media part 1, and you can see it has documents and settings and some other folders. So this looks like a Windows XP installation. So here's documents and settings. It looks like I have one user, Joe, and a default user as normal. So I'm going to go ahead and run my script, extension mismatch, and I will give it that directory. And off it goes. It's already done. Notice it did find some mismatched files. This docx file is really PDF. This PDF is really a JPEG. This JPEG is really a PNG. This PowerPoint is really a zip file. This PDF is really an MPEG-4. And that's it. That's all that were found on that file system. So here we have an answer just in a couple of seconds using a very simple shell script. One thing I should point out, we talked about file signatures before, and we said that a lot of these new formats, the XML-based formats, are compressed. So they're going to start out with PK. So it's great to use the file utility because the file utility said, well, maybe someone tried to hide something here. If you just looked at it quickly, you'd say PK, okay, that's what I should have for a PPTX file. But in this case, it was bogus. It was just a regular zip file that was hiding there. So there you have it. Some very simple things that you can do with a few lines of straightforward shell scripting in order to find mismatched extensions. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Windows Forensics here at Pen Tester Academy. In this video, we're going to continue our discussion of file forensics, and we're going to discuss a short Python script that you can use in order to find different kinds of files inside of an image file. So here I have my script. It starts out with the normal shebang. Now this one is a little bit different. And what's different about it? Here I'm running Python 2. Why Python 2? Well, some libraries are not yet ported to Python 3. One of those libraries is the Magic library that we used when we used the file utility. So this is built on top of a library that has a database of different kinds of files in Linux, and this particular one is not ported to Python 3 just yet. So we're stuck with Python 2 in this script. So I import this file. Incidentally, you can run this on Windows. However, it has a lot of dependencies. So you will have to install a bunch of files first because Windows does not have native support for this library. I'm also introducing something new, OptParse. OptParse allows you to easily parse command line options, and we will use the regular expression library. We also import the OS library in order to find out whether or not a file exists. So how does this script start out? We start out by defining a class. And this class is called FileFinder, and this is going to be a base class. It defines two methods. That's it. It defines one called matches. Matches will return true if a buffer that you've passed into it contains the desired file type. It also has a file type method that will tell you what kind of a thing this class will match. I then define a bunch of Finder classes. So here's the first one, JPEG Finder. It inherits from File Finder. So in Python, if you inherit, that means you will have the same methods. So it has those two methods, which I will, of course, override. To check for a match for a JPEG, I receive the buffer, and I will call this method in Magic that is called FromBuffer. There is another method called FromFile that you can use to determine if a given file with a certain file name is of a certain type. But here we are dealing with a file system image. I then do a regular expression search. Now you can get some more information about Python and regular expressions. One thing you will find is that there are two ways to look for things with regular expressions. There is a method called search and another one called match. Match only matches the start of a string. In our case, we want to match anywhere in this string. So if it is a JPEG file, the Magic library will return a string that contains JPEG image data and some additional information. So if JPEG image was found in the results, which I called mag, it returns true. Otherwise, it returns false. File type will return JPEG. So if you say, what sort of a thing will this file match? The answer is a JPEG. I define similar finders for PNG, GIF, bitmap, and some other types. I also defined a generic image finder, and it contains a list of image finders. So one for JPEG, one for PNG, GIF, and bitmap. Its matches method will cycle through all of these, and if any of them returns true, it will return true. Otherwise, it returns false. There was no match. And its type is image. Similarly, I define a PDF finder, an executable finder. It will say PE32 executable or some other kind of executable, if that's what it is. A zip finder, it will return the fact that this is some sort of archive. Now, I could have been more specific and said only a zip file, not some other kind of archive. And I thought most people, if you're looking for a zip, you probably just want any kind of compressed file. And then we have some Office document finders. Here we have PowerPoint. We have the DocFilio, the old school PowerPoint, or the new school PowerPoint. For a Word document, we have something similar, but there is a third possibility where it will say Microsoft WinWord. Excel is similar to PowerPoint. It has two options. And I also defined a generic Office document finder, which will return true on a DocFilio or a PowerPoint, Word, or Excel file. And it says I'm looking for Office files. This brings us to our main method. Our main method will first set up an option parser. So here I create a parser and I set it equal to optparse dot option parser. And in the constructor for option parser, you can give it a usage statement. So here's my usage statement. Usage is %prog. This will be the name of your script will be substituted. And then here's my list of possibilities. I can give it a search list, cluster size, image file, and an offset. I then use add option to tell my parser about each of the options I have available. Each of them have a short form and a long form, a destination, where are the values stored, and a help string. The option parser uses all of these in order to set some variables and also to provide help if the user requests it. Here we have cluster. This is a cluster size in sectors, in case I want to search through multiple sectors at a time. This should, in theory, speed up the search. However, you need to ensure that you are on the proper sector boundaries. You don't want to be one sector off and searching cluster by cluster for files. You have the image file. Just give it a name. The image file should, of course, be in RAW format. And you can also give it an offset. You don't want to start searching from the MBR at the start of the disk. You can start at the beginning of a partition. Once that's all set up, I call parser parse args, and this will return a tuple of options and args. My image file name should be found in options.imagefile. That's the name I gave it right here. And I will do a couple of checks. If this offset was passed in, then I will set the offset to whatever you passed as a string, converting it to an integer. Otherwise, that offset is going to be 0. I will start at the beginning. Cluster size, if that exists, I will set it. If you didn't give me a cluster size, I will go with 1. I will search each sector one at a time. Then I will take the search options and split them up. So for the search options, you have -s and then a comma separated list of the kinds of files you would like to search for. So I use split and I say, please split the string on commas. This gives me a tuple, a list of items back. I use that to initialize find list. I create an empty list called finders, and then I iterate over find list, and I check each item, and I say, is it JPEG or JPG? If it is, append a JPEG finder to my list of finders. I check that for PNG, GIF, bitmap, image, PDF, etc. Then I check if the file exists. If not, I display a message and I exit. If I've gotten this far, I should be good to go. I set a variable position equal to the offset, and then I'm going to open my file. I use the with construct that we've seen before. Say with open my image file as a read-only binary file, and the variable for the open file will be called F. I then seek to my position times 512. I read in a cluster, so I read in 512 times cluster size bytes. While I got something, while the length of that buffer is greater than 0, I will keep going and I will ask, is there one of the files that I'm looking for in this cluster? So I do this by iterating over my finders with a for loop. I say for finder in my list of finders. If the finder matches my buffer, then I will print a message. The message I will print is matching, and then %s is a placeholder for a string. So this is an example of a formatted string. So I have matching, and then a string goes in this placeholder found at offset 0x %x. This is another placeholder, this one for a hexadecimal value, sector %d. That is a placeholder for a decimal integer. I then have the % operator followed by this tuple. So file type gets substituted into the first position. My position gets substituted in for this placeholder, and it will be displayed as hex with any letters in uppercase because I have a capital X here. And my sector is just my position, integer division with 512. If I found a match, there's no reason to continue with the other finders for this sector. So I break. I go to the next sector. The break gets me out of this for loop right here. I update my position by adding to it 512 times the cluster size, and then I read in the next cluster. This brings me back to the top of my while loop, and it will check to see if I got anything or if I'm at the end of the file. Here, I use my standard trick in Python where I check to see if _name _ is equal to the string _main _. If it is, I call make. So it's a fairly simple script. Let's go ahead and run it. So I'm going to go ahead and run this on my image that I've used before. Run find files. And if I just run it with no arguments, it's going to say, well, that's not going to work. What if I run it as find files -- help? Now it gives me this help screen. And you can see this was automatically generated for me by the option parser. So I didn't have to do anything. I'll say find files. I'll give it an image file. And I will look for images. And I'll stick with that. I won't give it an offset or anything else. And that has run. I'm going to go ahead and stop it. Let me run it again with some slightly different options. This time, I'm going to say I would like to see PDF files and bitmaps. And I will give it an offset of 63 sectors to the beginning of the file system. So you can see I've gotten several hits for bitmaps, and I'm sure there's some PDFs in there as well. So I'm going to go ahead and stop this. Now, you could obviously expand this very easily if you decided that you wanted to search for some additional file types that I haven't listed. You just have to get the appropriate text from the file utility and then search for that. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon.